have to start. I think many people will be delayed, but I hope they will come. So the first session today is the session of broadly understood atomic physics 2. We'll have representatives of 3 universities which are working with us, especially with Professor Żążewski, since many years. And our first speaker today will be Professor Marek Trippenbach, who was my supervisor of master thesis when I was studying at Warsaw University. Słucham? So he was a dean, vice dean of Faculty of Physics for some time. He finished his PhD many years ago under supervision of Professor Żążewski. And now we'll talk about topological phase transition for quantum rotor Bose-Einstein condensate. So please, the floor is yours.
Good morning. Good morning. Thank you all for coming early in the morning. I was afraid that first talk I'll have no audience, but there is still maybe those people who can listen. So, okay. So my talk is actually about Bose-Einstein condensate in spin-dependent optical lattice. And the talk will be divided into 4 parts. First will be something about my connection to Center for Theoretical Physics. Second will be just my interest and the general interest, the subject that I'm interested in recently. And the third will be about Bose-Einstein condensate in spin-dependent optical lattices. So the third one I don't understand. The subject, so it is even more interesting because it's easy to talk about things that you understand. First, my connections. So I found some pictures from the first conference, Quantum Optics Conference. And you can see people, those pictures are from my friend, Vietnamese friend Cao Long Van. He was collecting pictures. And so here you see Eberly and Cao Long Van. Here you see Mariusz Gajda, how he looks like many years ago. I'm here, also with mustache. And here you have Jakub Zakrzewski, also look a little bit different. Kazik Żążewski. And those are 2 pictures, I think, more private. One is Professor Białynicki-Birula. This is a child of Cao Long Van and Professor Białynicki looking a little bit younger. And I think at the same time, Kazik was also present and he's here. So you can imagine what is the difference with years. And here is Danuta, wife of Kazik, and my friend Cao Long Van. My connection with Center for Theoretical Physics is mostly through Professor Kazimierz Żążewski, and I met him when I studied in the so-called individual group studies at my department. So there were a couple of people that had a different program, and Kazik was teaching quantum mechanics, and I liked the course, so I asked him if I can do master thesis, and with him, and I did, and then, you know, it was great. We published a paper with Mike Raymer, so I thought, oh wow, I just jump in the international society with Kazik. Well, the thing is that I met Raymer like 5 years after publication of these papers, and I told him, hello, my name is Marek Trippenbach, and we have a paper together. So that was our collaboration. Later on, I did my PhD with Kazik. And, you know, collaboration then was mostly toward Russian direction. And and this is the title. This was about atoms in the strong fields. Well, has nothing to do with what people are doing right now, those prehistorical preliminaries that we were doing. No, yeah, but I'm saying that the people who are working now, they're doing much more advanced models and stuff. But this was a Kiełdysz model, and the starting of the. I think this was thanks to Maciek who introduced the Kiełdysz model, and then we did some calculations about this. I even published a paper with Maciek and Jaś Mostowski. This is the only paper that we have together so far. So that was my time at Zakład Fizyki Teoretycznej. And then I moved back to the university. And today I am interested in two kinds of subjects. One is about non-Hermitian dynamics. This is Hamiltonians. Hermitian Hamiltonians are boring. Well, this is not true. Of course, they are exciting and there are many other things. But if I advertise my work, I show that PT-symmetric and non-Hermitian stuff is also exciting. So the stuff that we are doing about this was related. The first project was sort of initiated by experiment with Bose-Einstein condensate in the polaritons. And so we consider, of course, some specific case. The Bose-Einstein condensate of polariton gases are very specific. They are made of photons and excitons, and they are leaking, so people were actually considering and discussing whether they are still condensates or they are maybe like laser states. But regardless of that, the dynamics is definitely not Hermitian because you have gain and loss. There are particles that are coming into the condensate. There are two branches, and you're constantly pumping them, so there is at least linear loss. There's also saturation, and if you consider saturation and expand it, then you get something that is equivalent to nonlinear, sorry, I said loss. There is linear gain because of pumping particles there, but if you consider saturation, then the saturation is equivalent to the nonlinear loss in a certain limit. So we considered the case of potential that was done by the bump in the external potential of the form of the bump, then the condensate is formed in the form of the pressure around it, and if you have a spin 1/2 atoms, then they can interact, and basically the system can be described by two coupled equations. Two nonlinear Schrödinger equations. And if you have a nonlinear loss and linear gain, those equations are very dynamically interesting because, and this is the work that we did with Kuba Zakrzewski, so this is exactly why I mention it here, because this was a joint project. What you get is you find that there are some stable states, and they are antisymmetric with respect to the change of the ring that I showed you before. But if you start, for example, with the symmetric state, which is not stable, then the dynamics might be very interesting, and it of course includes all sort of symmetry breaking. You can find states that are not symmetric with respect to the change of the ring, with respect to the change, with respect to the the circle, so that you can break the local symmetry and symmetry between rings, and you can even have chaotic behavior. You can have limit circles. You can have purely chaotic behavior. So from the mathematical point of view, the system is very interesting. This is, for example, the plots of the chaotic behavior. So this is a spectrum given as a function of some control parameter. Moreover, the systems that are interested in very recently strongly investigated in optics, there are so-called PT-symmetric systems. So the systems with gain and loss. PT-symmetric is a very broad name, but in the context of optical system, it basically means that you have gain and loss, and they are balanced somehow. If you have, like, coming back again to those two rings case, the gain and you can have, for example, gain in one ring and loss in the other, and that system is called PT-symmetric. The system that people consider in the laboratories are usually waveguides. So basically, you have one core in which you have loss, and then balance gain in a second core, or for example cavities with part of them with gain, part of them with loss. There were a lot of experiments already, and first one was, I think, done by so first one I showed here was the waveguide that was divided into two cores, and in one there was pump beam, so there was a gain and there was a loss in the other part. Those systems are interesting because from the topological point of view, they have limited scattering, because somehow the propagation in one and the other direction are not equivalent. And then, because of that, if you propagate light in one direction, there's no scattering back, because the propagation in the other direction can be strongly suppressed. So basically, we are now working on similar projects that are related to the photonic crystal fibers, because photonic crystal fibers, you can have a lot of different roads, and you can realize much more interesting systems, configurations, including many channels, also balanced, and we have experimental group at Warsaw University that are producing those photonic crystal fibers, and they have their own glasses, and now we are working with them, trying to see whether they can do the balance between gain and loss. What you basically do in one channel, you put some extra wire, and then you generate the amplify the signal in one channel, and then you dop the other channel with centers that are actually absorbing light, and then you have a loss. And of course, the first breakthrough is to make the photonic crystal fibers with two cores. And then we can, if we manage to do this, the technology will be ready, then we can start playing, various things. The literature about this is quite big, and there are a lot of interesting effects. If you have, for example, a ring of the cores with loss and one compensating in a center with gain and stuff like this. So a lot of geometry, the geometrical effects and different aspects of the systems are actually predicted theoretically already, and I strongly believe that this system with photonic crystal fibers might be very interesting, and we may realize a lot of these things. One of them is all optical switch, because you can, depending on the intensity, you can put all the light in one channel or the second channel. And of course, you can do it also with this system. The problem is, with the PT-symmetric system, the problem is usually that, if you don't do it correctly, then everything goes in the gain channel and stuff like this. But nevertheless, you can still guide the light in one of the channels. Moreover, it seems to be more stable than the system without gain and loss. So it is very promising. There's also a lot of stuff that we do with the rings, with the PT-symmetric system. But maybe because of a very limited time and I want to take time with my colleagues, so that I will skip the things that are discussed a lot in this non-Hermitian physics of PT-symmetric systems, is the point where Okay, I have to go back. If you have a PT-symmetric system, why they are interesting? Why people discuss them a lot? The thing is, if you have a PT-symmetric system, there is a certain region, even though the Hamiltonian is not Hermitian, you still have a real eigenvalues. Okay, so that is equivalent to the Hermitian system in a sense. There are also unstable regions where you have, imaginary eigenvalues that is usually connected with either wave function going to 0 or going to infinity. But on the border between stable and unstable regimes, there is something very interesting. Those points are called exceptional points. And going around these points, you can have some very interesting effects. For example, in the waveguides, that leads to one-directional propagation. And one-direction propagation means that you have a very little scattering because there's no propagation in the other direction, as I mentioned before. Now, so that I'll skip. And from this experience, from these projects, I realized that maybe it is interesting to consider topological effects. You know, bicycles are everywhere, and so is topology. So we started to be interested in some topological effects. And of course, topology is studied in practically all the fields, so I'm showing very quickly this transparency. I don't think I need to convince you that the topology is very interesting in physics. Maybe I skip this. This was a couple of transparencies about, because there's some field that is now called topological photonics, where people are building lasers and amplifiers and various devices, using the fact that in the topological matter, usually the edge states are interesting. So you can build the systems like here, consisting of many centers, but what is interesting is the edge of the active medium. And you can build, Moti Segev is one of the leaders in this field. He's doing a lot of these experiments. Also the picture that I showed you with 2 wires in PT-symmetric configuration was also done in Moti Segev group, I think. The other one is Christodoulides in Florida, and a lot of theoretical work is done by my colleague from Lisbon, Konotop. So, you know, this is a rapidly developing field. I wanted to show you this transparency because this is, oops, I'm pressing the wrong button. Because that equation of motion is something that is similar to what we considered, you know, the linear loss and Saturay-Baird gain that can be expanded into nonlinear loss term. But I want now to spend a few minutes on the project that I do with Mariusz Gajda and Mirek Brewczyk. I was trying to select all the projects associated with people in the audience here and then Center for Theoretical Physics. That's why this selection was chosen. A lot of attention is given to the so-called artificial gauge potential and fields. People introduce potentials on atoms that are driven by the lattice. And using these artificial potentials, you can do a lot of interesting physics. Now, my idea about this was that maybe you don't have to do anything special about the lattices, because here people, you know, shake them and do various things, various tricks to introduce artificial potentials. I thought maybe we still did not explore the power of the and variety of the lattice effects if you introduce certain effects on the beams that are forming lattice. For example, you know, you can mix the polarizations, you can make airy beams, you can use beams with angular momentum. All of this is now developed and people doing a lot of experiments. So why not to do the lattice with the beams that are a little bit extraordinary and see what effects you can have. Okay, so here the story will be about something that is related to Einstein-de Haas effect. I will be talking about atoms with spin in the spin-dependent optical lattice. That is from the title. And basically, Einstein-de Haas effect is something that you can transfer angular momentum from the spins into the rotational angular momentum of your object, of your object of interest. For example, Bose-Einstein condensate. So, what is it all about? Imagine that you take rubidium atoms in the F1 state, this is a ground state here, with components of MF equal 1, 0, and -1, and you put it in the lattice in the crossed beams, but the beams have different polarizations. So there is a component in this direction, and there is a component perpendicular to this, and basically the beams are here. Polarizations are combination of EZ and the direction perpendicular, so vector perpendicular to the direction of propagation and EZ. So if you make a mixture of those two, and if you, my example will be with equal distribution between those two directions, so beta is equal to 1 over square root of 2, you can have a lattice. And if you calculate the potential from the first principle, so you take the potential, which is E times D, and you take the energy associated with this, like a second order Stark shift, what you see is that your potential will have vector, scalar and vector potential. And that's actually also tensor. But in this case that I consider here with J equal to 1, tensor part disappears. But what is the effect is that your atoms see not only the usually trapping potential, which is scalar, which is a product, scalar product of dagger times E, but there's also something that is resembling magnetic field, which is a vector product of E dagger times E, and I'm plotting here both potentials. Here this is a trapping potential, scalar part of the potential that is basically trapping atoms, and this is representing, because this is a vector field, this is representing the second part, which can be treated as a magnetic field. Of course, it is not really magnetic field, it is fictitious magnetic field, and for example, divergence of this field is not 0, so this is not basically something that you would call magnetic field, but this is a vector field. And if you consider, oh, this is the transparency, there should be another place. I just, okay, forget it. Now, you can put atom in one side of the lattice like this. And what you see is basically like an atom. If it is sitting close to the center of the well, of the side, is seeing rotationally invariant potentials, because they only start to see, okay, here I consider 6 beams, so this is hexagonal lattice, but I could consider 4 of them, and that would be quadratic lattice, but whatever, you see the at the edges of the side, you start to see effects that are related to the symmetry of your lattice, but in the center, this is cylindrically symmetric always, because it doesn't fill the edges, right? So if you consider atom, if you will solve Schrödinger equation, basically, because, and if you approximate those potentials with cylindrically symmetric potential, then the problem will have quantum number zeta, that is like angular momentum around this point, and you can numerate the state. This is a solution of Schrödinger equation for single atom. And I show here energy levels with zeta. Imagine that you have a harmonic, two-dimensional harmonic oscillator. There are two quantum numbers. One is a sum of excitation in each direction, and this is n in my case, and the other one is a difference. And the difference between excitations is called here zeta. So with this, I can identify all the states. Of course, I can numerically calculate, wave functions and energies of the system. And here, this is n equal to 1, n equal to 0 state, and here n equal to 1, zeta equal to plus and minus 1. Okay, I already have in the system magnetic field, fictitious magnetic field that I introduced through my laser beams, but I can also add in the z direction perpendicular to the okay, this is a two-dimensional system. So if I introduce in the z direction an extra magnetic field, my system and energies will depend on the extra magnetic field, and what you see is that the states change with the external magnetic field. What? Yeah, I'm done. This is the end. So what happens is that if you increase magnetic field, eventually what was previously a ground state will cross with the first excited state, and you will see the difference in the symmetry of the lowest energy state. Okay? So here I will explain why it happens in a minute, but here I plot population in each z component, in each mf component of my system, because this is a system with the spin equal to 1, so I have a component minus 1, 0, and 1. And if you plot the population versus external magnetic field, something happened, and this is now plotted as a function of the external magnetic field. But I can also plot it as a function of the ratio between this field and fictitious magnetic field. Fictitious magnetic field depends on the laser intensity, and this is a good measure for the value of the magnetic field. And you can realize that this crossing here is in the region when those fields, external magnetic field and the fictitious magnetic field, are of the same order. So basically this is of order of 1. If you see that, then suddenly something changed, because your ground state now is zeta equal to 1 state, and what happens is that that the symmetry is different. Now here is the total angular momentum. So up to the crossing there was equal to 0, then it's equal to 1, which means that in each component the sum of the spin angular momentum and orbital angular momentum must be equal to 0 here and 1 here. So if you look at the components, okay, so if you look at the various components, the total angular momentum in each of the components is in the, so on the top this is zeta equal to 0, so this is the ground state before the crossing, and you see that in order to have zeta equal to 0, you have to have in mf equal to 1, you have to have angular momentum equal to minus 1. So the sum is equal to 0. Here, there's no vortex. In this state, mf equal to 0, you just have angular momentum equal to 0, and in the other state, mf equal to 1, you have to have angular momentum equal to minus 1. In those states, this is zeta equal to 1, so after the crossing, the ground state after the crossing, and what you see is everywhere angular momentum is equal to 1. So, so this here is without vortex, this is with vortex with winding number 1, and here's 2. So what happens is that when you increase the external magnetic field, atoms are trying to minimize energy related to this external magnetic field. So they transfer atoms basically towards MF equal to 1. But in MF equal to 1, there is a difference. In one case, okay, so you see here how the population, MF equal to -1 basically doesn't change, but population in MF equal to 0 and 1, I think it's +1, yeah, they differ very strongly. For example, this is much more in MF equal to +1. But if you look at the states, at the what happens with the angular momentum, there is a difference in angular momentum and F equal to 1 because the vortex is stronger. Now what happens is that with this orbital angular momentum there is kinetic energy associated. So it is better for the state to minimize. So when you transfer atoms to this higher MF equal states, you are losing. In one case you're losing kinetic energy. Here is the plot. Sorry. Now I am in trouble. Can I go to the last transparency? Yes. Yes, so that's my last two sentences. What you see here is this is kinetic energy. In zeta equal to 1, it is growing. Zeta equal to 0, it's growing. In zeta equal to 1, it's decreasing. So basically, at the point of crossing, of this energy crossing, it is better to go into the state of zeta equal to 1, and the energy is lower there. So now I said that I'm talking about something that I don't understand, because now we are debating whether this is a topological phase transition or what is it. And I don't know, because we're trying to calculate Chern numbers and we didn't succeed yet. So this is a work in progress. Thank you very much.
So thank you. Now we have time for questions, but like 1 or 2 quick questions, not more. Maybe I can ask.
So thank you for the nice talk. If you transfer or want to transfer angular momentum from internal to external degrees in an interacting system, then you usually need anisotropic interaction potentials. Yes. Now you talk about single particle physics, right? It's not an interacting system of 2 atoms, right? As far as I understand it. But you are scattering with this light-induced potential, right? Is this correct? And is it the anisotropy of that artificial magnetic field that is causing this, or
no? I think
you have a monopole, basically, or?
You can have interactions if you consider BC, if you consider more atoms, right? I am only talking now about single site. Of course, it will be even more interesting if I will consider, states which are, which will be really over the whole lattice, right? It will be going to the edges, and we do it right now. We do this calculation. Now, if I consider BC, there is extra nonlinear energy, right? And I think that if I have the system constructed like I was presenting here, there is no asymmetry at all. And this crossing of the energy is a real crossing. But I can do avoided crossing if I introduce a slight asymmetry. And then I will have really, going on the... So that we also were calculating, You can add some extra, harmonic potential that is a little bit different in X and Y direction, and then you will induce avoided crossings. And you will, okay. So that's a very good remark, and that was something that we understand, but still, I don't know. The topological phase transition is something when you change something in the system when you change number of what's called singularities. Or so I don't know if we do that. And of course, usually people talk about topological phase transitions on the lattice using like Bose-Hubbard models. Here we can also write the Bose-Hubbard equations for that. But I'm still learning how to translate the language of the topological phase transition that is not like quantum phase transition. It has a different aspects to it. I'm trying to understand how I can classify this effect that I have here. Thank you.
Okay. So thank you. Let's thank the speaker again.
Thank you.
So our next speaker is Professor Jakub Zakrzewski. Yesterday we had some linguistic discussions about Zakład, so I think he's the head of Zakład inside Jagiellonian University. We should know that there were many beautiful experiments about many-body localization in ultra-cold atoms, and that's why I'm curious about the talk, does many-body localization really exist, given that it was measured? So,
if I will manage to do with this artificial things and artificial fields, hopefully it works. Okay. So then there is this absolutely marvelous design which allows me to point to this department, which is this Abteilung or Zakład Optyki Atomowej. So Atomic Optics Department, since we have a historical session, it was founded 50 years ago or so by late Professor Kunish, and who was, they founded the Atomic Optics Department when there was no atomic optics in the world yet. With current meaning. What they were thinking of was spectroscopy, but they didn't want to found the Abteilung of spectroscopy because there was other Abteilung in the institute like this. So they created the name Atomic Optics. Okay, so these are, I also like to give thanks to people with whom I work at the beginning, because I will forget. So this is the bunch of people involved, starting with a student from China whom I got from Maciek, and we worked only over the email almost. With Maciek, I have a privilege of having something like 35 or 36 papers, and the same amount with Dominique Delalande, and there are other people involved in this business. So what I will speak about roughly is first my link with conformal, not with conformal field theory, but with CFT, and then a little bit about many-body localization in something which I call before Suntice time. And then there is something after Suntice, I will explain it, a little bit about Rydberg atoms, and I will not reach conclusions probably because we are running out of time usually. So then there is this Zakład Fizyki Teoretycznej PAN, where I have found myself thanks to these two gentlemen, who, as this is Tomasz Dochnalik, the previous head of my Abteilung in Krakow, and he slept with Kazik Zążewski, as I understand, in the same room on Karczew's school, where they met, or at least they met there. In Trieste, but in the same room. This is important. So they became friends, and then Tomasz said that he has some crazy student who needs to be tempered, and so this is how I landed collaborating with Kazik, and also then I met Maciek already because he came in 1980 with Kazik to Krakow for a visit, if I remember. So my links, let's say, with Kazik started around 1981, when I had a short PhD studies ending with PhD in 84. So as I understand, I was the second PhD student, but the first really graduating under Kazik. And the funny thing was, again, that this defense was in 84, but my PhD officially is in 85 because the council couldn't meet because of the martial law. So I couldn't get the PhD formally. And it was also on strong laser field ionization, because this was Kazik's subject. So it was with me, with Maciek, it was with me, and later with Marek Trippenbach. And as you see, I still sometimes work on the same topic. Still, here it was single electron, and now we consider free electron ab initio simulations. And in this work, we have some Dali's plots together with Maciek, which is such kind of visualization to strong field ionization coming from particle physics, let's say. Okay, so this is the link with this nice institution, which I congratulate very much on the 30th birthday. I wanted to sing the song, but you are saved from it because Mariusz played the 40-latek yesterday, so I will not repeat the joke. And then I come to the subject of my talk, many-body localization, the famous experiment which you probably know. The idea is to show in the many-body interacting system that it doesn't have to thermalize. Normally, if you have particles interacting, like in the cup of tea, then particles interact and thermalize. If you prepare the in optical lattice atoms in every second site, so you have population in let's say odd sites and no atoms in the even sites, then due to interaction such a system should thermalize and forget about the initial condition. If you put the system in strong disorder, sufficient disorder, there's some Hamiltonian, blah, blah, then it turns out that the system remembers that outsides were more occupied and is non-ergodic and localized. And it was very surprising to a lot of theoretically thinking people, particularly in condensed matter physics. So there were plenty of models studied, and one of, as you see, we are jumping from atomic physics and bosons or fermions on the lattice to spins, because spins are easier to treat in some sense, and the well, you can have spin up and spin down for. So Hilbert space has two states per side, so it is easier to treat. This is such standard Heisenberg, in fact, chain with disorder potential, and then what one can study time dynamics, but I will not speak about it. Instead, I will speak about boring, according to Marek Trippenbach, real eigenvalues, that is spectral properties of the system. And then what you can calculate is something which is called in quantum chaos, which was the area I had the pleasure to work with for a long time, level spacing. But the nice measure which was introduced by Oganessian quite late in 2007 is the ratio of spacing. So you take the spacing delta n and you calculate the minimum of two consecutive spacing to maximum of this two consecutive spacing. So this number is between 0 and 1. It's dimensionless, so you don't care about density of states, about all the fluctuations are in this simple variable, and you don't have any problem with changing density of states of the system. And then you can study statistics of this thing, calculate distributions, but if you are lazy, you calculate just the average value of this thing, and then you see on this plot that there is some magic value 0.53, which is reached for very small disorder. This corresponds to ergodic situation and Gaussian orthogonal ensemble of random matrices. And if disorder is sufficiently large, then we reach a value which is 0.3893 something, and this corresponds analytically to Poissonian ensemble, which means to totally integrable system. And this can, in the early days of this physics, you diagonalize matrices for different system sizes, which is this K here, and made the finite size scaling analysis, putting these curves together on a single curve, and this way one could extract information about this transition. There was even a mathematical proof that in gapped systems with short-range interactions, MBL exists. Under some weak assumptions, except that there is very few people who claim that understand this paper. I don't understand this paper. And instead we do a lot of numerical studies. One thing which is worrying about this picture, which was obtained already by David Hughes and Oganessian in 2007 for some slightly different system, studied by David Lewis, by us, is that this critical exponent here breaks some fundamental bounds which should appear for one-dimensional random systems. Something is wrong, and nobody knows what is wrong. So when there was guys coming from Slovenia in the group of Thomas Prozen and Lev Widmar, who published very influential paper. This is 2020, but really this is beginning of 2019, except that this paper went through, I think it started with Nature, was rejected from Nature, from Acta Physica Polonica, from everything, and finally landed in PhysRev.E after 2 years of struggling and having something like 70 citations already when it was being published. So this is kind of a record. What they consider is other quantity, which is the spectral form factor, which is defined in this way. This G is a Gaussian function on eigenvalues, which just selects most of them except the edges, and you make the something like Fourier transform of this function appropriately scaled, and then if you do it for random numbers coming from GOE ensemble, that this line, dashed line, gives you the straight line for small times tau, and when the dephasing really occurs, then you have at this something which is called the Heisenberg time, so the inverse of mean level spacing, which is equal to 1 here, you get a flat value. And then if you calculate this property for the spins, for some physical system, then you can see typical behavior as a function of disorder. You see there is no red colors here, so it is, you can see different colors. And then this thing evolves somehow, in some way, and then at certain values of time reaches the Heisenberg time. Reaches the curve corresponding to GOE, so reaches the ergodic behavior. This is called tauless time. And then if this tauless time is much less than Heisenberg time, like here for low disorder, then we are in the ergodic situation. On the other hand, if this tauless time is bigger than Heisenberg time, so you never explore the full system, really, you don't reach the edges, then you have system which is localized. And now, taking again some complicated, for some reason, spin system, they have shown surprisingly that this tauless time, it scales with exponentially with disorder size, so this is not a problem. But what they have shown by the careful analysis of different system sizes, that if you superimpose the system sizes, apparently the tauless times scales like L square, system size square, polynomially. If it scales polynomially, and Heisenberg time, which is related to mean level spacing, scales exponentially, this means that tauless time must be shorter than Heisenberg time for some system sizes. So if we go to larger and larger system sizes, there will be no MBL. So whether MBL exists or not is started to be an open question. These are serious people and serious analysis. So then we jumped on it with Piotr and Dominic. And first we wanted to understand what happens with Anderson transition, which we know that it occurs. There is Anderson transition for non-interacting particles, and it always occurs for any disorder for 1 or 2 dimensions, and then there is a transition from localized to extended states. So we took the system for, let's say, 3 dimensions, and we see again the similar scaling of the tauless time until a certain system's sizes, which we could go now to large systems, where this behavior breaks. If you scale these curves by the volume, then you nicely find the critical transition between localized and delocalized states. if you go to dimension equal 5, then the situation resembles more the case seen by Suntais. But if you rescale the system, you again see the transition. So what happens? What happens was our idea was that simply we don't have sufficiently large system in 5 dimensions. So we have to go to larger system sizes, and when you have larger system sizes, we break this scaling found by Thomas Prosen and co-workers. And indeed, this is the standard paradigmatic XXZ or Heisenberg chain with larger system sizes, which we extended thanks to Fabien Allet from Toulouse. It was enough to send him email, do you have eigenvalues? And by the reverse email we got the link, here are eigenvalues, get them and use them. Okay, and so these are these eigenvalues, and we have seen that there is a deviation for this system with short-range interactions. On the other hand, for the repeating the calculations for the system of Suntais, we didn't see it because we have smaller system sizes, because this was system with larger tunnelings to next nearest neighbors. So then with Piotrek Sierand it is not as easy, because if you cannot diagonalize matrices of size 24, then he devised his own diagonalizing scheme, improving the diagonalizing library, creating something which he called Porfet. I will not explain how it works, but then he was able and we were able with Maciek Lewenstein because Piotrek was then with Maciek in ICFO to extend the diagonalization up to sizes 24, and again seeing this deviation from the leading behavior, which somehow suggests that maybe MBL really exists, but it is not a proof. What we could do is do very careful statistical analysis. I hope Mr. Chairman keeps the track of the time. No, we are not doing so bad. What is plotted here is either this gap ratio, which I told you, as a function of the system size and as a function of disorder. The color means the disorder. And as you see, when we increase the system size, typically this thing is, let's say, around Poisson limit, integrable, and then with increasing system size, it starts to bend up towards the localization. We cannot go much larger because we have no tools for diagonalizing systems which are larger. So this is, and nobody has these tools. So this is the problem. This is diagonalization of Hamiltonian matrices. You extract something like 1,000 or 2,000 eigenvalues from the middle of the spectrum, from the middle of the matrix, not from the bottom. For L equal 24, maybe 100,000. Okay, but you are getting 1 or 2 eigenvalues for these matrices. Yes. And also we need...
You cannot use lunch as normal because you're not looking on the ground state. You have to make trips because you... Yes, no. Maciek. You have to use a code which is polarized, which is vectorized.
Krzysztof. Okay. I take this time.
There are some efficient codes which are polarized, vectorized for the architecture. These grounds hundreds of faster than anything else.
And they cannot be used. What we have here, if we don't diagonalize a single Hamiltonian, for which we extract couple of low-lying eigenvalues after a month of calculation, but we are diagonalizing, let's say, 2,000 disorder realizations. So we have to diagonalize 2,000 of these matrices, okay, and extract from each of them something like 1,000 eigenvalues to have the statistics of 1 million or 2 million eigenvalues. Not in the middle. And when you make so-called shift and invert, the standard thing is the shift and invert of the matrix. So when you transfer them to the ground state, to the extremes, and then you can use Lanczos. Except that shift and invert, what it does is you lose the band structure of the matrix, and then the memory of the computer fails because you easily reach sizes of memories which are above options. Very, very nice, and it's not enough. I have Tera machine at my disposal, my own disposal. Okay, I have 2 Tera in Slovenia. It's not enough. No, okay, but it's not enough for 2000 diagonalization of these matrices because we will wait too long. Maybe we can discuss it, Krzysztof, later. I mean, I can tell you how many hours we use of supercomputer on how many processors. Okay. So then this is the statistics for this air-bar statistics, and this is so-called entanglement entropy, which you can measure with respect to maximally entangled state for the random matrix. It shows the same behavior, and in this way one can extract, let's say, the minima of this curve as the system size, and this is plotted here. So these are the data obtained as our border between localized phase and delocalized phase obtained from these plots from either entropy or the gap ratio. On the other hand, this line, which is here, is the line between critical and the thermal phase, and which we defined as the moment when this air bar starts to deviate from GOE, or when this entropy starts to deviate from 1. And this border is here. So for finite system sizes, let's say of the order of 20, we have, in fact, 3 phases, localized phase, thermal phase, and something which is called critical in the middle, and which depends on the system size, and only when we extrapolate, we may speculate that these lines cross somewhere for Heisenberg model at around this order equal 5, and somewhere in this J1, J2 model of the order of 12. So this suggests that MBL exists, but sizes around L equal 50 in diagonalization which are needed, and L equal 50 is for Krzysiek 2 to 50, and please diagonalize the matrix of the size 2 to 50. Okay, okay, fine. I will collaborate with you. We wanted to go in the different direction. Instead of going to bigger and bigger sizes in 5 minutes, fine. Instead of going to bigger and bigger sizes in brutal way suggested by Professor Pachucki, we wanted to go in the clever way. Clever way involves Rydberg atoms who have the property of Rydberg blockade. If you have one atom excited in one place, then the second atom can appear only sufficiently far apart. So in this way, such systems lead to Hamiltonians in which if there is a spin in a certain place, then the nearby sites are empty, which means the spin down, and which you obtain by such projection, and then the effective Hilbert space per site is less than 2, is some 1.1 or 1.2, which means that we can go to bigger and bigger system sizes. And when we made the same analysis, making this Rydberg blockade parameter alpha larger and larger, and comparing the same properties, the thermal value and the value coming from gap ratio statistics, these things now don't cross. They just go in parallel, suggesting that in this system, which we can go easily to sizes of the size 100 or more, in the system of Rydberg atoms, we predict, this is work done with with Trieste people, because Piotrek is now in Trieste, and this system, despite simplicity, doesn't show MBL. this can be also, we can look at other system which will be, let's say, spinless disorder fermions, but it seems that it has no interactions in the system, but there are interactions due to this projection operators which represent this Rydberg blockade structure. Again, the behavior is similar with system size, no crossing, and we can explain that in this system, the presence of disorder and this Coulomb blockade induces very long interaction, very long-range interactions, leading to the localization. So very long-range interaction lead to the localizations, and then this system doesn't have MBL. So I skip the last part, which is about disorder-free systems, so which require less effort. And I just say that the thermodynamic limit of MBL remains the open question. We don't know whether it really exists in the thermodynamic limit or not. Certainly for some, I hope that for some systems it exists. One thing which we are doing now is analyzing time dynamics of much larger systems, because for time dynamics we can use tensor networks and study time evolution. But even reaching the system size of the order of 400, we have a price we pay for it, which is the length of time for which we look at the evolution. And again, the data which are being prepared for publication are not conclusive. We cannot, from the, well, what we need in this area maybe Mr. Nurkowski or somebody who will solve everything analytically. Because otherwise, computers can only give hints, but they very rarely give definite conclusions. And apparently, the mathematical proof of Mr. Imbri is not so well mathematically founded as it seems to be. Okay, so this is the end of my talk. I apologize to Narodowe Centrum Nauki that this is not read, but it should be read. Okay, thank you very much.
So thank you for the talk and being on time. Now we have time for questions.
Kuba, one of the mechanisms of lack of thermalization, as far as I understand, could be confinement, which occurs in lattice gauge theories and which we even study with theta's. This is disorder-free, so does this can be interpreted or related to many-body localization or not?
It can. I think it can be related to many-body localization. There are other systems using this question. One systems are lattice, are these gauge theories which have a global conservation law for the whole system, with, for example, Gauss law or something, which introduce the bounds on the system, which lead to lack of thermalization. Okay, the other systems, very simple systems which are studied for last 2 years, were systems without disorder, but with either this is the system with harmonic trap, which we studied also with theta's, or the system with tilted lattice, something like Stark effect or just tilted lattice. So when the sites are non-resonant, okay, and without interactions there is so-called Wannier-Stark localization, which are analog of Anderson localization, let's say, but without disorder. And in many body systems also these things localize. And in harmonic trap, in fact, what we observe is that if we put these atoms in strong harmonic trap, non-weak like in experiments, but in strong harmonic trap, then in the middle, well, the local electric field, which you can define like this, in the middle it is low, so the system delocalizes, and in the outside part, it remembers that this some sites were occupied, they are blue, and some other sites are not unoccupied. So here the system is delocalized, is localized, and in the middle is the localized, and we have some kind of phase separation and the border between localized and the localized sites. The nice thing of this paper was that it was immediately verified on some artificial ion chain by Chris Monroe group. So this is the first time that something in my life was so fastly proved, okay? Because it was identified very. The other thing was, of course, the laser, dress state laser, which we had with Maciek long time ago and seen by Tom Mosberg.
I think we should finish now. You need quantum simulators, apparently, to answer these kind of questions.
Yes. This is why we work with Maciek on various quantum simulators.
Okay, so let's thank the speaker again. And our next speaker will be Tomasz Karpiuk. He represents the University of Białystok. Tomek Karpiuk published his first paper, I think, in collaboration with Professor Żążewski more than 20 years ago. And after that time, the group of from Białystok, together with Mirosław Brewczyk, was visiting CFT regularly. Now Tomasz is an independent researcher. He finished his habilitation many years ago after postdoc in Singapore. He's collaborating with many French groups. And he's known from being extremely good in numerics, what is also supported by his knowledge in physics. So we can use his knowledge about effects, phenomenon, to improve substantially numerical calculations. So Tomasz, the floor is yours.
Thank you. Hello. Okay. Good morning, everyone. Yeah, okay. In today's talk, I would like to tell a few words about disruption of atomic dwarf by an artificial black hole. But in the first part of my talk, I will try to tell a few words about the connection, my connection with CFT. Then I will introduce Bose-Fermi droplet, which is a starting point for this simulation. And in the main part, I will tell about the subject which is visible in the title. So this particular work was done in collaboration with Marek Nikołajuk, Mirek Brewczyk and Mariusz Gajda. In fact, all of us are somehow connected to the Center for Theoretical Physics. For example, Marek Nikołajuk works with Professor Czerny, as I understand, and of course everyone knows Mariusz, and Mirosław Brewczyk was the supervisor of my PhD thesis, and in fact I know Kazik through Mirek Brewczyk. So when I started my scientific career, I started to work with Mirek Brewczyk, and he introduced me to Kazik. And in fact, my first work, which is probably here, was done in collaboration with Mirek Brewczyk and Kazik. And since that time, we collaborate together for, I believe, 20 or 21 years. And we published, if I'm not mistaken, together about 20 papers, or exactly 20 joint papers. Okay, and I want to tell a few words about one of these paper, which was done quite a long time ago, because this paper makes a, this is not in, okay, full screen mode. So first I would like to tell you about a few words about the work, which is quite old, about bright Bose-Fermi solitons, which makes a connection to the current work about three-dimensional droplets. So in this work we considered one-dimensional system of Bose-Fermi mixture. Bosons were repulsive, and the interaction between bosons was repulsive, but interaction between bosons and fermions was attractive, and if it was strong enough, then effectively systems start to attract. And So here you can see what happened when we change the interaction in such a way that this interaction becomes effectively attractive. So at the beginning we have a cloud of fermions in harmonic trap, which is very broad here. Here you see the density of this cloud, and this curve shows the density of bosonic component. This density is red, of course, but it's black on this beamer. And so now we change the interaction in such a way that effectively it becomes attractive. And if we do it rapidly, the system breaks, and we see three bright solitons, two-component solitons. They are traveling on the top of, let's say, Fermi C. So there is too much fermions here. So to form these three solitons, that's why we have still everything is running in the trap. Okay, and after 15 years, these solitons probably were observed by Cheng-Chin group. And so here you can see the density profiles of bare bosons without fermions. And here you see density of bosons, but in the mixture of bosons and fermions. So after the interaction, or rather magnetic field, is tuned in such a way that in this mixture is effectively attractive. In bare bosons, we see some oscillations, but if we have this mixture, we see these three peaks here, which they interpret as these two-component bright solitons, which we predicted many years ago. So this was our motivation to work on the droplets, because in 2015, Dima Petrov showed that it is possible to stabilize the three-dimensional droplet in Bose-Bose mixture by Li Huang-Yang correction, and these droplets were observed. But first they were observed in dipolar condensate by Tillman Pfau group. Okay, so we consider now I go to the main subject. So we consider three-dimensional Bose-Fermi mixture at zero temperature in free space. Fermions do not interact. Bosons interact repulsively, and then the interaction between bosons and fermions is attractive. We consider not only this simple interaction, but of course we add this Li Huang-Yang correction. So we add higher order corrections to interaction between bosons and also between bosons and fermions. If you look at the figure which shows how the scattering length of bosons and fermions depends, you can find two regions where you can make this mixture effectively attractive. So it's here and here. So in this cesium-lithium mixture, it is probably possible to observe these Bose-Fermi droplets. Okay, and a few words about the theory. So the simple terms, energy terms, is the kinetic energy of fermions, the interaction between bosons and interactions between bosons and fermions. These are these standard contact terms of interaction. But of course, we add this correction, Li Huang-Yang correction, which is used from 2015. Of course, it was discovered earlier, but in this field of called quantum gases, is usually connected to these droplets. But we also add correction to the interaction between bosons and fermions. In this form, it was calculated by Viverit and Giorgini. Unfortunately, this cannot be calculated fully analytically, so there is a term, this is this integral. It can be done over two coordinates, but still there is a third coordinate. But this integral can be tabularized and used in numerics. So we do it this way. And finally, we add. So all these terms can be added and it is done here. And then we add, let's say, so-called gradient correction for fermions, which is called Weizsäcker correction, and also kinetic energy for bosons, and this is full energy of this system. And the evolution of this system, time evolution, can be treated by quantum hydrodynamics. Okay, and for fermions, the equation looks, this hydrodynamic equations looks like that, and here is the term through which all these terms comes into this set of equations. In fact, we do, from technical point of view, we do inverse Madelung transformation, and we go from this hydrodynamic picture to Schrödinger-like equation. So finally, for fermions, yeah, we solve this equation. So we have this kinetic, let's say, energy terms, this simple interaction term between bosons and fermions, and this term which is a correction to this interaction. And for bosons we have so-called Gross-Pitayevsky equation, but of course it's modified by this Li Huang-Yang correction and this correction to the mutual interaction. So we solve numerically these two equations. And first step is to find the ground state. Oh, sorry. So first step is to find the ground state, and so this is done here. We start with a Gaussian, and then, as you can see, this system is self-trapped. We have density of fermions and bosons, and finally this droplet stabilizes. Yeah, this is density. So droplet, of course, is spherically symmetric. So this is just, so here you can see the radius. So this way, this droplet, as you can see, can be found. And of course, we can do, in real experiment, usually experimentalists will start with a harmonic trap. And so here are 3 examples of this droplet inside of the harmonic trap. So here we have mutual interaction, which is not enough to stabilize the droplet. Then there is an interaction which is on the border of the stability, and where we have a really stable droplet. And if we look at that, so if the interaction is too low, of course, if we remove the trap, everything's spread. So there is no stable droplet. If we do the same, but for interaction which is exactly on the border of the stability, and when the trap is released, we see that the droplet is oscillating. So here we have a bosonic component, here we have fermionic component, and these are cuts through all 3 planes. As you can see, droplet is oscillating, so this oscillation is damped. But finally, as you can see, it gets smaller, so the droplet is evaporating. Yeah, it's because we are on the border of the stability. Okay, and finally, we have third situation when we should see stable droplet. Of course, this droplet oscillates because it was prepared in the cylindrical trap, and its oscillation in our theory, which is for 0 temperature, can take forever. Yeah, and now this oscillation is almost not damped. Okay, so we have stable droplet, and we wanted to do something, let's say, funny with this droplet. So one idea, in fact, it was Mirek Brewczyk idea, was to add potential which is similar to black hole potential. And I did such simulation, and we got some interesting, let's say, outcome. Then we started to search whether it can be related to something real in nature. So and we found through Marek Nikolajuk these papers about these ultra luminous flares observed in astrophysics, and these are papers about observation of such flares from 2 sources. And right after these papers, the appeared papers which interpreted this as a disruption of white dwarf by black hole. So we wanted to check whether our simulation can be related to this. So this is a figure from one of these papers, where here we see this very high luminosity flares coming from one of these source. Okay. First question is whether this atomic droplet can be a model of this white dwarf. So we assume that we will mimic a white dwarf which is made from helium. So inside there are helium nuclei and electrons. In fact, after some time, this object cooled down to about 10 to the power of 4, and after a long time to the 10 to the power of 3 kelvins. And at the same time, the electron, at the same time, the density of electron is very high. And it results that the Fermi temperature is few orders of magnitude larger than the white dwarf temperature. So from that point of view, electrons can be safely treated as a degenerate Fermi gas. And also this helium nuclei, the temperature of this, the temperature for condensation for this helium nuclei is 10 to the power of 5, which is about 2 orders of magnitude lower, higher than the temperature of this system. So also we can assume, at least at the beginning, that these helium nuclei are in the Bose-Einstein condensate. Of course, there are huge differences, because we do not consider long-range gravitational interactions. And in our case, we have short-range interaction, attractive interaction. And of course, in our simulation, we have neutral particles, not charged particles like here in real white dwarf. Okay, the second ingredient is this artificial black hole potential. I call it artificial because we assume that we want to observe this droplet in the experiment, in cold atom experiment, and of course such potential can be made by light. Yeah, nowadays experimentalists can tailor almost any shape of the potential, and of course they also can try to do such kind of potential, and such potential which can mimic this black hole, non-rotating black hole, was proposed, for example, by Paczynski and Vita, and we use this shape of potential. So we add these two terms to our equation. So here we have all these terms which I shown you before. Yeah. And we try to solve this system. In case of this two-body system, this binary system, there are possible three situations. All this depends on the total energy of this system. So we can have a hyperbolic orbit, parabolic orbit, and elliptical orbit. In fact, in our simulation, we will consider this situation when we have elliptical orbit. So this can be set by properly setting initial position and initial velocity of our droplet, and of course mass. So this will define all the other these quantities, and this way we will have elliptical orbit. So in the first simulation, we have such parameters that at the beginning our droplet is here. So somewhere here is this black hole. And parameters are set in such a way that at the beginning we are at a periastron. Periastron is the place which is closest to the in this case to the black hole. So then after some time we will be on the opposite side, and again possibly at the periastron. It depends what will happen. Okay, and this is the outcome. So what we see here. So here we have density of bosonic component and density of fermionic component. This is in linear scale. This is in logarithmic scale. So we see the droplet is here bigger because we have logarithmic scale. These are cuts through other directions. So let's focus on let's say these figures. As I said at the beginning, we are at a periastron. We see that there is opens a pipe between this bosonic density and the black hole, which is in the center. So the matter is falling on a black hole. Of course, if this matter would be charged, this matter is accelerated and it should radiate when falling. So okay, now we are somewhere on the opposite side. We see that some accretion disk, initial accretion disk is formed. So here you can see the cuts through this, from other direction, the cuts through this accretion disk. Here we see fermionic component. You can see that fermions are not falling during this passage on the black hole. Only bosonic component is falling. Bosons are simply much heavier. Okay, then we are on the opposite side of the periastron, and for a moment we'll be seeing a second passage through the periastron. Again, some matter is falling on a black hole. Unfortunately, we have here periodic boundary conditions, so there are some interferences. And finally, a huge amount of mass is falling on the black hole. And in this passage, also fermionic component is stripped from this droplet, and a huge accretion disk is formed, and the remaining of the droplet is leaving this binary system. Okay, and here you can see the figure which shows amount of bosonic mass which is falling at each periastron passage. So at the beginning, about 10 to the minus of 5 mass is stripped. Then again, 10 to the minus of 4. And finally, in this final passage, we see the destruction of this binary system. Okay. Yeah. The second example is just one passage during which this system is destroyed, just at one passage. Okay, maybe this is not very important, but maybe more important thing is what will when we look closer to this to one of these figure. Yeah, for example, here we see that because we have quantum hydrodynamics, we see quantized vortices here. If it would be scaled to astronomical sizes, it would be giant quantum vortices. And also matter, when matter is falling, we see that this matter gets fragmented. Yeah, all these things can be a source of fluctuation of radiation when this quantum matter is falling on the black hole. So the last question is whether we can relate this small droplet to real astronomical object, and so we can try such rescaling. Okay, maybe all these equations now are not important, but of course we can do that. These A, B, and C constant are not known. Before we say something about our white dwarf, this real astronomical, and about black hole. Of course, we can assume something, some typical numbers for the mass of black hole, and also for our white dwarf. And if we do so, we will find that the luminosity is about 2 orders of magnitude too large if compared to these real astronomical observations. And also time when the flare rise, or time which is when the maybe not rise but lasts, is also about 2 orders too short. Of course, in our simulations, our system is very tight. It is also because this simulation is faster in such configuration. If we would do simulation when this droplet is further from the black hole, probably it would be better. So we run such simulations now, but it's still not analyzed, and I cannot say whether it will look better. So finally, our calculations have shown that the matter is fragmented when it's falling, and it can be responsible for this ultra-luminous burst. So what was probably never considered for astronomical object is the formation of these giant quantized vortices. Okay, that's all. So thank you.
So thank you for this interdisciplinary talk. And I see that you have many questions. Maybe first Timan and then Agnieszka.
Thank you for that very nice talk. I have 2 questions actually. The first one is about the treatment of the dynamics. You assume a local density approximation if you introduce that LHY term the way you do, and also I guess this fermionic correction that you have also assumes a local density approximation. So all the lengths, all the sizes of what you are simulating should be large compared to any of those relevant length scale. Is this so? I mean, the healing length and all the lengths should be much smaller than any of the structures that you are getting here in these simulations. Otherwise, the LHY term that you are putting here, of course, is not the correct one. Yes, it has to. There will be finite size corrections. So that's the first question.
So probably you are right. I'm not very good at these theoretical considerations, but yeah, probably you are right. Yeah, that we should be careful doing this hydrodynamics with that.
Yes, I mean, especially in the last numerical, I mean, this dynamical, I saw very fine structures, very detailed, small things, and one needs to make sure, that all of these things are still still larger than the. And then the second question is about the thermalization. I mean, if you have a dynamics around that black hole, then you do a effective GP simulation. But if I would do this experiment, then I would be afraid that also two-body collisions lead to a thermalization in the system. Do you think this is all? I mean, and also, of course, in the real system, there will be timescales for that thermalization that could, for example, kill such a vortex formation in the end that you are so interested in.
Yeah, we looked slightly at that, especially at this bosonic component. We can treat this bosonic component with a classical field approximation.
Exactly.
And we looked how long it takes, the thermalization of this accretion disk. We are not focused on that, but yeah, we can try to do it. I mean, somehow. And the second thing, of course, is that we do not consider really the heating here. I mean, and in a real astronomical system, probably it is very important. And of course, this is not also like the case in our simulation. We were not focused on that.
Okay, good. Yeah, thank you.
Hello, thank you very much for a very interesting presentation. And I'd like to ask about your simulation of this white dwarf and black hole binary. So I understand that you are using the code units, dimensionless scaling, but first, what is the mass ratio between the black hole and the white dwarf? Is it a supermassive black hole and a white dwarf, or they are similar mass?
No, I think it is so it is immediate mass. I mean, so
you have here 10 to the 4 solar masses. The
so
black
this
hole.
is in astronomy for astrophysicists. It's some.
Okay, so it's 10,000. This mass ratio is about 10,000.
It's not a supermassive black hole.
Yeah, I see. It's intermediate, but yeah. So I would like to comment that this interpretation of the gamma ray burst is a little bit risky here, because gamma ray bursts are probably originating from stellar mass black holes. But anyway, the idea is interesting. And the second question is how close your material is reaching the black hole. I mean, you are using Newtonian gravity, yeah? So in terms of gravitational radius of this black hole, how close it is?
You mean how close to
the periastron or the size of the accretion disk?
To the Schwarzschild radius.
Yes.
Yeah. Yeah. In our simulation, this in fact this Schwarzschild radius, I think it's even not visible. Yeah, it's so small that it's even not taken into account in the first step on the lattice. So from this point of view, this matter is rather far away. Okay.
Okay, I see maybe the last question, and then we'll continue during the coffee break.
That's a very nice talk. Thank you very much. I want to make a couple of comments and pose a question. So these vortices of great interest at the moment. Cosmologists are very interested in the idea that the dark matter is a 10 to the minus 22 eV scalar field. And when they do simulation, they realize these vortices will form. The simplest way to see it is not with the Schrödinger equation, but with the Madelung equation from 1925, where you take the Schrödinger equation and show that it's equivalent to, you get an Euler equation with the velocity. One of the interesting things is, on these vortices, the velocity is divergent. It becomes bigger than the speed of light. And so there's
you mean
something
inside of the core of the vortex? Yeah. Okay.
And the other thing, the other comment is it's all been reinvented in the field of quantum optics, which is reinventing something which was realized by people doing classical optics for adaptive optics, which is that in a telescope beam you will have vortices in the light. And this is very nasty for people who want to use rubber mirrors in big telescopes to correct for the refraction of the atmosphere. But I've looked at this a bit. My impression is these vortices don't do anything interesting in terms of something we could actually observe in the universe. What do you think?
Okay, now we are working, because, what I said here is in fact, it's not quantitative, it was our qualitative, believings. And now we are working really to extract the radiation from this system. And, if it will be done, maybe I could answer your question. If it's true or not, yeah. We are working on that now. Yeah.
I think this is discussion for the coffee break. It can last long. So thank you. Thanks again to all speakers of this session. And now we have the coffee break. I have short announcement that Professor Iwo Białynicki-Birula was really asking for having the opportunity to give a talk, but about research, not about history. That's why we'd like to shorten the lunch break by 10 minutes and start the session after the lunch 10 to 3. And then in this FNP session, at the end, there will be 20-minute talk of Professor Iwo Białynicki-Birula about time crystals made of positron electron pairs. So, thank you.
Przesyłam ci maila. Już patrzę. To jest dokładnie ten, który właśnie teraz dzisiaj.
Krzysztof Pachucki?
Czysty pomidor.
Tak.
Rozumiem, że nie musisz mojego laptopa.
Nie trzeba. Mogę od razu pokazać też. Rozumiem, że pan nas potrzeba.
Ale nie teraz, tylko po latach do tej pory zapomnę. Proponuję go dalej.
Mogę dać swojego pendrive'a pod wodę. Komputer tutaj.
Jak ja tam wejdę, to on nie będzie
Coś się bliżej kamerę.
No bo ja coś mam.
Tak, chodzi mi po prostu o to, że ja tutaj nie widzę niczego poza... A nie, to jest to. Będę widział jako następnej kamery, która tam zostawiona.
No dobrze.
Pan rozpoczyna na Okej, ale jakby mam tutaj zaznaczenie. Tak. Ja sobie go zostawię tutaj. Może zostać, czy pan będzie korzystał? No, niech zostanie, to wtedy będę pamiętał, jak zostaje, przyjdzie następnie dlatego. Po kolei.
Będzie zmieniał. Nie, dobrze.
Po prostu nie pokazuję czerwonego.
Place the atoms already, let's say, on the circumference of a square, let's say, and then you have already more, and then you can continue this, and so I don't think that 100 is a limit. So it could be larger, but you say that up to 100 you don't see any.
No, we don't. Well,
and you would expect if you go to 1,000, then you also know.
We for any system size, we see a transition for any system size, except that this transition shifts with the system size in a linear way. So the larger the system size, the later the transition. But this different geometries, as you say, may introduce additional effects. I was only concentrating on this thermodynamics. For example, we have work with Giovanna Morici and Edwin with Piotr and then our student on incavity, when one has all-to-all interactions mediated by photons, and then you also CFT, despite the fact that the interaction is long. Time was short. We have to remember this also.
That there's also in our institute and in many other places, there's an effort to build large-scale Rydberg quantum computers.
Yes.
Of simulators. Up to 1,000 units. And all of these people are looking for an application, a physics application. What can you do with a system other than just doing digital quantum computing or get the money for it? Yeah. But we are most interested in the physics, and if there are questions, like fundamental questions, like the thermodynamics, that is great. Yeah. Okay. And if we have a protocol or something, to test there.
Okay. So we will think about it. We will think about it. Yes, especially as you say, to expand it into let's say 2D some way. More. Yes. Yes, because indeed this can be proposed as the quantum simulator implementation.
And maybe eventually it's hard for you to simulate it on the computer, and
yes.
Quantum
yes,
simulator is the one that will answer this question. We are actually looking exactly for such problems. It's not so
I will be in touch. Yes. Okay. I got the message. I will discuss. I will be in touch.
Nie wiem jak się dół idzie, żeby nie zasłaniało.
Nie, ale jest luźno. Jest luźno w razie czego przesadzić też.
I odległość kablowa, żeby nam wystarczyła?
Tak.
Jeszcze nie wstawmy, czy pan leży?
Są te pistolet?
Bo to ma problem z
Dobra.
Mogę spróbować swój.
Możemy za jakieś 5 minut sprawdzić tą prezentację, bo my w tym momencie będziemy podmieniać projektor, żeby trochę lepiej to działało.
Może lepiej przed. Tak, no myślę, że 10
Chcielibyśmy z przerwy skorzystać, żeby naprawić tą sytuację z projektorem. Dlatego.
I would like to check the presentation.
Are you in the next session?
Next session.
Okay, so could you please wait because we have to...
Okay, I'll wait for you.
Next.
Czyściki. Nie, możemy fałgą z tego projektora.
Znaczy po prostu mam wejście do PAU w kąpie, ale mam przejściówkę. Sprawdzałem, przejściówka jest dobra.
Dobra, tu mamy
Trzeba go zagafować.
Dobra, to ja go postawię, a ty już się wpinaj w kompo. Pół godziny mamy?
Tak.
Właśnie wiedziałem, że trochę się przedłużyło. Pytanie, czy będzie przedłużony też jakby... Czy jak było opóźnienie, to będzie przedłużone, czy zaczynamy 11:30?
Ja ten wyłączam.
Fajnie byłoby tam tym wyłączyć.
Tak, właśnie. Dzień dobry.
Na pewno niżej. O kurde. Możemy zasłonić.
Tak,
czy nie możemy?
Tak, możemy. Co, nie widzi go? Komputer go widzi.
Nie, zaraz zmienimy sens.
Okej. O, jest.
Ej, no kurde, jest różnica. Są kolory.
Są kolory, no właśnie. No to chodziło. Teraz pytanie, czy nieco bliżej go dać? Niżej na tym, tutaj.
Nie do końca, tym może sobie wyregulujemy.
Mamy radę wyregulować.
To będzie zasłonięte, czy nie? Czy odsłaniają na...
Znaczy, mogę zostawić, ale po prostu włączyć światło troszeczkę.
Wiesz, spróbujmy jakby dać mu trochę więcej światła, czy... Dobra. Nie, no daje radę i tak.
fotografowania?
Albo tą panią może żeby sprawdzić prezentację, a ja tu będę ogarniał to.
Aha, dobra. To pana. Do you have your own laptop or we can use pen drive?
I was going to present using Google Slides, so I was guessing if it's okay to present.
Okay. Do you have a HDMI?
HDMI, yes. This is very nice. VGA would be a problem, so I think like this one.
Of course. Okay, let's try it. Just
Okay, right?
Okay. HDMI.
Alright, could you please change the screen view inside your computer so that
You mean
the FN and I don't want to
yeah, no problem. Yeah.
so that you duplicate the screen.
Yes. Okay.
To ty? Coś robiłeś?
Nie.
Yes. So it's automatically set to duplicate.
Wyruszasz kablem do tego pewnie.
Pomożesz mi na chwilę? Sekundę, tylko stolik przemieść wyżej. To może to pasujemy na równo. Tutaj, gdzie ja jestem.
A, to jest tutaj.
Tutaj, w tym miejscu. Piętro wyżej.
Na tej wysokości czy ci?
Tak. Na razie tak.
That. Sorry, but our capture card, I think it doesn't see your presentation in your computer.
Teraz to ty?
Nie. O.
Na pewno nie?
Na pewno nie. A co? Coś?
Teraz. Bo straciłam obraz. Może po prostu zrzucić na naszego kompa prezentację, czy nie?
Tak bym chciał.
Dla bezpieczeństwa zrzućmy może na nasz, panu tylko pilota dać.
Make a PDF.
Yeah, if that
Tyle.
possible, then please. Yes. It will be easy.
Do you have a USB?
Yeah, of course.
Okay, great.
There you go. You have your own.
Oh yes, yeah, oh yeah.
So yeah,
Oh,
let's not because we have our stickers, but let's try not to mess them up. And,
Oh yeah, because I'm
but
kind of the same brand.
we have stickers on ours. So.
Okay. That's.
Już ci rzucam gafer.
Mam tutaj w torbie.
W razie czego?
No poczekaj, tu ktoś siedzi na tym niezaklejonym, czy nie? Kojarzysz?
Możemy zamienić, jakby, albo powiedzieć, może był czerwieni.
Najwyżej tutaj.
New program. There it is.
Zostawić Ci na wszelki wypadek fałkę backupową?
Zostaw na wszelki wypadek, tak.
Się
Mam fałkę backupową, więc tutaj też byłoby dobrze.
To my z wyjścia HDMI, nie?
laptopie? Tak.
Nie w laptopie, tutaj. Mogę się podłączyć HDMI.
Ja swojego laptopa.
Tak.
Tak.
tylko nie wiem, czy już jest czas.
Mamy czerwony.
Jeszcze 3 minuty, tak?
Mamy czerwony, dziękuję.
Okay, I see everybody is coming here, so just slowly starting this session is called Alumni of the Center for Theoretical Physics, and we will hear in this session 4 talks by very young people. Our recent alumni, PhD, or just in a couple of weeks they will have a PhD awarded by our center. Maybe it is only worth to mention here one historical remark, because Center for Theoretical Physics is eligible to give the PhD degree only since, I think, 2015, while all the previous PhD dissertations were processed formally outside at the University of Warsaw or somewhere else, University of Kardynał Wyszyński. And since 2015, we are eligible to give our own diplomas with the logo and stamp of the Center for Theoretical Physics. The first person who was awarded this diploma is here today with us, Małgosia Siudek. She will speak later. And now we will start with the first talk by Piotr Grochowski, who is
not an alumnus.
Not an alumnus yet. You will have your PhD defense, I think, in a couple weeks.
Yeah, hopefully.
Hopefully, of course. But I saw your thesis and referee reports and opinion of your advisor, which is very enthusiastic. So.
But I'm still before the physics exam, which is supposed to be the hardest part.
Okay. So please feel free today to be relaxed and tell us something nice and funny about your research. Welcome.
Okay, so before the scientific part, as in the same way as a couple of my predecessors, I'm gonna reminisce about my, well, these couple of years in the CFT. Well, I cannot claim that I'm as scientifically old as the CFT itself. It's like 1/6 or 1/7, but still I have like really good memories working in here. So it started almost exactly 6 years ago when I was asked by the university to go for an internship somewhere. And to tell you the truth, I just randomly chose a person from our old beautiful website of CFT, and this person randomly chosen was Professor Żukowski. You know, after the second year of undergraduate studies, that couldn't be like a really educated choice. So, but all in all, I consider myself lucky when it comes to like both at the level of the choice of Professor Żukowski as my mentor, and at the level of the whole CFT, about like the level of being the part of the whole community. And first, I would like to thank all of the people of CFT, both present and not present, that I spent this couple of years with. So let's go for before I go to the like scientific part, like it's usually like you don't take pictures during your work, but somehow I managed to find a couple of them. I'm just gonna show you 2 of them. This is probably the one in the left is during one of the BEC seminars. It's like it was taken in March 2016. It's probably my first photo taken at CFT, and still at this it's like pre-pandemic. And the second one is like probably kind of a sneaky photo because I don't really remember taking it. It's in the room of Professor Żukowski during one of the, let's call it scientific exchanges. And Professor Gajda is present and our other alumnus, Rafał Łodziejewski. And it was taken just before the graduation of Rafał from the CFT. Okay, so let's go for the scientific part. And the first thing I want to do is to just show the faces of all of the people that were involved in the projects along my way in the CFT. So my collaborations with these projects were focused on in couple of, let's say, with people that were from couple of places. So we have the Warsaw part, which has of course Professor Żukowski, myself, and probably already a master or almost a master. Maciek Łebek, who has been with us for like last 3 years, I believe. Then we have our colleagues from Białystok that came basically every week on Wednesday to talk, to discuss with us and so on. So like our collaboration was really strong. Mirek Brewczyk and Tomek Karpiuk, who is probably here. I can see you. Okay, but he was here. And we have Martin Trappe from Singapore, who came as a postdoc to Professor Żążewski group like just before I came to CFT, and now our most recent collaborator, Andrzej Syrwicz, like I would like to say from Kraków, but he's already left Kraków, and right now he's in Stockholm. So it will be rather like an overview talk of like all of the methods, all of the projects that I did as a, well, bachelor, master, and PhD student in CFT. So let me, like, it will be quite a basic talk. So let me start with like so I will focus basically on 2 different physical systems that will try to show the same thing. And this thing is ferromagnetism. So when we think about the ferromagnetism, we think about like some piece of metal like nickel or iron or whatever that has like this robust property that it creates magnetic field. It's usually connected with the robust magnetic moment. And the question where this magnetic moment comes from was like, it couldn't be explained at the level of the classical electromagnetism. It was even rigorously proven by like independently by Niels Bohr and Hendrika von Leuven that on the basis of the just electromagnetism, the classical electromagnetism, there cannot be any magnetic ground state. When of course they were thinking about something like ensembles of the dipoles that like trying to align in the field. And like the explanation of the ferromagnetism was like really like a big success for quantum mechanics, like for these fathers of quantum mechanics. They introduced notions like spin, like Pauli exclusion principle, and let's say exchange interaction. And during these early days, there were 2 competing models. So when we think about the metal, we can think about these valence electrons like either localized at each atomic site. This is like a localized model. This was called the Heisenberg model, or like purely delocalized, or in other words, itinerant electrons. And that was called itinerant model or a Stoner model. So like probably most of you know this Heisenberg model, but this Stoner model is not so known. So what we think, like, so the most basic explanation of the Stoner model is that we can think about some effective repulsion between the different electrons of different spin. Of course, it's like a screened Coulomb interaction. So usually in the periodic systems, we translate our system into like, we represent our system in a momentum basis, or like, or like in a let's say energy representation, like giving density of states, telling us what states at which energies electrons occupy when we add them to the system. So the Stoner model tells us that if there is this repulsion between 2 different spin species, then the density of states for both spin up and spin down electrons are shifted with respect to each other. And when we add the electrons up to some Fermi level, there is an excess of, let's say, spin up atoms with respect to the spin down, giving us non-zero magnetization of the sample and some kind of magnetic moment and ferromagnetism. So, repulsion between the, so as you can see, these spectra are shifted like in different directions depending on the sign of the, like if it were like effective attraction, there will be shifted another way. I mean, they're just repelled with each other. Okay? This is like a phenomenological model, so probably just assumes the braking and shift. No, nothing. You just. Yeah. Okay. Magnetic field. Yeah. But okay. At this point, it doesn't matter because I'm gonna focus on the like ultra cold version, in which like everything will be clear. So this is like a really simple model. Okay. As you pointed out, it's like not very well based, but it's like there was like a lot of complications with that because like you couldn't really describe real solid state systems with it. And like the general answer to like what happens to the electrons in the metal is like much more complicated. It's like something in between this itinerant model and the localized model. But like we would like to ask a question: what happens if we consider like really simple Hamiltonians that divide by these fathers of quantum mechanics, and whether we can realize them in real life in experiment? So the answer for like specifically for the Stoner model is that we can do it in with ultra cold atoms. So probably equilibrium ones. Yeah. Yeah. Okay. I'm not. I don't want to go into detail because like I don't really remember how it was derived. It was like based on some like not very good assumptions. It just like this kind of repulsion can provide a change in the density of states. That was the point. And okay, it will be clearer for the ultra cold version at least. I hope. So. Instead of like looking for these really complicated metallic systems, we go for a systems easier to describe and realize in the lab. So we look at the gases of some atoms that are like extremely dilute. So the distances between the atoms in the given ensemble are much larger than the, let's say, length characteristic of for the potential between the atoms. So there is a like really good approximation then to the interaction between these two atoms, like meaning that this very good approximation means that they can only collide head-on. So like in all this partial wave expansion of the interaction, you can just take the lowest part, the S wave part. So we can just use a single parameter, which is called a scattering length, to describe the whole interaction in the system, and it can be described, like it can be modeled by the contact potential with some given strength. I will use also just as like this parameter, like I will also call this parameter just G. So in contrast to like the electronic system, there are like these gases are trapped with a very good approximation like in a harmonic trap, and we can imagine that we have a, let's say, a Fermi gas. We can imagine we have two different Zeeman states. So the difference between Zeeman states and like real spin states is that there's, due to this interaction, there is no spin flip. There is no spin flip mechanism. So if we prepare the sample with in a balanced way with like the same number of atoms in each species, they cannot change. It's like the spin number conserving system. So contrary to like this electronic system, we say that we have a ferromagnetic order if both clouds want to spatially separate, so to occupy different places in a harmonic trap. We will call this situation like analog ferromagnetic phase. So it's just a phase separation of two different fermionic gases. So they were done like with this system, like especially with lithium-6, there were done like quite a lot of experiments to see whether this phase-separated state really exists. It can be supported, but there was one big problem, because like in this experimental setup, in which, by the way, we can like freely tune the interaction strength, there is also like if you look just at the two-body problem with like spin-up, spin-down atom, you can see there is, apart from like this repulsive state, there is also a weakly bound state, which is called a dimer. So when they were trying to like quench into strong repulsion, when I say quench, just turn the interaction to like strong repulsion, they saw a lot of losses into the due to the creation of dimers. So they could in most of the experiments they couldn't see the separation. So what people did, and that was our motivation for the work back in 2015-16, was the experiment that was done in the lab of Giacomo Roati in Florence, in which they prepared this kind of system, which is initially separated by means of the magnetic field in a trap. Here is a trap. They separate both species and put an optical barrier between it. So it's like an artificial domain structure, artificial ferromagnetic state. And what they do, they just release the barrier and look whether it mixes or not, whether it's like this state is stable or not. So I'm not gonna tell you what happened to the experiment because I'm just gonna switch into our methods, our approaches and so on. And then you will see that the same thing will happen with our numerics. So our approach is similar to what Tomek said in the last talk. Well, it's the same approach. So we use so-called quantum hydrodynamics. So it's like alternative name is Madelung equations. And we usually when we represent fermions, we need, well, when you compare bosons to fermions, in order to describe bosons quite well, you only need to a single function. But then to describe fermions, you usually, due to the fact that they occupy consecutive energy levels, so different states, you need let's say for n fermions, you need n function to describe it. This is the easiest many-body approach to fermions. But we go even less deep, trying to describe the system with just the density of the single particle density of the fermionic cloud and the phase. So you can see it inside this function psi. We call it a pseudo wave function. We describe it as a square root of the density times some phase, which is connected. The gradient of this phase is just the center of mass velocity of, say, of this fictitious fluid, let's say. So we can imagine that we have our fermions that are a bit stationary, that move with some velocity that are given by this phase. And then we can write at the same level of approximation the Hamiltonian with the kinetic energy that consists of this intrinsic kinetic energy due to the occupation of consecutive energy states, plus this collective motion of the center of mass, plus external potential, plus the mean field form of the interaction. So this is just this interaction strength G times n plus times n minus. So this the energy is higher if just the overlap of two clouds is higher. This is kind of expected. So then what we do, we just do the Euler-Lagrange equations out of this closed system, get the hydrodynamic equations, which are usual, the same as the, let's say, classical hydrodynamic, apart from the fact that we also have so-called quantum pressure. This is a difference between the quantum hydrodynamics and classical one. So it can be equivalently, almost equivalently, there are some technicalities about the, let's say, about some technicalities, but almost equivalently, we can rewrite these hydrodynamic equations into the form of the almost Schrödinger equation. So again, we have the form of the Schrödinger equation. So we have a time derivative, some effective Hamiltonian, let's say, acting on the linearly on the, well, non-linearly on this pseudo wave function. So we have usual parts, just a Laplacian, the interaction. So this is this nonlinear part, interaction between the species, external potential, quantum pressure, which makes it different from the classical system, and this intrinsic kinetic energy of fermions. And then to get dynamics, we just solve it by some methods. And to get a ground state of the system, we used imaginary time evolution, which this is like a trick. So usually what we do is just to propagate the system by this unitary transformation, this unitary evolution operator. But if we take the imaginary time, it becomes like a exponentially decaying operator. And if we apply it to the state, the ground state decays the lowest. And after some evolution, we just get almost only the ground state. So this is like the trick to get the ground state. So, okay, so what we do, first we check what happens with these two component Fermi gas in a trap looking for the ground state. We see two transitions. So first of all, if the interaction, if the repulsion is not very strong, then the density profile of both gases is the same. Then there is some critical interaction in which it starts to separate in the center of the trap, not breaking the spherical symmetry. Then it creates, like with the strong interaction, a bit kind of a donut in which one of the species sits inside and the other sits outside. And then after some other critical value, it separates into two halves, breaking the spherical symmetry, getting like two. So this is like this phase-separated ferromagnetic state. So that was like our analysis of the ground state. We did a phase diagram as a function of number of atoms and the interaction. But what is important is that we went on to studying the dynamics present in the experimental setup. So as I told you, initially separated clouds, barrier in between, release of the barrier, and then like two clouds attacking each other. So what happened for this small interaction? Two clouds, like for no interaction, two clouds just like oscillate with the frequency of the trap, and then with the growing interaction, this frequency gets lower. And then after some critical interaction, those two gases stay separated, signaling the stability of the ferromagnetic state. And what happens when we compare our results with the experiment? So this is what I just told you. So this is this frequency of the motion of these gases. It goes down with the interaction, and then it goes higher because one of the species feels like it would be hitting a wall. So it oscillates with the twice of the frequency of the trap. So we didn't have a good agreement with the experiment, so we needed to refine our interaction. So because like this just simple type G n plus time A minus was too simplified, it didn't account for the quantum corrections to it. So like we use a couple of different schemes, like perturbative expansion, like a lowest order constraint variational approach, and quantum Monte Carlo to get like better, let's say, functionals of energy. And then our agreement with the experiment was perfect. So these triangles are experiments and different symbols are our simulations. So the agreement was almost perfect. Okay, but the big question about our approach, whether like how does it, like why does it even work? Because we assume that our system is hydrodynamic. So for sure, non-interacting Fermi gas is not hydrodynamic, and if there is overlap between two gases, we would then say probably that it is hydrodynamic because it provides some kind of thermalization process in which allows to describe this system as really like this flow on some kind of fluid with insides being like in a stationary state. So what we did is that we checked our approach with the time-dependent Hartree-Fock approach. So this is like this many orbital approach, like we describe every fermion like with a single function. And so we checked a lot of collective modes and so on. And what we found out that our approach works in some cases. So if the non-interacting hydrodynamic frequency coincides with the true non-interacting one, then it works. If it does not coincide, then it does not work. So that's our conclusion, meaning that we can use our framework, but we need to know in which cases. Okay, I just showed you only repulsion between the. I just showed you only repulsion between the two species, and didn't say anything about this dimer formation, which was crucial in the experiment. So the problem with this dimer formation is that in 3 dimensions, it's naturally present in theory because we have we model this interaction by the contact potential, which gives us for free the bound state of 2 fermions. And on the other hand, if we consider the same contact interaction in 1 dimension, like the repulsive interaction does not support the bound state. So we have a problem in here because like we cannot really model very well systems like in a many-body way for 3 dimensions. So what we did, we tried 1 dimension with a different potential. We called it a 3 delta potential, which looks like this. It means that we have a single repulsive delta type term, like when the 2 atoms coincide, plus 2 peripheral attractive deltas that allow this like 2-body system to have a bound state. So we checked what happens in a system, in 1-dimensional system with a strong central repulsion with additional bound state. And what we found out, so we did it the like full many-body dynamics with some more sophisticated methods. And what we find out that really when we consider the same geometry in the course of the evolution, there is a fraction of molecules appearing between 2 clouds. So really like this is like a situation in which and the, let's say, domain wall between 2 fermioning species, we have really molecules that separate the fermions. So this is like almost the same as it happened in the experiment, because they also saw some dimers in between the two domains. But of course, it's like a 1D analog, which is not the same mechanism, but like it can be used as a analog of this full problem in 3D. So, okay, that is the last slide. So the other thing that we did is to use our approach to study a different system, a mixture of bosons and fermions. So this kind of thing was realized in a group of Professor Rudi Grimm in Innsbruck. So what they did, they had a BEC, Bose-Einstein condensate, immersed into much larger, so this is the BEC, immersed into much larger fermionic cloud. So they could freely tune the interaction between this BEC and fermions. So what they did, they excited the system in such a way that they they were sweeping from the strong interaction to weak interaction between the two clouds, effectively exciting a breathing mode, like a breathing mode. So this BEC was we're doing like a pumping inside the Fermi cloud, and they checked the frequency. So in the theory that was accompanying the experiment, they could not explain some behavior. Well, they checked this, the rate of these oscillations as a function of interaction. Okay, the experimenter starts, so you can see that it's like it grows and it falls down. So they could not explain it with a theory. What we did, we used the same approach that we did before, but in a finite temperature. So what we found out that this non-monotonicity is due to the fact that this Bose-Einstein condensate inside changes temperature during the time evolution. It rethermalizes, it gets colder. So effectively, that's the reason why this frequency changes. And they didn't know it in the experiment, they didn't know the theory. So it just shows how versatile our approach is. And again, we got a perfect agreement with the experiment. So I'm running out of time, but that was the last slide. Thank you.
Thank you very much. We have a couple minutes for questions then. Please, Bożena.
Let me give you we are missing the person giving the microphone.
This molecule formation mechanism looks very attractive when you have this medium confined by those two phases. But in 2 or 3 dimensions, this will be much more difficult, or you think it may still work?
You mean like theoretically or experimentally? Experimentally is probably easier. But theoretically, to do full, as we call it, many body calculation is very hard, especially in the dynamical problem. So I can imagine that the best people did was really complicated stuff that allowed for couple of fermions. and not much insight of really what happens in the system.
And in reality, it should work.
Well, in reality, like people see this dimer formation in 3D.
Okay.
But it's like we propose to do an analog in 1D system.
There is one more question from Wojtek there.
Thanks, Piotr, for a very nice talk, and hopefully hold my fingers for you to be alumnus very soon. But you use a phrase on one of the slides you were showing that your prediction agrees perfectly with the experiment, or even other way around. The experiment agrees perfectly with your prediction. So of course there was an alarm bell in my head, and as a cosmologist, I'm even much more flabbergasted if you get even 10%, 20% agreement. This is what we call perfect. So I understand this is not you who made the experiments, but could you explain why there's no error bar? So what kind of a measure of some kind of variance?
There were error bars, but like they created chaos on the plot, so I just get rid of them.
So what do you mean by perfect?
I mean like up to a couple of %, but on the other hand, when you would talk with the people from real complicated, sophisticated quantum many-body stuff, they would say if it's not below 1/10 of 1%, it's absolutely bad. So depends on the type of the experiment. Okay. So in our case, I said perfectly because it was almost it was within the bars of the experiment.
Okay, so it was up to your satisfaction. Thanks very much.
Yeah, exactly.
Any more questions, please?
Actually, I have a remark and a question. The remark is with respect to the one of the first slides of your talk. Namely, you said that the Leuven theorem excludes ferromagnetism. Isn't that the Leuven theorem was initially devised for excluding diamagnetism?
I would say, I don't know. Really, I don't remember.
Well, I think it was meant for diamagnetism, yeah.
Probably, but in Niels Bohr physics, that was for sure ferromagnetism, I can imagine. But again, I'm not sure. Because
and then came Landau quantum theory of diamagnetism. But anyway, my question is about this coefficient CL.
Okay.
Do you have any microscopic interpretation of this coefficient or relation with microscopic parameters of this coefficient?
Yes. So that was work done by Krzysiek Jachymski when they compared the scattering properties in a really quasi 1D system of basically two bosons interacting via van der Waals forces. So the comparison is there, but with the exactly this system. So van der Waals forces, Feshbach resonance, and they just we can almost unambiguously compare the CL, L, C naught with the scattering properties like the scattering length, finite range, and so on.
Okay, thank you.
I think that was the last question in this question sessions, but of course I encourage you to continue discussion with our student on the break and help him prepare for the final exam. And now we turn to the next presentation. This will be given by Swayamtrupta Panda. He is also our soon-to-be alumnus. His defense is already planned, and it will be next week. So actually, I would like to invite all of you to take part in this public defense. It will be broadcasted on the Zoom. The link is on our website. And Swayam spent here in Warsaw 5 years, yes. And he worked with a great success under supervision of Professor Bożena Czerny. And he will tell us today about black hole mass scaling relation based on coronal gas and its connection with accretion disk.
Thank you so much. I hope you can hear me well. This works, okay. Thank you so much, Professor Januk, for giving a fantastic introduction. So my name is Swayamtrupta Panda, and I'm going to switch a little bit towards talking to you about astronomy and astrophysics right now. And I'm glad that I'm the first speaker in terms of giving you an introduction. So this will be also going in through some very basic parts of the astronomy relating with the black holes, and what I basically do right now with a couple of collaborators from Brazil and Spain at the moment, where we try to figure out a novel black hole mass scaling relation using coronal gases and trying to establish a connection with the accretion disk in the black holes that was already discussed a little bit in the previous session. So as Agnieszka mentioned, I'm actually doing I finished my PhD studies at the Nicholas Copernicus Astronomical Center, and soon next week, actually next Wednesday, I'll be defending at the Copernicus at the Center for Theoretical Physics. All right. So the outline of my talk would be going to be a brief introduction about active galaxies and what are their constituents. So basically giving a flavor of what we're going to work on and talk about. And then I will move on to tell you about how different methods of black hole mass estimations are done and what are the relevant scaling relationships that go into play here. And then we'll switch gears and focus on coronal line emissions in active galaxies and establish the new scaling relationship that we have observed using these coronal lines. And in the end, I would conclude with a new prospect connecting coronal lines with the main sequence of quasars, which is the main aspect of my PhD studies, which is relating the diversity of type 1a AGNs, active galaxies, in the context of really allowing a sequence which is similar to the HR diagram for stars. Okay. So, as I mentioned, so the basic question is about what is an active galaxy. So basically, what an active galaxy is, it's an embodiment which is sitting right in the center of many of the galaxies, and at times when it is really active, can outshine the luminosity that is coming from the entire galaxy itself. Oh, sorry. Okay, sorry. Is it better now? Okay, thank you. All right, so let me rephrase again. So we have this quasar, which is the high luminosity active galactic nuclei, which is sitting right in the center of this galaxy, which is having beautiful spiral arms over here. And at times when it's active, the luminosity can outshine the host galaxy itself. So if you zoom in very close to this nucleus part, this is a structure. It's a cartoon diagram, but it has also been verified by many observations throughout the decades, where we see a central supermassive black hole sitting right at the center, and then there is a physical manifestation of the accretion disk that is actually engulfing the matter around it and forming this accretion disk. And then we have these Keplerian-bound gas clouds, which are then, I'm going to tell you about how we distinguish between these different kinds of gas clouds based on how close and far they are from the central supermassive black hole. Then it's all circumscribed by this dusty torus. At times it can be quite colluding, and the dusty torus doesn't necessarily need to be a smooth distribution, as has been shown in this artistic impression. And at times when the activity of the AGN really starts to be really vibrant, the gravitational energy that is being drawn by the accretion disk can shoot out in form of the mechanical energies and show us these relativistic jets that can even go beyond the scales of the sizes of the galaxies themselves. All right, so to understand basically the phenomena and the physics behind what are the energy dissipation and mechanisms that is at play using the active galaxies, we actually have something called the broadband energy distribution in the active galactic nuclei. So AGN is the short form for the active galactic nuclei. Over here, I'm showing, and let's try to first focus what is actually the AGN intrinsic continuum. So this diagram is actually the spectral luminosity on the y-axis, and on the x-axis we have the frequency in the logarithmic scale. So what we see in the AGN intrinsic continuum, which is really coming from the very subparsec regions of the AGN, we have the accretion disk component, which is basically a realization of the thermal photons. And then we are accompanied by inverse Compton scattering of these photons, which then manifests in this form of soft X-ray excess and coronal power law. Thereby, after this intrinsic emission, what actually happens because of the presence of this dusty torus is that this intrinsic emission gets reprocessed and re-emitted at longer wavelengths, typically in the peaking up in the infrared. So that is the component that comprises of the dusty torus. And of course, even if we go further away, we have the emission that is coming from the star formation and typically of the galaxy itself. But let's now concentrate to the aspect of what is called the AGN intrinsic continuum. So that was one thing from the energetics point of view, but actually if you would like to realize what is actually happening inside the AGN and the nearby vicinity of the AGN, it's quite interesting to do high-resolution spectroscopy. So why spectroscopy is really important is that a typical AGN active galactic nuclei spectrum contains three primary components.
One, which is the underlying AGN ionizing continuum that we can clearly notice and appreciate, which is really embedded in the spectrum itself. The next is the absorption lines. We can clearly see them using these dips that are prominent all throughout the spectrum. And the more importantly are the emission lines, which can be broadly categorized again into broad and narrow. So these are the typical emission lines that we see in a generic AGN spectrum. And the broadness, or the degree of broadness, lets us know about the velocities with which they are rotating around the black hole, and thereby allowing us to position these emitting regions from how far they are from the black hole. So basically, the combined information of the underlying AGN continuum, the absorption lines, the emission lines, really help us characterize the dynamics, the energetics, and eventually the composition, because of the variety of emission lines that we see here of their immediate surroundings. And not to forget about the time aspect of these AGNs, because they do vary, as has been shown in the previous talk where our colleague was showing this interaction of the white dwarf with the black hole itself. But in this case, we can clearly notice that in a matter of just 12 years, the AGN continuum, which was really at a high state, dropped down to be in this black curve, which is the recent spectroscopic measurement using the Sloan Digital Sky Survey over here. And we can clearly see there are two things happening. Not only the actual AGN continuum is drastically reduced, but also the response of the emission lines due to this AGN continuum is actually getting also reduced. So there are these two aspects that really help us convolve the picture of the AGNs and this inner workings of the AGNs. All right, moving on to the next part of the talk, which is going to be about black hole mass measurements and how do we estimate this very fundamental aspect of black holes. The number one aspect of doing that is using dynamical methods, which is basically we are utilizing the Keplerian motions of these entities, for example, these broadline region clouds, the gas clouds that I showed in the diagram before, around the black hole. So I'm going to focus on the one that is highlighted over here, which is using the broadline region clouds, using their line width information from this high-quality spectroscopy and broadline radius that is being estimated using reverberation mapping techniques. So there's a neat little review by Professor Cherny and Marek Nikolaev back in 2008, where they put together all the available methods from which the black hole mass measurements can be done. So since I mentioned reverberation mapping, let me just give you a brief overview of what is a reverberation mapping. Typically, just to emphasize that it's also celebrating about its 40 years in the making. So reverberation mapping is actually, on its own, the light echo method. So the idea behind is that we have the central accretion, the accretion disk surrounding the supermassive black hole, which is the principal energy source emitting the continuum. And the continuum basically then arrives at the observer directly, but part of the continuum could actually get intercepted by the broadline region, which is circumscribing the supermassive black hole. So the idea behind the reverberation mapping is actually calculating the light travel time between the direct light that is received by the observer and one that is scattered by the broadline regions. By doing a cross-correlation between the continuum light, which is the direct light, and the light that is being reprocessed by the broadline region, one could estimate the sizes of these medium and how far they are from the central ionizing continuum. A recent work by our group actually has compiled the latest database of 120 reverberation mapped AGNs on this diagram. Actually, on the y-axis, we have the R parameter, which is the size of this medium, which is represented by RBLR here, measured in the units of light days. And on the x-axis, we have the logarithmic of the monochromatic luminosity at 5100 angstrom. So this is sort of a proxy of the measuring the total luminosity that is being produced by the accretion disk itself. So this is one of the reasons, actually, as a pitching of our own group here at CFT, led by Professor Cherny and our postdocs and PhD students. I'm over here. And this is the classical work that we are doing, and this is one of the research where we are leading. And the idea is utilizing high luminosity, high redshift AGNs, and characterizing this radius luminosity relationship that I showed you in the previous diagram, and utilizing this aspect of scaling to constrain and use AGNs for cosmology. So this is at this point, we are at the stage where we can measure efficiently and corroborate whether, based on other methods, existing methods, such as using supernovae, Cepheids, more nearby sources, can we also utilize AGNs and quasars, which are typically higher redshifts, in the context of understanding the evolution of the universe and the Hubble diagram. All right, switching back to the black hole mass measurements, the other two important aspects, apart from the dynamical methods, is using spectral fitting methods, where we basically are heavily dependent on understanding the theoretical frameworks which can allow us to fit the spectrum, as I showed you in the first slide of the spectral energy distribution. So in this regards, we need to understand what is the black hole mass, but also understand the parameters, which are mostly the accretion rate, the spin of the black hole, and the viewing angle, because in this case, we are talking about sources which are really extended and not as compact as stars in that scenario. What I'm going to focus on for the few slides next is the scaling methods, where actually what is happening is the black hole mass measurements are estimated previously using the spectral fitting methods and dynamical methods, and they are being realized with respect to some measured observable properties of the spectra. One such long-withstanding relation is the M-sigma relation, which is basically relating the black hole mass of the supermassive black hole at the center of the AGNs for typical spiral galaxies, and relating them with the stellar velocity dispersion of that galaxy's bulge. And there have been works going on for 3 decades already, and we have a good enough handle, and this seems to be one of the highlights of utilizing the aspect of computing masses for supermassive black holes for newer and newer sources. So let's now switch to the aspect of the work that we have been doing here. It's utilizing coronal lines. So the namesake of coronal lines has actually nothing to do with, well, it's actually have to do everything to do with the solar corona, because these lines were first and foremost seen in the solar chromosphere, and eventually these coronal lines, or the high energy forbidden ionization emission lines, they are characterized by forbidden line structures transition, which are produced by collisions of highly ionized species. So the typical ionization potentials of them can go beyond 100 electron volts. I'm going to show you 4 examples of such ionization coronal lines. And because of this very high ionization potential, they're considered to be reliable signatures of the central accreting black hole and presence of AGNs in the galaxies. But they are not ubiquitous. They are ubiquitous. They are not just confined to AGNs. They've been found for supernovae remnants. They're found in planetary nebulae, and also for evolved stars such as the Wolf-Rayet stars. But their coronal line luminosities in these are really, really low. They can be up to a factor of 1 billion times smaller than the AGNs, which really helps us characterize by knowing the luminosities that we get from these high-resolution spectra of AGNs. So basically, trying to study these forbidden high ionization lines is of great importance, as I already mentioned. So just one telltale signatures, and really at the forefront, where we are utilizing integral field units to map the regions of emission around the central supermassive black hole. So I'm not sure if you can visualize that, but there is a small cross right at the center. This is the marking and the position of the supermassive black hole in these 2 cases. And these are the velocity maps for different emission lines, for the H2 emission, for the bracket gamma, and here on the right is of silicon-6. So on the top is an example of a high Eddington ratio source. By Eddington ratio, I mean the bolometric luminosity normalized to the Eddington limit. And on the lower panel, we have a case of a low Eddington ratio source. And clearly, we can see that the one of this coronal line emission is not really following the ordered motion that is being represented by the H2 and typically by the bracket gamma. So this is an indication of something non-circular, and is an indication of an outflow in these kind of sources which are accreting at higher than Eddington. So coming to our work that we have tried to encompass is, we created a database of black hole masses that are already being determined by reverberation mapping, and utilizing these high signal to noise ratio spectra, we get epochs of optical and near-infrared spectra with accurate coronal line measurements. So the 4 coronal lines that we have utilized is the RN7, that is in the optical, so shown over here, silicon 8, silicon 10, and silicon 6, which are in the near-infrared. And the question, why did we utilize them? They are among the strongest coronal lines seen in the AGNs in the range of electron volts of 100 to 351. And our final working sample is of 31 AGNs, and what we focus primarily on and found a robust correlation is that with the silicon-6 normalized to the corresponding nearest H+ emission. So this is the result from our work, that the scaling relation that we have achieved using black hole masses with respect to this coronal emission of silicon-6 normalized to bracket gamma is actually comparable, has a comparable dispersion of 0.47 to the 3-decade holding relation of M sigma relation that currently has a scatter of 0.44 dex. Right now, we are at a very nascent stage. This is the first of its study, utilizing only 31 of its AGN. But as I showed, in the future, we are actually increasing the reverberation mapping estimates to up to 120 AGNs. And the plan is to take a look and go back and look at high-resolution spectroscopy for these other AGNs to populate this, this scaling relation diagram. And here I'm just showing a few snapshots of the beautiful spectra that we have obtained using space-based telescopes such as the Hubble Space Telescope and many of these ground-based instruments such as the Sloan Digital Sky Survey and telescopes in Argentina and Chile. So this is the part with the optical spectra. This has been zoomed for each of these cases. And I'm trying to highlight the case with this blue-word asymmetry. We can clearly see these spectral line profiles are not symmetric. And these blue-word asymmetry is indication of outflows. And these are the sources which are the candidates for stronger than Eddington accretion. And we do see a telltale signature in the near-infrared part of the spectrum for the typical sources as well, where we can notice that the sources which are actually Eddington a little bit above or at Eddington do have this asymmetry even in the near-infrared part of the spectrum. So now coming on to the idea of we understand that we see this observed empirical relationship between the masses of the black hole and the coronal lines. But what is actually driving this is something of the question that we wanted to answer here. So utilizing a standard approach of Shakura-Sunyaev standard disk and a multicolor blackbody temperature and adding it up with the power law continuum for the coronal emission, we are able to feed this spectral energy distribution, which is also characterized, the peak of its temperature is characterized by the black hole mass, the accretion rate, the efficiency of the accretion, and the size, which is in the units of Schwarzschild radius from where this emission is coming from. And this is the typical framework of the flux distribution of this SED, which is eventually put inside photoionization modeling, which is actually solving the non-LTE gas, taking into account radiative transfer with ionization balance and local thermodynamic equilibrium. So what we are trying to find out is that we have a very nice agreement of the envelopes of the different photoionization model on top of the observed data points, which has been overlaid on this plot here. By doing so, we are not only focusing on what is the emitting sizes of this region, but we are able to figure out what are the typical number densities of these regions, which is of the order of 10 to the power 4 to 10 to the power 5 particles per centimeter cube. And they are placed at the distance which is neatly at the resolution limits of the instruments that we are using at 3 parsecs. So we also end up just testing with the warm coronal component, which I mentioned typically before, that it could actually suggest that when the sources are accreting at higher than Eddington limit, the stronger contribution of the warm coronal component can be appreciated. And this is indeed the case that we do see a stronger emission in the coronal lines when we include this additional component of warm corona. And the way the warm corona looks like is mentioned over here. We have the accretion disk component, which is the same as before. But in addition to the hard X-ray power law, we have a third component, which is due to the thermal emission being backscattered and producing this coronal emission that is coming from the very vicinity of the accretion disk. Well, towards the end, I would like to focus on a new avenue that we have started very recently. And this is utilizing these coronal lines to investigate the main sequence of quasars. So what is the main sequence of quasar? This has been the topic of my PhD dissertation. And the basic idea behind the main sequence of quasar is that it is an analogous scheme to the Hertzsprung-Russell diagram that has been used to classify stars based on color diagram, based on luminosity temperature prescriptions, and being able to announce and tell us what is the stellar evolution that one star would be able to do if we have the knowledge of the main sequence diagram. So the idea behind this actually approached back in the 1990s, where people utilized single vector decomposition and principal component analysis in order to appreciate and put together the observable quantities from AGN spectra, which are now more complicated, more extended sources, and realize the optical plane of this main sequence diagram. So this is a plot that is coming from my paper from back in 2019, which was published in Astrophysical Journal. And over here on the y-axis, we have the line width information that is telling us about the velocity profile of this H beta emission in units of kilometers per second. And on the x-axis is a typical very interesting quantity called RFE2, which is the relative strength of FE2 emission in the optical normalized to the corresponding H beta emission. So now when we try to connect, this picture is actually what we have tried to understand recently, that it's a continuous sequence that connects the low black hole masses, which are typically accreting at higher Eddington ratios, and to their higher mass counterparts, which are now more quiescent compared to these low mass counterparts. And this is typically what we have found and emphasized and concluded from our studies, that this ratio is typically driven by the Eddington ratio, accompanied by the cloud properties from where these emission lines are being produced. But what is interesting is that what we found from our sample now on the left-hand side is now this plot is plotted against the Eddington ratio, but as a function of this ratio, silicon 6 over bracket gamma, for the sample of sources that we have currently, the best measurements available for silicon 6 over bracket gamma. And we clearly see a telltale signature of this emission line intensity increasing with the increase in the Eddington ratio. And if you would like to notice, these typical sources which are lying at the over right end of this correlation are the ones being populated in the extreme population A of these quasars and have been noticed to have higher RFE information. So what we are trying to do is not really relate two unrelated estimates and tracers, but this one is the one relating to the broadline region part of the clouds, which are much closer, subparsec level clouds, which are closer to the supermassive black hole. And these are the emissions which are coming from further out from few parsec scales from the narrow line region clouds, and they typically being driven by the same amount of quantity, mainly the accretion rate, the Eddington ratio, is a telltale signature that these two emission regions are being connected by the photoionization that is being caused by the radiation from the central accretion disk itself. So to summarize, the coronal lines really are a clear, robust indicators of strong activity in the central nucleus of the AGNs, and is rich in ionizing photons. And these photons can eventually photoionize mediums that are extended up to tens of parsecs, and where the mean densities can go as below as few particles per centimeter cube. We have found a robust scaling relation between the black hole mass and the strength of one of these very high ionization coronal lines, the silicon 6. And at the moment, the relationship is as good as the M sigma relation, but it will get better in the coming years. The strength of the coronal lines is directly connected to the accretion rate of the AGNs that I've shown here on the right. And utilizing this information, we need to do further studies, which is ongoing at the moment, to test this diversity that I showed you with the main sequence diagram of AGNs, but linking now with coronal lines, especially in the era of the upcoming large-scale surveys, spectroscopic surveys, such as the James Webb Space Telescope, the Mauna Kea Spectroscopic Explorer, which are going to revolutionize the upcoming decade for astronomy. So that will be it. Thank you.
Thank you very much. Thank you for a very interesting presentation and for keeping up with time perfectly. So we have time for questions now. Wojtek, please.
I understand that, correct me if I'm wrong, but this is so fundamental, so maybe if I got it wrong, it would be silly me, that in all these calculations, you basically ignore any kind of a self-gravity of the accretion disk, right?
Self-gravity is, it's not taken into account because we are talking about the emission that is actually coming from the surface of the accretion disk. So typically that could really modify the emission that is coming from the very central regions.
So very central regions.
Yes,
okay.
But to add to that, the emission region that we are looking at typically gets ionized of the order of hundreds of EVs.
So this is corona, basically.
This is the part which is closely related to the warm corona, not to the hard corona, which is typically very closer. So these effects actually nullify because they are really involving photons of higher energies which are transparent to these mediums which we are talking about and trying to find the diagnostics for. So yes, indeed, should be the effect, but in terms of the emission regions that we are considering, these are these photons which are really transparent. They contribute really nothing in terms of the emission for these regions.
Right, thanks very much for clarifying that for me.
Actually, I also wanted to ask, how fast are these outflows? What is the velocity of these outflows diagnosed by coronal lines?
So typically they could be of the order of hundreds to few hundred thousands of kilometers per second, but typically that has to do with involving mediums which are not just photoionized, but also relevant in terms of shock mechanisms. So in terms of where there are CSS sources which are really starting to grow in their relativistic jets component, we do see that these outflows are much more pronounced compared to sources which are typically just run down by normal photoionizations of accretion disks.
Okay, so are they unbound, leaving the host galaxy, this material, or is going to turn around and feedback with the accretion flow again?
So there was a recent paper last year which actually ended up resolving the kiloparsec scales of these regions, and they are still in the moment where they are still outflowing. They are still connected, but the results of photoionization have suggested that there is a mix of shock and photoionization, more dominated by the shocks itself, which really tells that this is being pushed away from the central nucleus and getting to be unbounded in the coming future. So that would be very interesting to see.
Małgosia, sorry, I cannot see from the mask.
Thank you. It was really interesting talk. I have two very, probably silly questions. First of all, what is the redshift range of your sample of those 31 galaxies? Because I can imagine that through the line measurements, you have some limitation for the redshift. Yes.
That's true. And so these redshifts are very much nearby sources because we are able to resolve these regions up to 30 parsecs of scales. So definitely, we are talking about very local group of galaxies. The typical redshifts goes up to 0.2. But not very far, because we really want to resolve these kinematics of these regions and be sure that the line we're talking about is standing out in the spectra itself. So this is why we also employ this high signal-to-noise ratio spectra for these sources.
Okay, yeah, and the second very, very short one. So of course those 31 galaxies were the type 1 AGNs, yes? And do you have any idea if it's possible to create a similar scaling relation for the black hole mass for type 2 AGNs?
Perfect question. I think I should have mentioned that in the conclusion itself, but the point being that these are the regions which are typically still going to be seen for type 2 AGNs. And by making this robust relation that it's applicable right now for type 1 AGNs, the idea exactly is to then transfer it to type 2 AGNs, because we will be able to see the maps for these coronal lines, and then we get an idea about what is the black hole masses expected out of them if our correlation still holds for the majority of sources for type 1 AGNs. So that's a great question, and we are looking forward to that.
Yeah, thanks. Thank you very much.
Thank you.
Thank you, Swayam. I see one more question by Bożena, and then we finish the session of questions.
My question is not to Swayam, my question is to the audience. He's talking about densities like 10 to 5 particles per cubic centimeter. What's the current density of the vacuum in laboratory? 10 to 9, 10 to 12? In the same units? Because those densities he's dealing with are surely much, much lower than vacuum. But what is the vacuum? Anybody can answer this question. What is the density of the vacuum, right, produced in the laboratory?
I don't know about other subjects, other disciplines, but in ultra-cold atomic experiments, we are not using this highest vacuums possible. Still, the vacuum is of the order like 10 to minus 10 of bar. 10
to minus 10?
Yes, and then we have to compare units.
In particles per centimeter cube.
10 orders of
magnitude higher.
What he does.
Okay, very interesting comparison. So let us now move on to the third speaker of this session. We are happy to see here today with us Tomasz Maciążek. He graduated from Center for Theoretical Physics in 2018, completing his PhD thesis under supervision of Adam Sawicki, our director now. And he worked for these past couple years abroad in Britain. In Bristol, yes, as a postdoc, and I hope he will tell us more about his postdoc career and science project that he completed there.
Okay. Thank you very much for the introduction. As Professor Janik said, I graduated in October 2018, and I did my PhD under the supervision of Adam Sawicki. But I've actually spent a great deal of my scientific life at the CFT, beginning already 10 years ago, when I enrolled to the internship program by Adam, to a project by Adam, Michał Oszmaniec and Marek Kuś. And after the internship I stayed, I wrote my master thesis here and then my PhD thesis. So I think I can safely say that I've at the CFT I have learned how to be a scientist, how to do research, which makes me very grateful for this opportunity to speak here today at this anniversary conference. The talk is about a result in density functional theory. I'll try to make it very non-technical, and if you're interested in more technicalities, or if it's if you'd like to, if something is not clear, feel free to ask me. Also, feel free to look at this archive preprint with the same, which has the same title as my talk. So, density functional theory is primarily interested in the ground state problem, and there are two settings I'll be talking about simultaneously today. One setting is pair interacting spinless bosons in some external potentials, and the other setting is the one involving pair interacting electrons, which are of course spinful and they have spin 1/2. And I'll be restricting to the singlet sector, so total spin 0. However, in fact, I'm thinking about finite dimensional and discrete settings. So I've got a lattice of points, a lattice of sites, and they are connected by some hopping amplitudes. It's completely general, so it's finite, some little d. So, in general, we can approach the ground state problem by just doing this huge minimization over all n-particle quantum states. This is a generic method, works for any Hamiltonian, but the price we are paying is that the dimension of the minimization domain grows exponentially with the number of particles. So functional theories, they build those similar minimization problems, but for specific families of Hamiltonians, and this allows us to reduce the dimensionality of this minimization domain. So what I'll be focusing on today is this division. So a Hamiltonian will be written in, as single particle terms, little h, and some fixed interaction. So you can imagine that we are fixing our favorite field of physics, like Coulomb interaction or Hubbard interaction, and using this information we are building our functional theory. So once we've got this division, we arrive at something which is called reduced density matrix functional theory, where the dimension grows quadratically with the number of sides of those with little d, but it's independent of the number of particles. Why is it the case? It's thanks to something which is called the Levy-Lieb constraint search, which has been formalized in the late 70s and in the early 80s by Levy and Lieb. And it comes from this this calculation which I will show you now. So I'm writing down the ground state energy with subscript W to emphasize the fixed interaction, and I'm thinking of this ground state energy as a function of the single particle term of my Hamiltonian. So as before, I've got this minimization over all n-particle wave functions. So now we are noting that the little h sandwich with psi can be in fact written as trace of little h with the one-body reduced density matrix rho. So this suggests us to split the minimization into two steps. First, we minimize over all one-particle density matrices, and then we further minimize over all n-particle states that maps to a fixed one-particle density matrix. So this is formally the same minimization. Now we want the right-hand side. We want to write as a functional of rho. So by definition, we are defining a functional. so that we can formally write the entire thing as minimization just over the one particle density matrices. But of course, the complexity sits in this functional. So if you want to do it in practice, we have to perform this minimization analytically, not only numerically, because we want to have a functional. We want to plug this into a computer program and then minimize over all one body density matrices. But this is what the reduced density matrix functional is. It's finding it is the main goal, which is probably maybe not unachievable, but very, at least like super difficult. What's good about it is that it's universal, so it doesn't. It works for any one particle term. So once we've got our interaction, it works for any hopping. So any, yes, and we can connect sites by any hopping terms, and it's still the same functional, and any on-site potentials. Surprisingly, it's actually known for the Hubbard dimer. There is an analytic formula which can be found in either of these papers. We can simultaneously consider the Bose-Hubbard interaction or the Fermi-Hubbard interaction. On the dimers, we've got two sites, site 1 and site 2. This means that our one-body reduced density matrix is a 2x2 matrix. Hermitian, and it's complex, but when we say that the wave functions are real, we've got just two variables, and this allows us to plot this surface here. So on one axis we've got the off-diagonal entry of the density matrix, and on the other axis we've got the one of the diagonal entries, and that's the plot of the functional. And what I'm interested in is something which I hope that you can roughly see what's going on here. At the boundary, there's a cusp of this functional. So if we make a radial cut through the domain, the domain are all one-body density matrices that come from some pure state. It's the same picture for two bosons and for two singlet electrons. So mathematically, these are the same problems. And the domain is a sphere. If we assume that the rho is real, then it's just a circle here. So if you make a radial cut and parameterize the radius with d would be the distance from the boundary of this domain, then the plot that we get looks like this. And if we plug in the formula, we will see that the gradient of the functional diverges repulsively at the boundary, like 1 over square root of the distance from the boundary. So you can imagine if we do the numerical minimization, that will be kept away by this gradient from the boundary. And in the literature, it has been called this numerical phenomenon has been called exchange force when we are talking about fermions, or the Bose-Einstein condensation force when we talk about bosons. And why is it the case? It's because the boundary is composed of states which are completely condensed when these are bosons, or of matrices corresponding to states which are completely condensed. So when we've got two particles, the spectrum of rho would be 2, 0. Or when we've got two electrons, it's the same spectrum. One singlet electron, one electron occupying one orbital and the spin up, and the other electron occupying the same orbital spin down. So that's the boundary. So it means that when we are approaching this non-interacting state, then we are kept away from this state by this gradient. So the main result I want to tell you about today is the generalization of this phenomenon to any interaction and to any dimension, to any pair interaction and to any dimension of the one particle Hilbert space. But to yes. Could you say again? It's in the leading order. It's in the leading order. So it could be some other function, but if we expand it in the powers of d, then we get the leading order is 1 over. The leading order would be the square root of d minus the square root of d plus some constant. So to even state the result in the bigger generality, we have to imagine many sites and think of either fully condensed states for bosons or non-interacting states for fermions. These are in the singlet, so we are putting a pair of fermions on each orbital, spin up and spin down, or all bosons in one in one mode. And now, by changing the single particle basis, we are moving on this set of the set gamma BC or gamma HF, depending whether these are fermions or bosons. Now, to define the variable d properly, we have to take any row and diagonalize it. And once it's in the diagonal form, we are connecting it with this dot, with this blue dot, with the row BEC or row HF. And it's all actually a Euclidean space. So this is just a straight line in a Euclidean space. Then the occupation numbers are always assumed to be decreasing. And then this is well-defined distance. And the reason why this diverging gradient exists when we take d tending to 0 is this inequality. So at the exact functional at point u row u dagger, u is a single particle basis change, is bounded by this long expression, but here we've got d. Beta d depends only on the direction of this line segment. F of u gamma bc u row u f of u row bc u dagger is the exact functional at this point. Now plus some function c1 which depends only of u. This expression is responsible for this repulsive gradient. And now plus some c2 which depends on of u only again, times d over beta d. So we can plot it. We can plot d over beta d on one axis and then the functional and the bound on the other axis, and this is what we will get. So the bound coincides with the exact functional for d equals 0, and this means that the gradient of the bound is the upper bound for the gradient of the exact functional, and this implies the result. And so the point is that this inequality holds for any pair interaction, and it's true in any dimension. Why is it true? It's because I was able to construct a wave function ansatz. So the fact that the functional is upper bounded is very trivial, because the functional by definition was a minimum over all wave functions mapping to a fixed row. So now once I've got an ansatz, I take any wave function. This is an upper bound for the exact functional. So the difficulty was to really find analytically an appropriate ansatz function. It's difficult because we have to invert this map, a map which assigns one particle reduced density matrix to a n particle state for any row. In a finite strip around those gamma BEC or HF states. We also have to control the geometry of the problem, and we also have to have the desired dependence on the d variable. So I will briefly show you how this state looks like. It's not maybe so important for the talk, but I don't want to keep you. Yes, it would be a bit disappointing if I didn't tell you. So this ansatz state is determined by the eigendecomposition of the one-body reduced density matrix. This will be the construction for the singlet sector for electrons. So we are taking the eigendecomposition. Again, the occupation numbers now new are decreasingly ordered, and to this row we assign the Slater determinant, or Hartree-Fock state, which means that we are taking an orbital phi1, so the highest occupied orbital, spin up and spin down, and so on up to n/2 highest occupied orbitals. And now the ansatz state is here. It's a bit of a lengthy formula, but the idea is pretty simple, because we are just superposing this Hartree-Fock state, and now we annihilate 2 electrons from some of these orbitals. From one of these orbitals, we take out 2 electrons, and we create them in some of the other orbitals. So we are doing something like a doubly excited states, and we superpose them with some alpha ij amplitudes, which square to 1. And now the whole difficulty is to find those parameters, alpha ij and epsilon here, from the condition that this state is supposed to be mapped to the given row. So in particular, the distance d it depends on epsilon in this way. Now I'm not writing the formula for beta because it's very long, but it's some expression in alphas. The point is that d is proportional to the total number of electrons minus the number of electrons occupying the highest occupied orbitals. So it has this. If this was the Bose-Einstein condensate, this would be the depletion parameter. But I'm talking about electrons, so that's some other entity. So the final point I would like to tell you in this talk is that the bound that I just showed you could perhaps be actually used as some useful approximate functional. So the idea is to, so we're saying we cannot find the exact functional, but we are taking the bound as and we are pretending that it's the exact functional and do the minimization, and hope that the minimizer will reflect some properties of the ground state, of the one-body reduced density matrix of the ground state. And the problem I studied numerically is called the electron transfer problem. So we've got a chain of sites with uniform hopping. The interaction was the Fermi-Hubbard interaction. The on-site potential varied linearly from site 1 being 0 at site 1 to some value at site D, so from left to right. It grew from left to right, and now we are asking about the average occupation number of the ith site in the ground state. So just for completeness, this is the Hamiltonian. So uniform hopping, VI on-site potential, which varies just like plotted here, some interaction strength and Fermi-Hubbard interaction. Why did I take this problem from all the possible physics problems? It's because it has been pointed out as one of the current challenges in the reduced density matrix functional theory. And this is a challenge because some widely used state-of-the-art approximate functionals give qualitatively incorrect results, even for the Fermi-Hubbard dimer. So what I did numerically, I took a chain of length 4, not 2. Qualitatively incorrect. So I can. So if you plot it, so we are changing V, the difference between potentials on the sides. We are plotting rho, the diagonal entries of the one-body reduced density matrix. The exact results are those plateaus. This is a bit small. So there were supposed to be crosses and red dots here and here. So for comparison, there is the Hartree-Fock method, which behaves completely differently. And those other functionals, they behave more like the Hartree-Fock method here. So they don't reflect, they don't give those plateaus. So we can see that this approximate bound works really nicely, at least for this short chain. So this is encouraging to maybe do some more numerics, some proper quantum chemistry numerics with this functional. So in summary, the repulsively diverging gradient could be considered as some very fundamental explanation for why there are the occupation numbers in the ground state of an interacting system are never maximal. So there are never n bosons in the ground state when there are interactions. And reproducing this repulsively diverging gradient could serve as a test for new approximate functionals. Because if this functional gives the gradient, it reflects the behavior of the exact functional, which is desirable, of course. And it worked for this chain that I showed you. And of course, there are some further challenges. There's a purely mathematical challenge, which I swiped under the carpet here, because there is no rigorous proof that the exact function is actually differentiable at the points that I was showing. It is a reasonable assumption. It's supported by some numerics and by analytics for the Bose-Hubbard dimer. But of course, I'm not aware of any proof of this fact, or of any counterexample for that matter. And some obvious other challenges would be to extend this to doublet sectors or triplet sectors and so on, so that they can be used in some quantum chemistry for molecules. So thank you for your attention.
Thank you very much. Questions? Please, Professor Żążewski.
If you would like to discuss, as you mentioned a couple of times, non-interacting fermions, could you tell us how is your approach comparing to the very primitive Thomas Fermi functional, or perhaps Thomas Fermi functional with the Weizsäcker corrections?
Well, I haven't really thought about this. So the functional, by construction, it will give you if there is no interactions in the Hamiltonian, it will give you just the Hartree-Fock result. So it will be exact by construction, because then we are minimizing.
But how does it compare to Thomas Fermi?
I'm not sure. I'm not sure. That's a good question.
Yes?
I have a question about the variational answer that you showed us. This one. So my first thought, it looks like a lot of variational answers that I've seen in the literature for example, for an impurity problem, but they were in the momentum representation. But usually we talk about the expansion in the particle holes. So you only take one term in here. Mm-hmm. You could imagine that you can take two fermions and other two fermions and put them in the different places. So how general is this variational ansatz? Because you can imagine the more general one.
So this works for any dimension, but the problem is that if we've got more than 4 electrons, it works only in some finite strip around those Hartree-Fock states. So imagine if you put more terms, you could in principle cover more density matrices. But then we are losing. What's nice about this ansatz is that that the one-body reduced density matrix is automatically diagonal.
Okay, so you just say that this variational ansatz is good, but it's not exact in the sense that you could imagine. You only cover some subspace of possible density matrix.
Yes. When there's more than 4 electrons. When there's less, then it's all the entire set. Up to 4, it's the entire set of.
Okay, you were thinking about only the space representation, spatial representation. You could also think about the momentum representation, and then you would retrieve this, let's say, Polaron ansatz, probably, and it would be I can imagine it was never rigorously covered in the literature.
Okay. But I imagine if you've got momentum, then you need some translational invariance, right?
Probably.
So here one of the points was not to use any symmetries.
Okay.
So
Yes. So are there any more questions? Adam, please.
Can you elaborate a little more about this statement that you made at the very end, that this divergence of this gradient gives you, so can you show me this? Yes. That you can never attain the maximal possible occupation number, because
this is actually just the numerics, yes?
Yeah.
This is a numerical method to find a ground state.
Yes.
So is there anything like which can lead you to this kind of a conclusion? Because this is a physical conclusion somehow.
Yes.
Yes, but there are like some ugly proofs of this or something like this, and this would be a very, I would say, nice and clean proof of this statement. But I have a feeling that the connection is a little bit ad hoc. So can you comment on this?
So I'm not sure why is it ad hoc, because I mean they've got this repulsive gradient, so if you minimize, you're just numerically kept away from this set, and that's I mean that's all I wanted to say about this.
The question is actually about the validity of numerical proof against the analytical proof. Yes.
The proof is okay. The conclusion is
Okay, I suggest that you discuss this later.
Okay, I'm
The conclusion is well known,
yeah.
and it comes directly from the Bogoliubov approximation to the many-body problem. It's a classic result.
Okay.
You want to answer something more?
Yeah, I don't want to take too much time. I'm not sure. So I try to think of this Bogoliubov approximation here too. Does it also assume that some translational invariance?
No.
No. But it uses momentum representation.
No.
No. Okay.
It can.
Well, of course it does if you apply it to the translational invariant
Yeah.
problem.
So I've seen
But
it
in
only.
the trap it doesn't use the
Okay.
momentum.
So I'm familiar only with the translational invariant setting. But also the Bogoliubov, it needs weak interactions.
Yes.
So here I'm somehow not using weak interaction assumption. But maybe maybe the fact that rho is close to this non-interacting set, maybe it implies that the interaction must be weak or something like that.
That would be my expectation. Yeah.
Okay.
So thank you very much. I can't see any further questions, so I would like to invite the last speaker of this session to come here and launch her presentation. We have a pleasure today to meet Małgorzata Siudek. As I said at the beginning, she is our first alumna who was awarded the PhD degree at the Center for Theoretical Physics in 2017, and all the procedure and voting and everything was done by our Science Council. And she worked as a research assistant in the group of Professor Lech Mankiewicz. And as far as I remember, she was always very active in the institute, also in the dissemination of science, science picnics and all those events which we love and we cannot enjoy during the pandemic time, but hopefully they will come back. And yeah, let's turn to Małgosia. And actually I would like to know what was after your PhD. You started a postdoc in Spain.
Yes.
Yeah. Where was it?
After my PhD in 2018, because
actually after, oh sorry, let's make it a little bit, okay. So actually after my PhD, I make a little bit of break because I had my second child and then went to a postdoc after my maternity leave. But first I would like to thank you for the invitation. It's nice to be here and I'm really grateful that I am able to be here in presence. So it's really nice to get out of the Zoom. And I know that it can be hard to sit down now for such a long time, and probably you are thinking already about the lunch. So, but please wait a minute. I promise that I will not show any equation in my presentation and some nice images maybe. Just going back, I wanted to share with you my first memory when I come to center. I was interviewed by Professor Lech Mankiewicz to start the internship during my master, and in those time, I couldn't decide which project I want to join, and he said to me, "You have a unique opportunity to join the Pie of the Sky, the project which is the pioneer and building the cutting-edge instrument for the new generation of the observations." And I was thinking, yeah, sure, I want to do that. And then my journey started and is still ongoing. And my passion to the cutting-edge instruments still exists. So in Spain, I'm Marie Curie fellow, and I joined PAU project, which also be the cutting-edge camera, which we can see here. This is the one, and it's located in the William Herschel telescope. And contrary to the Pie of the Sky system, or maybe better said, is said to, luckily for me, it's not totally automatic, and therefore I had to spend some amazing time in Canary Islands to make the observations. But honestly, it's not the topic, the project that I wanted to share and discuss today with you. I hope that at some point I will be able to share with you my work within PAU, Spanish project, but I found more really relevant to talk to you today about the follow-up project that started during my PhD. So sometimes it happens that PhD students made the project, and then they are forced to go to the postdoc and change the project, and are not able to continue the work started during the PhD. This was not my case. So during my PhD, one part of my PhD thesis was to develop a new approach to galaxy classification. And then it followed up in several projects, and which are still ongoing, but I selected 3 of them, just which are already finished, and I would like to present them today. So basically, I hope that I will have time to present everything. I would like to start with showing you how our galaxy classes are connected with the environment, and then how our new developed methodology can be applied for the future large photometric surveys, and the work done by PhD student Sebastian Turner about finding the synergies between low and intermediate redshift classifications. But let me start with some motivation why I started to work with the galaxy classifications. So here we can see the tuning fork diagram proposed almost 100 years ago by Edwin Hubble, and he divided galaxies based on their shapes into a group of elliptical galaxies and the spiral galaxies. Spiral galaxies he divided for the depending on the concentration of the spiral arms and if they hold or not the bar. The elliptical galaxies are distinguished in different types depending on their ellipticity. And in the between there is a group of lenticular galaxies. And basically every galaxy that didn't go into this category was classified as irregular galaxies. And there was a time where this diagram was thought to be an evolutionary sequence. So people were thinking that the evolution of galaxies is starting from elliptical galaxies moving to the spiral galaxies. But after 100 years later, we know that this picture is far too simple to mirror the true real zoo of galaxy classes, and moreover the evolution of galaxies goes another way, and as the spiral galaxies host new young stars, and when they are aging, they are becoming elliptical and full of red and old stars. So I think that we are living in an amazing times when during this 100 years our knowledge about the universe changed rapidly, and I think that this recently was also appreciated by the Nobel Prize Committee. What is the cause of our rapid change about our knowledge of universe? Is for the main ingredient is that we are now building the new generation of the telescopes. So when Edwin Hubble did his pioneering work about the galaxy classification, he was actually sitting on the table looking at the photographies, and based on the shapes he was able to classify the bright galaxies. But with the new generation of the telescopes, we can see more structures in today's galaxies, as well as we are able to reach the first galaxies that were formed. So this gives us the new opportunity to study the galaxy evolution, and this is then followed by the new approaches to galaxy studies. Also, this is accompanied by the increasing number of observations. When Edwin Hubble was starting his classifications, he was working on tens, hundreds of galaxies, but now we are talking about exabytes of data. So we know that it's not longer possible to sit down and just classify galaxies. We need to develop a new methodologies, because we are not able to do that by ourselves. So one approach was to ask people to help us. So you probably are familiar with Galaxy Zoo project, where the citizens were able to classify the galaxies. But now we are developing a new, more automatic tools. So the bottleneck is not now the data availability, but our ability to extract useful and reliable information from the data. And that's why I'm interested in the automatic pattern discovery, using all the information about galaxies that we have. So in my work, I'm trying to answer main questions like, why do these structures look like this? Why we have so much diversity in the galaxies? And taking the opportunity of the new generation of observation, going back and allowed us to analyze the past history of galaxies. I'm wondering what is the past history and how it has changed during the cosmic times. So this is quite new branch of of the studies, because normally we are used to distinguish, to follow the classification proposed by Edwin Hubble, and we are distinguishing 2 or maybe 3 galaxy types. But the question is it enough? Is it enough to study the galaxy evolution, different processes that regulate the mass assembly of them? So when I was starting my first paper, I was analyzing red passive galaxies, and I was using the color diagrams to distinguish these red dead galaxies. And I remember that I had spent a lot of time validating the contamination, the completeness of the sample, and I was thinking, are we truly need to do the sharp cut in some 2-dimensional space? We have new methodologies, so maybe we could use more information, more multidimensional approach. So here are the colors of the galaxies. This is RK and Novaire. So these are the just the photometric observations of the galaxies in different filters. So the colors are basically the differences in that. Yes, in the let's say the luminosity of the galaxies in different filters, and based on that we can predict what. Sorry, because here is an additional information about the density. So this is the specific star formation rate. So this tells you about the how many new stars are produced. So basically, here are the blue. This blue are corresponding to this blue spiral galaxies, which are still forming new stars, while these are the red passive galaxies, which are already filled by red and dead stars. Yes, at some redshift. About the cosmic time, I will be speaking in a moment. Now, so in my data, I have the great opportunity. During my PhD, I started to work on Vipers, which is spectroscopic survey with a similar statistical fidelity to the SDSS survey, which is the biggest, the largest spectroscopic survey of the local universe, so at low redshift, and Vipers is the complementary at higher redshift, reaching the universe at the half of its age. So this was the with Vipers we started the new epoch when we were able to trace the evolution from the structures observed at the half of the age of the universe to the well-known structures that we observed today. So I will go super quickly through the methodology. So as I mentioned, we developed a new methodology, which is based on the unsupervised clustering algorithm. And this is a novel approach which use the which first of all doesn't need any prior information. So far in astronomy we used a lot of supervised methods. So we basically we had the sample of the known galaxies, and we wanted, according to them, classify the new observed galaxies. But this doesn't allow algorithm to find the new shape. And as we know that the structures of the galaxies are more complicated that we were thinking earlier, I think that it's nice to it has the potential to ask the computers to find this these unique clusters in the multidimensional space. So during my PhD, I was using one of the algorithm which is called Fisher expectation maximization, which is consisting of two main assumptions. It's do the dimensionality reduction and the clustering to find the clusters of the similar properties of objects of the similar properties. And this method is based on the assumption that it finds the latent subspace. So if we have two samples in a two-dimensional feature space, then the matrix is transforming this into one latent feature space, which is able to divide them. And this is the iterative method which provides us with an adaptive method and iteratively finds the new subspace and the new new clustering, which finally the outcome is not the binary classification. So it's not 0-1. We have the probabilities of found for each of the galaxy of belonging to each cluster. So during the PhD, I was classifying Vipers galaxies and we found 11 subclasses which were well separated in the multidimensional space, but as unsupervised methods still pose a number of questions, we address them in my first paper by analyzing different properties that weren't used in the classification procedure and find these discontinuities also in the spectroscopic and morphological parameters. Then, after my PhD, we still were working on this classification, and one of the projects was focused on analyzing of the environments of this. So I was analyzing for this project. I was analyzing 50,000 of galaxies. So Vipers observed 1,000 of galaxies, but we almost 100,000 of galaxies. But I selected only the most representative, so only 50,000 of galaxies, to be sure that we are talking about the representative subpopulation of unsupervised. So no, it was only the cuts on the purity, on the quality of the spectroscopic redshift and the emission lines, if I remember correctly. So then we know that it's the processes, the mechanism that regulates the galaxy evolutions. Ones are the internal one, but there are also the external ones. So we wanted to see if what is the environment of our galaxies. So Dressler showed in 1980 that we can see that these blue spiral galaxies are mostly located in low dense environments, and in the dense environments we mostly find these red passive galaxies. but again, most of the studies so far were made only for the 2 or 3 group of galaxies and only at low redshift. So we took the opportunity to see how our classification and our classes are connected with the environment. So first of all, there is a bunch of definition of the environment. So just to be clear, in my work we were using the local density contrast, which is related to the local density of the density of the matter, and we can say that I will call it now delta, and when the delta is high, the galaxy is in the dense environment, while the delta is low, we can say that the galaxy is on the desert. Taking the opportunity that we had this unique set of observation at the half of the age of the universe, first of all, we've confirmed that the relation found by Dressler also holds at the at redshift 1. And after that, we looked into detail and asked if our subclasses can add us some more information. And for example, here we have the three red galaxies, and we found that one galaxies which follow the general trend of the fraction versus the delta is composed mostly by the small galaxies, and this gives us the hint that this class might be built by the red nuggets, the relics of the galaxies where the mergers didn't play so significant role as we thought that they are shaping the galaxy, the red galaxies. The same we did for the green galaxies, finding that there is a different behavior between low and high mass galaxies, as well as for blue galaxies when we find the subclasses with the increased activity. So with this, we showed that the more detailed classification can allows us to have the deeper insight into the influence of the environment on the properties of different population of galaxies. Then we wanted to test if this methodology may be applied for the photometric surveys. As we know, spectroscopic surveys are high cost and are limited to low areas, so we wanted to check if we can adapt this for large photometric surveys like LSC coming. And we did the same unsupervised classification on the photometric redshift, and we find that we are able to reproduce the spectroscopic classification with high accuracy. And additionally, we are able to separate the stars and the broad line AGN. So there is a lot of potential to use this method for also for other photometric surveys. And the last work is done by the PhD student Sebastian Turner in the Liverpool. So the former PhD, because he's starting his postdoc soon in Estonia. But the purpose of the project was to trace the changes in the galaxy classification from the which occurred from the half of the age of the universe to this epoch. But as we changed a little bit the input parameters, as in case of my classification, which I did for PhD, we note that some colors are more important in our classification, so we tried to balance it, and that's why we changed the input used to do the classification, and we do the classification the same for the intermediate redshift and for the low redshift sample. And both samples were in both samples we found 7 galaxy classes, and we can see that they are broadly consistent. So this axes don't have the physical meanings. They are corresponding to this latent subspace that I was talking earlier. But here we have the color diagrams that I showed before, and just comparing the intermediate and the low redshift, we showed that the complex structure that we observed today was already present at the half of the age of the universe. We only note some small some changes in the low mass red galaxies, which seem to be more influenced by the environment in our epoch. But it's time to finish, so I will just leave you with the summary. Thank you very much.
Thank you. You are on time. You are on time, so that's very nice. Questions? Please, Bożena.
Can you show again the previous slide? My question is whether all those classes really form a continuous distribution, or there is a gap. Just by eye, on this right picture, I see a gap, which means that evolving galaxies are jumping from, let's say, this class below the black line.
So let's say here
on the left, it looks more like continuous, really, distribution.
So yes, this is the region when we expect that we will see this the galaxies which are transiting from the blue to red galaxies, and just by comparing these two pictures, we can expect that more quenching is happening at lower redshift, but as we are not entirely complete with vipers at this region, we cannot say this for sure.
These are different instruments.
Yes,
right?
exactly. So we made a great effort to avoid the selection effects, but because we cannot be sure, because these are different calibration, different instruments. That's why it's only, I would say rather that it's only the hint about that something may going else in this region, but not for sure. I think that we need still more observations made by one instrument.
Yes, Swayam.
So I have most likely a question which is maybe more generic. So in terms of this method, thank you. So in terms of the method, the second part involves this clustering. So as I understand, there must be some kind of hyperparameter space which deals with basically defining a distance so that you can make those clusters.
Yes, so I didn't devote a lot of time of this, but the parameter space was a little bit different in two different projects. So in the last project, the parameter space is built of the colors, starting from going with the increase of the wavelength from the sets, whereas in our first classification, I don't know if I have showed it, we used just all the absolute magnitudes, but normalized to I magnitude. So that's why the UV colors were a little bit more important in our classifications, and therefore we were a little bit more sensitive to the recent star formation activity.
Thank you. So what about the hyperparameter space, which actually goes into the clustering aspect? Because I see that you have made those groups.
Yes. So this is the parameter space. These magnitudes are the space, and then the algorithm is just transforming them to some latent subspace.
Okay, and they are individually being able to be clustered all together.
Yes, all together.
Great, thanks.
I see there is one more question, Karol.
So you mentioned this nice web page, Zoo of Galaxies, at which everybody could look at many pictures and even give some information concerning the kind of galaxies. I recall my kids were very much involved in this many years ago. So the question is, do you know whether it was really possible to make some usage for scientific purpose of all this information gathered from amateurs?
Yes, I can point you, I suppose, to the direct paper of Masters et al. 2019, I suppose, when they it was one of the most important paper highlighting the citizens' effort that they made, because she showed that because of our common effort, we found that this diagram was far too simple to reflect the real zoo of galaxies, and there is a lot of information and what has changed, and mostly it was because of the Galaxy Zoo.
So if that was the last question, I would like to thank all the speakers of this session, and thank the audience for coming here and for all the lively discussions. And also I would like to invite you today, late afternoon, there is a poster session where our other alumni or PhD students are showing their very nice results in the posters. And announcement.
Just a reminder that I remind you that we'll start 10 to 3, so the next session will start a bit earlier, because FNP session will be extended by a talk of Professor Birula. Okay, that's it, thank you. And I wanted to, I hope that you appreciate that we now have a red color on our slides. So I'm grateful to Paweł and the company Wypożyczenia.com. They brought their own projector, so we are not using the mounted one. So thank you.
I zobaczymy, czy mnie słychać. Raz, dwa, trzy.
Troszeczkę wyżej mikrofon.
W którym roku? Ja mam przypominać, ja nie pamiętam. Który obroniłem się? Czy napisałem? Bo to... Raz, dwa, trzy, raz, dwa, trzy. Fajnie. Już?
Good afternoon, everybody. This session is devoted to Nobel Prize winner, Polish Nobel Prize winner.
So I'm leaving now. If
and first speaker is Krzysztof Pachucki, Professor Krzysztof Pachucki, an outstanding Polish theoretician. The title of talk is there. I'm not going to read it. I remember him as a very young fellow, the doctorand at our CFT. He reminded me that to enter the doctoral studies at CFT, he had to pass an examination, and he did it during his military service. I would like to say something which is probably in Polish culture. Polish is probably not a very high compliment, because he was very brilliant, He was very clever, very sympathetic, but many of our doctorants were like that. However, Krzysztof Pachucki, moreover, was exceptionally hard-working fellow. And this was really exceptional. This was how I remember him. Okay.
Jerzy, thank you very much for such an introduction. I don't think I'm a hard worker or heavy worker, rather. But anyway, if you think so, let me present the topic of my presentation: precise atomic spectroscopy and search for unknown interaction, in a little bit wider context. So, how we test fundamental interactions in laboratories. One way is, for example, to scatter particles at very high energy, GeV, at TeV, and this is what CERN is doing, trying to discover some new particles, trying to discover some, measure the transition rates, decay rates, and check if they agree with the theoretical predictions. Another approach is to perform measurements at very low energy, sometimes on the tabletop, but not to go to high precision, but not to go to high energy, but to go to the very high precision. And there are several ways to verify, to test fundamental interaction. One way, for example, is to search for electric dipole moments of elementary particles. For example, neutron. A neutron is a spin 1/2 particle, and it has a magnetic moment, but it may also have electric dipole moment. Why not? But if it has an electric dipole moment, it violates the inversion symmetry and also time reversal symmetry. And we know that time reversal symmetry is broken in the nature, but this violation is very small. So nobody yet has observed the electric dipole moment, but the measurement of the detection of the electric dipole moment of the neutron would be a clear indication of the violation of the standard model of fundamental interactions, because it predicts, but at very low energy, at the very low. It predicts electric dipole moments, but at very small value. I think at the order of 10 to minus 40. Now the limitation is about 10 to minus 32, 10 to minus 33. One can also search for electric dipole moments of electrons or even atoms, and there are several experimental groups who are looking for the electric dipole moments of fundamental particles and atoms. Another approach is to measure the magnetic moments. And if you measure magnetic moments of the proton, it doesn't say you much, because you cannot calculate magnetic moment of the proton. But considering the leptons, like electron muons, we can calculate the magnetic moment of the electron and muon from first principles, only knowing the fine structure constant and the mass ratios. And the best example is muon, because muon is much heavier than the electron, so it is more sensitive to some unknown particles of larger mass. If there are such particles, then we would observe a difference between the measured magnetic moment of the muon and the theoretical predictions. And indeed, we observe such a difference of the order of 4 sigma, which we so far don't know what is the origin. The experimenters are trying to push the uncertainty to narrow the density to be sure that this experimental result is correct. If they confirm in a couple of years, then we have a clear discrepancy and can look for some explanation, some new forces, some new interactions. The only problem is that we have only just one parameter, magnetic moment of the muon. Nothing else. So it is very difficult then to find out what this discrepancy comes from. Another approach is, for example, to determine the constants by different means. And I will describe a little more about the determination of the fine structure constant. But this is also approach. It's another approach. If you observe the difference between the different approach, okay, this means that there are some effects which are of unknown origin. One has to correct maybe the experiment. But if experiment is confirmed, then this is a clear indication that our theory is incorrect. And I will describe this in a little more words on a few slides. Another approach is, for example, to study spectroscopy of exotic atoms, like Electron-Positron. It forms an atom, and one can make a spectroscopy. We can calculate very accurately such atoms, and then compare with the experiments. And several such measurements are being performed with electron and muons. And the last approach, which I will mostly concentrate, is the spectroscopy of simple atomic systems, like hydrogen, helium, hydrogen molecule, even lithium, beryllium, and compare theoretical prediction with experimental result. Here we have a problem that spectra of even such a simple system of hydrogen depends on many physical parameters like Rydberg constant, fine structure constant, electron-proton mass ratio, even finite size of the proton, distribution of the magnetic moment within the proton. So a lot of parameters which are not aware of. So to test fundamental interaction, one has to combine several transitions, not only one transition, combine several transitions to remove this dependence. And I will describe this in a moment. So, why I think the spectroscopy, atomic spectroscopy is one of the best way to test fundamental interaction. It is because it can be extremely precise. An example is the 1s2s in hydrogen. It's a 11 years old measurement. It is accurate to about 15 digits, which is okay. But it's not the limit. The atomic clocks are stable up to 10 to the minus 18, so one can even measure more accurate. Here the limitation is nature width, because nature width is about 1 hertz. 1.2 hertz, so it is a limitation of this nature width. But there are some transitions which can even measure more accurately. Very good. How then, what are the theoretical predictions? In fact, we cannot use all these digits. As I mentioned, we need several transitions to be able to draw some conclusions. Another example is hydrogen hyperfine splitting. It's also known very accurately, with maybe 14 or 15 digits. And how accurate are theoretical predictions? No, theoretical predictions ends at the 5. We cannot get more accurate. And the reason is very simple. Because at this digit, the distribution of the magnetic moment within the proton enters. We know approximately what is this so-called magnetic form factor, but we don't know it's enough accuracy. So we can calculate this at the precision of 33 ppm. So this 33 is 6 digit. 1, 2, 3, 4, 5, even it is 0 here. So at this precision we can do the calculation. All the other digits are impossible for us to predict it. But we can, for example, compare hyperfine splitting with hydrogen with hyperfine splitting with anti-hydrogen, and then check if there are differences. In fact, there are measurements of hyperfine splitting with anti-hydrogen, and the result is the same like in hydrogen, hopefully. Otherwise, it will violate the CPT theory. Another example is, okay, what about comparison of hydrogen hyperfine splitting with the muonic hydrogen hyperfine splitting, where electron is replaced by muon? It is much more closer to the nucleus, and then it is more sensitive to nuclear size, nuclear structure, and the comparison we can check if it agrees. But the problem is to do the measurement. So such a measurement has not yet been performed. It is being planned by 3 independent groups in the world, but none of them was able, after 5 years of working, able to complete such a simple measurement. In fact, it is not so simple. And another way is to study the exotic system, like antiprotonic helium. Such a system is studied for about 20 years in CERN, and they have very accurate predictions for antiprotonic helium because it's a long-lived atoms. It lives for milliseconds, so one can perform accurate measurements. Another example, which I like very much, is a recent measurement where one considers such a system: proton, proton, and electron. We called it H2 plus molecule, or HD plus, if it's a proton, deuteron, and electron. we prefer to have HD plus because of the small mass difference. The small mass difference allows for existence of electric dipole transitions. Otherwise, we don't have electric dipole transition. But if the masses are slightly different, the electric dipole magnetic transition, electric dipole moment doesn't vanish. One can perform the spectroscopy, and in fact, the best electron-proton mass ratio is obtained from the comparison of the experimental transition frequencies with comparison to theoretical predictions. And then one obtained the best electron-proton mass ratio. There are two papers in Nature and Science a year ago. One can also use a little bit more complicated system like helium, H2, for example, for determination of magnetic moment of deuteron quadrupole moment, and also for example, to measure the charge radius of helium. It is a project which I have been realizing for a couple of years. Unfortunately, our result does not agree with experimental values, and we are looking for the mistake. And let me present this project on the helium and hydrogen molecule. Is rather complicated, and we have a virtual group, which I have several collaborators from Praga, Wojciech Patkos, from St. Petersburg, Vladimir Rochin, and from the University of Poznań, Komasa, my former PhD, Marek Żukowski. As I mentioned at the beginning, that one of the way to test the fundamental interaction is comparison of fundamental constants. And one of the most fundamental constants is fine structure constant. And what is the way to determine the fine structure constant? The best way is from the electron magnetic moment. Because the electromagnetic moment, according to the Dirac equation, is 2. Or this prefactor. Magnetic moment is equal to G times Bohr magneton. And this G is a dimensionless quantity, and we call it G factor, and according to the Dirac equation, it has to be 2. And then there are some QED corrections. And these QED corrections can be calculated. And they were, such a calculation was being performed for 30 years. It's known very accurately, about, I think, 11 digits. And one can compare with experiments. And there are several experiments. The most recent one was performed by Jerzy Gabriels. And from the comparison of theoretical predictions with experimental value, we got the fine structure constant. And similar comparison was performed for muonic G-2, and for muonic G-2 we observed a discrepancy. And now, from the electron G-2, we can determine the magnetic moment, and this is we can determine the fine structure constant. This is this value of the fine structure constant as obtained from the electron magnetic moment. However, there are also two other measurements. One can observe the following. Take the atom. Atoms absorb the photon, and we know that the photon has some momentum. So after absorption, this momentum is now transferred to the momentum of the atom. If it's just a single photon, it will be difficult to measure. But one can perform several such, or dozens of such absorption. So this atom gains some momentum. One can measure this momentum by comparison of two paths. Of one atom which didn't absorb this several photons, another which absorbed. One can compare the momenta and measure this momentum. And this is another way to measure the fine structure constant. And there are two measurements based on rubidium and on cesium. I would say, in spite of the fact that they differ by 2 sigma from the G-2, but everything is at around a 10 digit. So there is agreement, there is a slight disagreement on the 10 digit, or even on the 11 digit. The difference on the 11 digit. So there are two completely different ways to measure the fine structure constant, and if we agree on the first 10 digit, I would say, and disagree on the level of 2 sigma, I would consider this as a very good confirmation of the quantum electrodynamics, because there are very different ways to determine alpha and to obtain agreement at the level of 2 sigma. And this I would consider one of the best tests of quantum electrodynamics, because it doesn't involve any unknown factors. All other measurements require elimination of unknown factors. And as I mentioned previously, with the muons, we observe the discrepancy. In fact, it is 4.2 sigma discrepancy, and we between the standard model prediction and the experimental value, and we don't know what is the origin. Maybe there is some new physics. It requires a confirmation of this, to narrowing this experimental uncertainty, also narrowing this theoretical uncertainty, which is rather difficult. And then, if this 4 sigma goes into 5 sigma, then we have a common assumption that 5 sigma is we can say it's a discrepancy, and it requires a confirmation. It requires explanation. Regarding the atomic spectroscopy, one of the main uncertainty of the atomic spectroscopy is the fact that the nucleus is not a point particle. It is, for example, a proton or heavy nucleus, or another nucleus, heavier nucleus. It's not a point. So it has a finite mass, but it also has a finite charge distribution. And we approximately know what is charge distribution, but it's only approximately. It's very difficult to measure this charge distribution. So one of the way is, for example, to obtain this charge distribution from the atomic spectra. And the best way is to consider the so one way is to compare the theoretical prediction to 1s, 2s, and to 2 other transitions like 2s, 2p, 2s, 3s, 2s, 4s, and adjust unknown constant. This unknown constant is the Rydberg constant and the proton charge radius. And from this one obtains, this proton charge radius shifts the energy levels in this way, is proportional to the wave function of the region times mean square charge radius of the proton, and gives some, and one obtains some the charge radius. Similar determination can be performed not from the electronic hydrogen, from the muonic hydrogen, which is much more tight, is much more smaller, is more sensitive to the proton charge radius. And such a measurement has been performed 10 years ago, or 11 years ago. We expected that we have a just more accurate determination, but in fact, these 2 measurements disagree significantly. I mean, the measurement of the proton charge radius between the hydrogen and the muonic hydrogen. And this is the beginning of this history. In 2010, 2013, there were 2 measurements of the proton charge radius, which lies on this line. The electronic measurements, I mean, from the hydrogen spectroscopy, from electron-proton scattering, lies in this band, and we have 5.6 sigma discrepancy. Nobody knew what is the origin of discrepancy because it cannot be explained in a simple way. It is too large a discrepancy that can be explained by some mistake. It's much too large. So, and since then, people start thinking what can be the reason, what can be the source of discrepancy, and there were 7 new measurements on the electronic side. So there are, again, original muonic hydrogen measurement, next one, muonic deuterium measurement, all of them are in agreement, and then new experiments on hydrogen. 2s4p from the Garching, again in agreement with the muonic hydrogen, 2s2p, also in agreement, and the very recent one, 1s3s, it's here. It's also in agreement. So all the new measurements in hydrogen happen to be in agreement with the muonic determination of the proton charge radius. Nobody knows why. I mean, nobody knows what is the reason that the original hydrogen experiments were incorrect. It is unknown. In fact, this transition to 1s, 3s has been measured almost at the same time at the different laboratories. One in Paris, another in 2020 in Garching, and they disagree. Nobody knows why they disagree. It's difficult to say, but now means since most of the independent determination agree with the muonic hydrogen, CODATA 2018 assumed that this proton charge radius is the one obtained from the muonic hydrogen. So we think that there is no new physics there, but we still don't know what is the reason that these 2 different way to measure hydrogen spectra give different results. We don't know it yet. Similar measurements has been performed for not for hydrogen but for deuterium, which is heavier isotopes. And for deuterium, it was the same situation. And after correcting the proton charge radius, now we agree that this deuterium charge radius is in agreement with that from the muonic deuterium. As I mentioned that there are no yet measurement of the happy-fine splitting in muonic hydrogen, but there is a not very accurate measurement of muonic deuterium. We try to compare with our theoretical prediction. In fact, we obtained a strong disagreement. And also, we don't know what is the region. The happy-fine splitting value is the following. The theoretical predictions assuming point nucleus is this following. The difference comes from the deuteron size. And if we include only deuteron size, we have a just opposite sign. We have to include the nuclear porosity. We obtain something like this. And still there is kind of a little bit of discrepancy. We don't know what is the reason of discrepancy. Somehow, the nuclear theory is not something like an atomic theory that you have a well-defined Hamiltonian. In nuclear theory, we can write the Hamiltonian, we don't know what is the accuracy of these parameters. So it's, in fact, it's difficult to justify the accuracy of the calculations. So we obtained this agreement, but we don't take it very seriously. We think that this nuclear theory, even such a simple nucleus like deuteron, is not well known. Another very recent measurement is the helium. In fact, in helium, helium is also a very good example because nucleus doesn't have a spin. It's a spin zero nucleus. So one can compare the determination of the charge radius of helium, which is alpha particle, from the muonic helium and electronic helium. In electronic helium, there is a problem that if we take one electron out of the helium, then we have helium plus, and then it's almost like hydrogen. The only problem that this transition, 1s to s, is in the ultraviolet, and there are no lasers there, so it's very difficult to perform measurement. Now, there are two groups in Munich and Amsterdam who are trying to perform the 1s to s measurement in helium plus. Maybe they will obtain this year or maybe next year. And by measurement of 1s to s in helium plus, one can determine the alpha charge radius and compare with the muonic determination. This will be a very good test because if we have agreement for protons or disagreement for the different units of hydrogen, it will be very important to know how it is for helium. So for helium, in fact, there is no yet electronic determination, but there is only muonic helium determination. The muonic helium determination is the following. It's very accurate. And let me point the following, that there was an older measurement in 1977 who claimed that they measured that they observed a transition in this band and determined the charge radius, but a different one. And this experiment, this very new one, proved that the older measurements were just incorrect. They observed something, some signal which cannot be associated with the 2s to pi transition in helium plus. So this is a very recent measurement and obtained a very accurate helium charge radius, which we plan to compare with the electronic determination. As I mentioned, there is one possibility is to perform such a comparison with helium plus, but the experimental is very difficult. We can also perform such a comparison with atomic helium. And with atomic helium, it was in fact my project because there are measurements on atomic helium which are accurate enough. For example, the 2 triplet S to triplet P transition is accurate enough for determination of the alpha charge radius. The only problem is to do the calculation. So we tried very hard. We have been working on this for a couple of years, obtained the result, which unfortunately is in disagreement. What I mean it is in disagreement is the following. If I use means our recent calculation, it is in very good agreement, in fact, but for the difference. But we observe discrepancy for the different transition, for 2 triplet S to triplet D, 2 triplet P to triplet D. We observe a discrepancy for other transitions. So we think that we have made a mistake, such a mistake that it cancels out for the difference, but it appears only for the difference between triplet S and triplet P. It appears only for the transition between different levels. I'm finishing. So, for example, this is the experimental value for the ionization energy for triplet S state. This is the theoretical prediction, and the difference is of the order of 7 sigma. Is 0.4 megahertz. And this same is different for triplet P, so it cancels out in the difference, but doesn't cancel out with comparison to triplet D, and we observe discrepancies with other states. We don't know what is the source of discrepancy. Checking this calculation will take another couple of years. So this is the scale of difficulty in this calculation. And let me finish that although it was difficult to determine the charge radius, one can determine the charge radius difference between helium-4 and helium-3. Because for the difference, all this correction almost cancel out, and it's much easier to do the calculation. In fact, the situation is not so obvious. There are several experiments, and almost none of them agree with each other. So we don't know what is the difference. And in fact, this Munich helium group is now planning to perform the measurement. In fact, they have done measurement. They are now interpreting the data. And it was very interesting to compare the isotope, the difference in the charge radius between helium-3 and helium-4 with that from the Munich hydrogen, with the Munich helium. And then we come to which experiment would be correct. I think the theory for the isotope is very simple. So we think it's maybe one of the experiments is correct. We don't know which one, and we will this year we expect the result for the Munich helium-3. So, let me finish by presenting now what are the further options for testing fundamental interaction in precise atomic physics. As I mentioned, one of this is measurement of lamp shift in helium-3. Another, which is also ongoing, there are two measurements in helium+. Of 1s to s transition, they are very difficult. Another is Munich hydrogen hyperfine splitting, and to compare with electronic hydrogen. Another is such a system which consists of only point particles, muon and electron. It's a point particle, so we can have very accurate theoretical predictions. The only problem is that this is a muon, it's unstable. It lives only 2.2 microseconds, so one has only a window of 2 microseconds to perform the measurement, to combine the muonium and perform the measurement. In fact, there are some, means the results here are not yet competitive with respect to the normal hydrogen. Another way is, for example, by a comparison of muon-proton scattering, or for example here, electron-proton scattering, muon-proton scattering. And then check if there are such differences in observing the scattering. Such a project is ongoing. It's called MUSE at PSI. And there's also another project at CERN, where people from my faculty are involved, is to measure once again the muon-proton scattering at very high energy, which I believe is more sensitive to the proton charge radius. And finally, there's also a project to form another bound system, which has not yet been found, is the proton-antiproton or antiproton alpha. And such a system, certainly the ground state will immediately disappear due to annihilation. But if antiproton is a very circular orbit, let's say L = 40, that will live forever, and one can compare theoretical predictions with experimental result. And this, I would say, this is one of these best systems to study in the near future. Thank you for your attention.
Thank you very much. Questions, remarks? Okay. If no, then we... Bożena.
Very naive question. In the case of proton, you said you have a structure because of quarks, right? But in the case of electron, is this an assumption that electron does not have a structure, or is this observational fact?
No, it is both. Both. It is also observational fact, but observation is up to some TeV. In fact, I don't know exactly what is the energy, but it's also a fundamental assumption in the construction of the standard model that leptons are pointless. No, the leptons are point-like. So this is also if one observes a structure of the electron, this would be a discovery. I would say it's a new physics. In fact, it would be very interesting. But it's not so easy to observe the structure of the electron, because the structure of the electron can be observed by scattering electron of another particle which has a structure. So it's, maybe it's, by scattering electron with another electron, or with electron with a positron. Yes, this way one can observe the structure of the, but so far has not been yet observed.
So
another very naive question from a layman. Krzysztof, you mentioned something about the magnetic dipole of a proton, but it's that we don't know enough about this. What is the problem?
It's known. In fact, magnetic moment of proton is known with 10 to minus 10 precision.
You mean theoretically or experimentally?
Experimentally. Theoretically, you are not able to do the calculation with the first, maybe the first digit.
So that's my question. Why is it not possible to? I mean, is it not possible to do it theoretically, or is it difficult computationally? What are the problems?
It is a very good question to Lech Mankiewicz, who is who knows strong interaction much better than me. And the reason is the following: that to calculate the structure of the proton, one has to use this. One has to take into account the strong interaction between quarks, and this is in the unperturbative regime. You have to do it on the lattice, otherwise because you don't have an expansion parameter. On the lattice, you mean they have to model the three or four dimensional lattice. I don't know. Maybe 3-dimensional lattice, maybe 10 by 10 by 10, or 20 by 20, and then you exhaust the computer memory. So you cannot. There are lattice calculations, but they can predict maybe first digit or first 2 digits. One cannot calculate magnetic moment of the proton with 10-digit accuracy. There's no way.
Okay, thank you very much.
Okay, so thank you very much again. And according to the schedule, the next speaker is Professor Żukowski, and this will be online talk. Is it possible to check whether...
Yes, I am here.
He is already there. Tak? Okay, so the title of the talk is Multi-Photon Entanglement and Interferometry and Wigner's Friends. Okay, so go ahead.
Thank you very much. So I'm very happy to be. First of all, am I heard? Can you hear me? Okay, very good. So I'm very happy to attend this super seminar, and let's say I congratulate the center so many years, and I have to declare that the center was always a kind of, let's say, example for us, and we tried to catch up with it, and we shall continue here in Gdańsk. And one of our, let's say, one of the ideas of forming ICTQT, of which I'm the director, was to have also some kind of little center like the one in Warsaw. So so let me start with my talk. I hope that I will find the right. The right screen to share. Sorry, I have some trouble in control of my. Okay. Now everything works. So the title is, as Chairman said, Multi-Photon Entanglement and Interferometry. And Wigner's Friend, there are two types of English ends to show that there is some kind of difference between those two parts. And why the first part, let's say, as I'm in the session of FNP awardees, let's say the prize that I received was mainly for multi-photon entanglement interferometry, and that's why I wanted to say something related to that. And then, as my work is quite often linked with foundational aspects of quantum mechanics, so I will tell you some things about the Wigner's Friends and the way they were, transfigured or misrepresented in recent times. And as I'm a representative of this International Center for Theory of Quantum Technology, which exists only from 1918, and it is totally funded by Foundation for Polish Science, FNP, and the money that funds us is European money channeled via several, let's say, pipelines, but really the origin is the budget of EU. And the abstract that I have given reads more or less like this, that multi-photon interferometry allows us to observe strange quantum phenomena. They are paradoxical if one uses classical concepts. And for example, Bell test showed what quantum theory is not. And we are living in this era where quantum information science and technology emerged, and this is because many of the Gedanken experiments of the past are now possible to in the laboratories, and they find applications in quantum technologies, and therefore one has to understand what is behind those Gedanken experiments. And what I claim, and that will be the leitmotif of my talk, is that interpretations of some of Gedanken experiments go too far, and I will concentrate on first on let's say 1.5 Gedanken experiments which are turning real in photon, really two. No, it depends on the interpretation. 2 to 4 photon entanglement interferometry, and then I move into something which is much more foundational, and is a Gedanken experiment per se at this moment. Okay, sorry, I don't know why I cannot. Okay, so this is my first part as it was promised in the abstract, and the first part is based on an article which is in archive, and it has been submitted and not published yet because of the mania of the universities to collect the so-called points before the classification of universities. We are searching for a journal which will give us, which will publish us and give us as many points as possible. And this is the reason for the delay. And the paper is wave particle complementarity, detecting violation of local realism with photon number resolving weak homodyne measurements. And that is my team, and perhaps I will present them in such a way that there's Tamogna, Antonio, Marcin, Bianca, they form my group. Still there is Konrad, who is not co-author of that, and Marcin Karpiuk is a guest author from another group of ICTPT. And so this is the team responsible for this work. Okay, and so I promised a little bit of interferometry at the very beginning. So this is the interferometry. Okay, so this figure shows a schematic of 2 experiments, if you see, there is a kind of source A, which is in this box, and source B, which can replace this one for the experiment B. Okay, so let me talk about experiment A, and this was presented by Tan, Walls, and Colette in 1991, and it's quite famous and stirred quite a lot of controversy at that time, but I would dare to say that initially it was kind of interpretational controversy. And what we shall show is that some of the claims of the papers were totally wrong, and that's a little bit a different story. And the Tan, Walls, Colette was selling this experiment as something that shows single photon non-locality. Okay, so we have a single photon, just one photon, a Fock state, okay, of one photon impinging on the initial beam splitter, which is 50-50. On the other side, there's just plain vacuum. And then it's obvious to you that there will be a superposition of photon being here or being there. But if you go into second quantization, perhaps I will, I don't know why it doesn't work. Perhaps I will be able to move. In the second quantization, you can rewrite the state if you take into account the states of the beam 1 and beam 2 in such a form, and it looks like a maximal entangled Bell state, and therefore, let's say at that time there was a gut reaction. Oh, so we can violate a Bell's inequality. We are very happy, and they suggested the following contraption, and that was a very interesting contraption. But they wanted to use weak homodyne measurements. Okay, so here comes a local oscillator field on both sides. Another local oscillator field. Of course, it's a coherent state of the light, and not only this photon here or there impinges on the 50-50 beam splitters, but also this local oscillator. And of course, what the gut reaction at the time was to vary the phase of the local oscillator. Just if you worry about things, let's say, really to do the experiment, both local oscillators fields must come from this one source to have a stable phase relation. Okay, so don't worry. Sorry, there were some sounds. No, everything okay? And of course, then the counts were supposed to be measured. Okay, and according to Tanwol's Colette, there is a violation of Bell's inequality in such a contraption, and therefore, according to their words, some of you know that I hate the term non-locality, but I'm in this moment I'm quoting, and so the quotation is they show non-locality of a single photon. So this is our let's say starting point. The claim of Tanwol's and Colette that this represents a Bell test. Okay. What is interesting? Some years earlier, there was a first experiment which suggested observation of effects related with entanglement and in a weak homodyne measurements, and that was proposed by Grangier, Potasek, and Jerky, and it was using the emblematic source for entanglement, which is parametric down conversion. Everybody knows that it's let's say that it gives an entangled state, and it was a weak. If you look at the let's say the paper more carefully, you see that it's weak parametric down conversion, and of course the local oscillators. So the measurement part was identical with the Tanwol's Colette experiment, and here also weak homodynamic was performed. So it's a kind of emblematic source of entanglement. And one of the things that is in our paper is that after analyzing this paper of Tanwol's Colette, we noticed suddenly that Grangier, Potasek, claim that this experiment is a proper Bell test. Is we do not have a proof that it's unfounded, that it's wrong, but it's unsubstantiated. So there is no proof that it is so. But let's say our very strong conjecture is that this is so. Okay, so let me summarize. So we are talking about photon number resolving weak homodyne measurements, And what is very important, they are now feasible. The group of or groups of Walmsley are able to perform such experiments. And as a matter of fact, they exactly did such experiments a few years ago, but unfortunately followed the interpretation of the original authors of the papers. Okay, and this first experiment can be neutrally called as excitation of spatial modes by a single photon, okay, without all this ideology, okay? And what we show that in those weak homodyne detection with measurement settings defined just by phases, okay? So the local oscillators are of constant strength. There is no well-known classicality. How do we do it? We show just an exact, perfectly exact local hidden variable model for that experiment. And so this is bad news, but on the other hand, there is something that is that was, of course, our inspiration were the works of Hardy, if somebody of you knows this, but we went a little bit further with this, and we now claim that still such in case of such sources, but not measurements, one can violate Bell's inequalities, but we have to, in a way, utilize the kind of full complementarity of wave and particle aspects of photons. Okay, so one of the alternative Bell settings must be when there's no local oscillator, and even the beam splitter is removed. Okay, so we just measured whether the particle is there or not. Okay, and we call let's say this an off settings, and something like that gives an indisputable violation of local realism. So let's say instead of Tan-Walls-Colette idea that there is always a constant local oscillator here, constant local oscillator, and they just vary fields, we have an off situations, and even more, what is very important, we also tune the reflectivity, and of course transmittivity too, of the local beam splitter. So they are not 50-50, and then at certain moment we find an optimal transmittivity on both sides, and then we have a strong violation of Clauser-Horn inequalities. And there are some still additional details to be said about this, but perhaps I will come back to the motivation for that. The motivation is like that those experiments, they live in the literature, and most probably students learn that they are representing some of the most striking features of non-locality in quantum mechanics, which may be demonstrated using phase-sensitive measurements on the field produced by a single photon. These effects may not be explained classically using a particle wave or hidden variable theory involving local causality. Okay, so such claim is, for example, in the textbook of Milberg and Walls, and of course, our finding shows that it's other way around. And we just found another textbook in Springer, which is a good publishing house, the story of light science from early theories to today's extraordinary applications. And there is a generalized version of that type of experiment shown there, and a lot of conclusions drawn, and of course they are unfounded. And just a word or two, let's say the quantum predictions for the Tan-Walls-Colette, they look like this. So they are quite simple, and what is very important is this interference term that depends on the difference of the local phases, and that's why it looks bellish. And we adapt a model by Jan Oke-Lachun, my old collaborator, with whom we also created a model for so-called two-photon Franson interferometry and showed that it's also not a proper Bell experiment. So it's in a way based on those models, but our model is quite complicated. Of course, once you get the gist, you can reproduce it. Okay, but it's quite complicated because, as you see, we have to model all those events. But it turns out that the Jan-Oke model can be partially applied to each of those situations, and then we have a convex combination of models. And what is very interesting, so these are charts which you can find in the archive concerning Jan-Oke's model. There's no time for me to explain them. And this model fully covers the range of homodyne strength for which Stanwolds and Collett predict a violation of local realism, because our model works for such values of alpha. And on the positive side, it turns out that you can cure everything if you use Clauser-Hahn inequality, first of all, but in a specific mode. Okay, all events in the Clauser-Hahn Bell inequality, which are here, and this is let's say inequality satisfied by local realism, and if all those events are despite the fact that we talk about fields and we have those homodyne measurements and whatever, we concentrate on events related with projectors. So they, let's say, from the quantum point of view, every event is a projector. So event A prime is a single photon detected in mode D, and no photon in mode C1. Okay. And we have a beam splitter with optimized transmissivity and the local oscillator on. Whereas the event A is the one where the local oscillator is off. And I would beg some people to switch off their microphones because there's a distortion. And the event A is just a single photon in D, the oscillator is off, and there is no beam splitter. Okay, and of course the detector C in such a case is mute. If we come back here, okay, just imagine that there's no local oscillator, there's no beam splitter, so the single photon can be detected only here. Okay. And so with such alternative experiments and such Bell inequalities, we can violate the inequality. And so still, let's say it is, let's say, if one works hard. And we have a conjecture that the Grangier-Potasek hierarchy experiment also has a model. And for the dominant counts, we have a explicit model, but further on, the interference becomes prohibitively complicated for a trivial model. Okay, so let me now jump to I hope that I, let's say, have 40 minutes, and I passed now 20 minutes. Okay, so the second paper that I would like to discuss is Physics and Metaphysics of Wigner's Friends, and subtitle, even performed pre-measurements have no results. And that's with Marcin Markiewicz, who sorry, he's not a member of my group, but he's so-called independent researcher in our center, but he's very much collaborating with our group. And this is the archive version is here, and what is very important in the archive version, you can still find my dedication to the memory of Fritz Haacke, with whom I worked on quantum measurement theory, and we have a joint paper on that in 1993. And this very much helped me to understand this this problem of Wigner's friend. Unfortunately, physical regulators does not allow, let's say, in acknowledgements to give such statements about to whom the paper is dedicated. As a matter of fact, I know that Fritz was a great friend of the Warsaw Center. So I have to tell you that in my friendship with him was not only linked with physics, but also we were both long distance runners. So we were running every second day around the lake in Essen when I was there. And as a matter of fact, 1 year before his death, he came to Gdańsk from Germany on electrically supported bike to Gdańsk. We met, and then that was the last time that I saw him. Okay, sorry, I don't know why so I will skip the abstract of the physical regulator. So everything started with the paper of Frauhinger or of Renner. And I kind of lived with this paper for some time. As a matter of fact, when I heard it for the first time at a Vienna conference, I didn't understand a word. But then I noticed that the interest in this grows and grows. There was supposed to be some kind of new paradox about quantum physics, and seemingly very strong. Just look what a claim. Quantum theory cannot consistently describe the use of itself. Okay, that's very, very dangerous. Seemingly, this paper ended up also at the cover page of New Scientist. But I kind of was not observing the developments. But finally, I found a paper with, for me, totally shocking paper, experimental test of local observer independence. And in this moment, I decided, okay, this enough is enough. And of course, this paper is in a way related with the measurement problem, which into which we, let's say, contributed the measurement, quantum measurement theory. We contributed a little bit with Fritz, and as you know, this is the measurement problems is a kind of tension for some between the unitary evolution and measurement process. Okay? And the 1930s solution was that the measurement implies the state update, or if you like, collapse, from Neumann-Lüder's collapse and Bohm was telling us that this is due to interaction with macroscopic instruments that they had to be taken into account. And he was right, but never expressed himself, let's say, to precisely in terms of mathematics. Okay, but but then moved the decoherence theory related with quantum measurements, of which the flag bearer is Wojtek Żurek. But the most beautiful description of decoherence program for quantum theory of measurement, surprisingly, you can find in the textbook by Bohm in 1951. That's a very important moment because Bohm became Bohmian in 1952. He was still a Copenhagen guy, and this is the most beautiful. And environment is a very important. So I skip this transparency, and I will tell you something about Wigner's friends. So everything is about Wigner's friends. The paradox of Frauhinger and Renner is really using the notion of Wigner friends, but it is an extended Wigner friends. I don't know whether it's Wigner's friends or Deutsch friends. So let's say the original Wigner's friend is something like that there is a kind of state of a system which is superposition, and then friend is either +1 or -1 after making an experiment. But friend is closed in a sealed lab. So for the Wigner, the description of the sealed lab seemingly is still, let's say, an entangled state of the friend with the system. Okay, but then Wigner says, Wigner opens, then that's what you can find in the writings of Wigner. So Wigner opens and sees either this or that. And Wigner just checks the result of friend. That's Wigner of Wigner. That's friend of Wigner. Okay, and Deutsch in 1985 introduced a perversive modification in which Wigner performs a measurement on friend's lab. That means entire Wigner with the system and his measurement, the entire friend with system and the measurement device in a basis which is effectively, as we call it in the paper, complementary to the friend's basis. So let's say on this is based the Frauhinger-Renner paradox. And I will not go into this paper. The thing is that they use friends and Wigners. And really Deutsch Wigners. Without Deutsch Wigners, this does not work. And they want to, the paradox is like that there is a inconsistency of conjunction of the following conditions. One is universal validity of quantum theory understood as follows. If Born rule applied to any scale, to some physical, on any scale to some physical system predicts some proposition with probability 1, then an agent can be sure that the proposition holds. Okay? For us, this should be changed, that everything that it's needed to be described by the quantum way must be described in a quantum way. Okay, we would like to, let's say, that's for us universal validity. But let us not challenge this at this moment. Then, conclusions drawn by different agents having the same knowledge of the initial state must be consistent. Okay. And then every measurement has a single outcome. Okay? And we agree, but it depends what do you mean by measurement. Okay, and so the apparent paradox of Frauhinger and Renner is undefined status of measurement by friends. Okay, either this is proper irreversible quantum measurement, in which the coherence is involved, or in principle reversible pre-measurement. Okay. So that's the thing. But the surprise of our paper is that even in the second case, the paradox disappears. That in the first case, the paradox disappears. That's kind of obvious. Okay, and in the paper we apply standard quantum measurement theory with decoherence, which involves an environment. So every measurement system is not a trivial qubit or something like that, but it's coupled to environment, and that's the only way. Let's say you can learn about the results and so on. And environment, of course, by definition, is uncontrollable. And then the paradox disappears. Okay, then we give the paradox the second chance in step 2. We assume that there is no decoherence in friend's lab, so that the friend is really a kind of virtual friend. Okay, and still friends, if you have no decoherence, then there is a superposition. The friend is in superposition, which I showed, and the friend can only, according to quantum mechanics, it can have a hallucination of an outcome. Okay, but then the friend's outcome is erased by this effectively complementary measurement of Wigner, and therefore it is counterfactual. This hallucination of outcome by friends can be confirmed only by Wigner making a confirmatory observation, not complementary. Okay, and that's what is Wigner's friend by Wigner. If it is violated, then the friend has only hallucination. And finally, we give in third three, we give one more chance. We consider counterfactual outcomes. Okay, so we say, okay, let's agree. The hallucination, let's treat as a counterfactual. Okay, it will never be observed, but let us assume that in transitory moment it was a fact, and we show that this is in full contradictions with quantum mechanics, and just to remind you, let's say some. I see that my time is running out. Sorry, I have still 8 minutes. Yes, am I right? Okay, nobody protests, so I assume this. Okay, so let me say something. Remind about quantum measurement theory. So in quantum measurement theory, we kind of agree now that we have a pre-measurement stage in which, let's say, we have an initial system. Okay, in a non-trivial superposition, and then the pre-measurement is an entanglement of the measurement device and perhaps the observer, if you like. But of course, this is a little bit of stretching. But I give still a chance for let's say this a little bit far-reaching picture. So pre-measurement is just a formation of an entanglement of the measuring system, which is the apparatus plus friend, with the measured system. In this case, the measured system has subscript G. Okay, and the thing is that the real then enters the decoherence, and only then we can talk about stable measurement result. Okay, of course, quantum measurement theory never explains why a specific single result happened, but this quantum measurement theory is within quantum mechanics, and quantum mechanics its goal is only to predict the probabilities.
5 minutes, okay.
Yes, and so this is the pre-measurement, and now I would like to say that what really Frauhinger and Renner introduced, they introduced kind of super Wigner, which is an agent who is capable to make measurements in bases containing superposition of the laboratory of the friend in states which are related with two different results of its measurement. So this is the formal way of putting this. Okay, and the proper measurement by friend would involve environment in his lab, and there will be two distinguishable states of entanglement, and the state of the lab after the measurement process will be in such a collision. But of course, if you trace out environment, you see that the state of the laboratory is mixed, and the eigenvalues of the mixed state are alpha squared, alpha modulus squared, and beta modulus squared, which are the probabilities. And this is of course because you cannot do irreversible interaction with the environment, and you cannot control it. Okay? In a way, this is related with Heisenberg count. So if you have already the reduced density matrix of LG, the measurements in this effectively comparative basis by Wigner will give just random results. Okay, so irreversible proper measurements, you cannot formulate in such a case the Fraudinger Renner paradox. The predictions are different, to put it short. Okay. Now, in case of virtual friends, who do not have an environment, okay, let's say you can form the paradox, right? But the thing is that the virtual friends perform only reversible pre-measurements. So this is the end of the stage of the development in the lab of the friend. And in such a case, Super Wigner can perform effectively because there is no environment in Friend's lab, can perform an effectively complementary measurement, which, for example, has some states. But this completely eradicates his possibility for verifying the result. Okay? Because it's a superposition of the heads and tails, okay, the two opposite results. Okay, and this means that the hallucinations of friends are counterfactuals. And then for the counterfactuals, we find a GHZ kind of for those in the step 3, we say, okay, let counterfactuals be acceptable. So, but this can be killed by using a GHZ experiment. GHZ state is a specific state of 3 qubits. We have 3 laboratories with 3 Wigners, 3 local Wigners, and 3 friends in each laboratory, inside of the laboratory. And the thing is that we ask friends to measure in basis, which is complementary to the basis defining the GHZ state. And as you know, in the case of qubits, we have 3 complementary bases. Okay, and Wigners measure in still different complementary bases. Okay? And this allows us to formulate a GHZ paradox. I have no time to go through the details, and in which the conclusion is that the hallucinated results of Wigner's friends have imaginary values, whereas they should be plus minus 1. As it is, let's say, we use the kind of Bell, let's say, we ask them effectively to measure Pauli matrices, so the eigenvalues are plus minus 1, and let's say if one tortures those counterfactual results in a GHZ way, it turns out that they are imaginary, which is a kind of symbolic. Okay, nice wording from the past. So the counterfactual outcomes of virtual friends form an internally inconsistent notions. They do not exist even in theory. That's our conclusion. And what is very important, of course, this has some ramifications, very strong ramifications concerning Fraudinger-Renner paradox. But what is very important, our results also have to be now taken into account if one analyzes so-called relational interpretation of quantum mechanics of Rovelli. That's, if one reads this, one sees that they have bearings to that, but we did not write anything specific. Anything specific about that. And finally, let me end with some pedagogical implications. I think the following, and these are Marcin Markiewicz, these are my, Marcin perhaps would disagree, but I hoped he does. The role of the decoherence must be a part of any university role lecture on quantum mechanics. It's not taught. Advanced students, master and even doctoral, must be warned that many researchers working in the foundations of quantum theory do not believe in quantum mechanics as it is. And now, more pragmatic. If you formulate a paradoxical statement on quantum prediction, first check whether it holds within quantum measurement theory. And finally, to all of us, that one must work toward more precise quantum language. For example, I think the word observable is okay, but state of the system is definitely a misnomer, and it is causing a lot of trouble.
Okay.
Thank you
Thank you very much. Questions or remarks from the auditorium? If no, the last
Is it
talk
okay
of...
to ask online question?
Yeah, please.
Right. Paweł Chorodecki from Gdańsk. Quick question to the first part of the talk.
Yes.
This measurement that uses photon resolution detector, you have two settings, and normal in Bell experiment, these two measurements should be fully complementary. What is the degree of complementarity in optimal settings in your experiment?
That's a very nice question. This is really tricky. This is really tricky because, let's say, from the point of view of the initial state, you have here POVMs.
Exactly.
Okay. And so it's really very, let's say at this moment, I think, let's say we, in a version in a preliminary version of the paper, we had a discussion of the fact of those POVMs and to what extent they are complementary. But of course, they are complementary. Okay, that's obvious. And the situation is absolutely complementary. Okay, but not maximally complementary. Okay, it's absolutely not. It's definitely complementary because in one case you measure just photon click, and then you measure the interference of this photon. So you measure a click after an interference of photon with the local oscillator. Okay, so there is this wave aspect. So there is another funny thing that you can even interpret that in this Bell experiment you never have the same state, because in the off situations you have just the single photon, okay, but in the on situations you have the local oscillator photons and the single photon, okay. But of course POVM picture gives let's say a unified view with alternative POVMs. So
if I may interrupt, have you estimated the maximal Bell value that you can achieve with such?
Yes, and there is a lovely thing, and if
slightly
I may...
out of time.
Okay.
So I propose to waive the discussion, and the next speaker of our session is Professor Białynicki-Birula. So let us thank the speaker again.
Thank you very much.
Microphone. I am grateful to Krzysztof Pachucki, who allowed me to change my previous decision just to talk about history. But when I saw my colleagues speaking about real physics, I decided that I should not really restrict myself to my historical talk, but I will now talk about something which might be related to physics. Whether it is or not, you have to judge by yourself. So the theme is time crystals. This is a fashionable topic nowadays, and oops. Aha, nie włączył. O, dziękuję bardzo. But we decided recently to contribute something to this new subject, and this is about time crystals in an environment that looks rather peculiar. The environment is electron-positron pairs coupled to the electromagnetic field. So the idea in physical terms is quite simple. We have electron-positron pairs. Of course, they annihilate, and when they annihilate, they produce electromagnetic field. But when we have electromagnetic field, the electromagnetic field can create electron-positron pairs. So this is how it works. But of course, one must now use some theoretical tools to put this to a test. So how this is done, you will see in a moment. As I said, this is the main message. And now, to prove that time crystals are fashionable, even in Poland, we have a strong group. Krzysztof Sacha, Jakub Zakrzewski, who are working in this field. And Krzysztof Sacha even wrote a book about time crystals. But the topic that I will discuss is not covered in this book. Well, what are time crystals? According to the definition that I took from the review paper, time crystals are time-periodic self-organized structures postulated by Frank Wilczek in 1920. Well, now about the tools. We have to somehow use the existing tools, that is QED to start with, to describe such processes as pair creation, pair annihilation, electromagnetic interactions. But of course, to involve the full mechanism of quantum electrodynamics to treat this problem would be an impossible task, because this is not a particle problem, but this is the problem of a whole system, which is even difficult to somehow put into formulas. However, there is a tool that we developed some time ago, which is the Wigner function. I will explain this in a moment. But before that, I just summarize what I said before, that we have this system, and it should be in a self-consistent way generate these time-periodic structures. And the tool is the Wigner function. Well, the Wigner function in quantum electrodynamics is a bit more sophisticated, but it is based on the same idea. This is the Wigner function of the electromagnetic field. I go back because I pressed the wrong button. Here is the this is rather sophisticated tool. Somehow okay, this is where I started to talk about the Wigner function. And in ordinary quantum mechanics, the Wigner function is a Fourier transform of a bilinear combination of the wave function and the complex conjugate wave function as defined here in this formula. Now, the Wigner function is some kind of a substitute for the ordinary distribution function in phase space. But of course, quantum mechanics is not classical theory. Therefore, it does not work all the way. The Wigner function is not positive definite as the distribution function should be. However, it reproduces very well the averages of quantum mechanical quantities.
Of some quantum physical quantity.
All quantum physical quantities if you do it right. And doing it right means that you have to order your operators properly, and we know this, how to do it. Okay, so I go back some 30 years when in a paper with Johann Rafalski and Paweł Górnicki, who unfortunately left physics and is now a businessman in producing tiles. We wrote this paper to show that one can extend the notion of Wigner function to quantum field theory. And this is how it goes. Instead of taking wave functions, I take the genuine field operators. The field operators now are psi. And these are Dirac field operators that obey the Dirac equation in electromagnetic field. Now, to make this into a function, I have to take the expectation value of this operator. The product of two field operators is still an operator, and to make it into a function, I take an expectation value. And therefore, this object now, W alpha beta, is an object which describes the properties of this state, because the operators are just operators that do not know anything about the state of the system.
But that's not the commutator what is here?
Yes, this is a commutator just to make it more symmetric. In technical terms, the commutator excludes the unnecessary contribution from the vacuum. Commutator, not anti-commutator. Anti-commutator would make it trivial. That would be just a function, not a delta function. Notice that this is time dependent, of course.
And A is not the operator?
A, as I said, I should now explain it. At the beginning, A would be an operator, but now I make the essential assumption to make it possible to proceed. Namely, I will now consider the electromagnetic field as a mean field, as some kind of an average, a classical mean field. So the physical content of this formula is the following. I take a solution of the Dirac equation for the field operator in a given electromagnetic field. So this function W alpha beta depends on the electromagnetic field, not only on the state of the system. And with this definition, I proceed, and this is fairly complicated. The Dirac spinner has 4 components. When I have 2 Dirac spinners, I have 16 components. But this matrix is Hermitian, therefore I can reduce this to 16 real functions. So that we are talking about 16 real functions, and of course to solve this in any feasible way would be impossible, but now come the essential assumption. I assume that magnetic field is absent and the electric field points just in one direction, and it is only a function of time. When I make these assumptions, these are not approximations, but I am just looking for solutions with such a property of the electromagnetic field. So this is not an approximation, but just a restriction of my function to a certain simple... Wait a moment, it will be here in a second. It is uniform in space and depends only on time. So I'm talking about local properties of this object. So equations are horrible in general, but with these assumptions, these are the equations that we derived in this paper. They are non-local, they are non-linear, etc., and there are many of them. So now we proceed, and the assumptions allow for great simplifications. Non-local terms disappear because of the assumption of homogeneity, and we can take 4 equations that decouple completely from the rest. Again, this is not an approximation, but it happens so that when these assumptions are made, 4 equations stand out separately. And then it turns out that not only these equations separate, but they contain the important characteristics of my system, namely the number of pairs and the current which is produced by these pairs. So the further simplification, I will not go into it. There is a famous method of characteristics that can be found in books on partial differential equations that explain this method. And lo and behold, suddenly these equations become ordinary differential equations for the following functions. We have f, which is the number of pairs. We have g, which is the current. And we have h, which does not have a simple explanation. It's one of the components of the Wigner function for the Dirac field. Then we have the electromagnetic potential, which of course, when taken the derivative, produces the electric field. And the electric field is coupled to the current. So we have a self-consistent system of equations. Now you can forget all this mumbo-jumbo that I said, because these equations are quite interesting. So you may start from these equations, because I love these equations for several reasons. First, they do have something to do with the starting point. However, they have properties that you would not expect of such a simple set of equations. No analytic solutions are known, because such equations, similar equations, are known very well in the theory of chaos. Lorentz equations for the butterfly effect, and related Rissler and on Heil's equations have the same structure. And the structure is that on the left-hand side, you have the time derivative, and on the right-hand side, you have linear and quadratic terms. Quite simple, but as Lorentz noticed, his equations are even simpler because he had 3 equations, not 5, that they have profound chaotic properties. This is how this business of chaos really started in modern times, because before we had Poincaré, who felt that there is something interesting, but he did not have a computer. So he didn't go too far. So these are the equations. If anybody has some experience with such equations, I recommend studying these equations and show that they are interesting. So
you know they present strange attractor?
Beg pardon?
Do you know there exists a strange attractor as a solution to these equations?
Yes, I will show you right now. Well, this system of 5 nonlinear equations has two constants. The energy, well, in the original equations that I have shown in our 30 years old paper, the energy was well defined as the energy of the electromagnetic field and the energy of the Dirac particles. But now they are reduced to these simple cases. Still, you see some remnants. You see the energy of the electromagnetic field, which is the electric field squared. And then you have contributions from these pairs. And there is the norm, which is preserved also. Of course, this does not guarantee the presence of these extra constants of motion, that there are no runaways. Most of the solutions are runaway solutions because you can have the electric field going to infinity and the potential going to infinity, so that the energy is still constant, but the solution diverges. And now, there is an interesting mechanical counterpart of this. Just by calling these variables different names, you notice that the whole system can be considered as kind of a kicked top. And kicked top, of course, is one of the main tools of the chaos theory. So this is the kicked top, how it works. I renamed these variables, and now I have a nice canonical system with the Poisson brackets, the Poisson bracket between the potential and the electric field, as you might expect, is 1 because these are canonically conjugate variables, and these f, g, and h functions turn out to be components of the angular momentum. What does that mean? If I impose the commutation rules, the Poisson bracket relations between these components, f, g, and h, calling them mi now, then the equations of motion become the standard canonical equation. The derivative of any function f is the Poisson bracket of f with the Hamiltonian. And the Hamiltonian is what I call the energy before. So the Hamiltonian is written here, and the association is quite simple. Electric field is called the momentum. The minus the potential is called the position. And just by dividing by 2, I have the right formula for the Poisson bracket. So these equations are in a way even nicer than those equations that were invented by Lorentz and others, because they do not have such a nice canonical structure. So now we come to the most interesting part of this, to the solutions of these equations. As I said, I have no analytic solutions. However, I do have a computer, so I can look for solutions of ordinary differential equations, and this is just something which even the small laptop can handle. Well, if you take just any initial conditions, then this is what you get. The current and the number of pairs are chaotic in a way, and this may be where the chaos is sitting. However, by fine-tuning the initial conditions, that takes some patience, you have to look and test, you get the following structure. Here is the number of pairs. The number of pairs is this small amplitude, and you have the current. And you see, of course, that when the number of pairs increases, the current also increases, etc. There are two periods. One period is this fast oscillation. And when you look at the numbers, these fast oscillations are connected with Zitterbewegung. What is Zitterbewegung? Zitterbewegung is something which many physicists still don't understand what it means. This is simply the fact that Dirac equation that has the Zitterbewegung built into it, it was even noticed by Dirac at first, is not a single particle equation. It describes the combination of electrons and positrons. So when you have the combination of electrons and positrons described by a function, then in addition to the energy of an electron, you have now the energy of the pairs. And the energy of the pairs is roughly, in the non-relativistic approximation, twice the energy of the electron. And Zitterbewegung is indeed the frequency which is about twice the energy of the particle here. So these are fast oscillations. However, there is something which you will see on the next slide very well. You get a periodic solution. Even these tiny, tiny details are reproduced. And of course, you can run computer and see what happens if you do it for a longer time. This is what you get. A periodic structure in time that now describes, you can see these dark curves, that they are not resolved, but they reproduce the number of pairs, which fluctuates also. And again, of course, as I mentioned before, you have fast oscillations and slow envelope of these oscillations. There probably exists some formula for the period, but I could not discover it. But now this is what I call the time crystal of electron-positron pairs coupled in a self-consistent way to the mean field, mean electromagnetic field. Many other nice solutions can be found, and they are in our paper. I will not talk because I should not talk for too long. And I come to the conclusions that the QED vacuum populated by electron-positron pairs coupled in a self-consistent way to the electric field exhibits periodic time evolution. Now, you may say that my approximations were really too strong, but anyhow, what I can say for sure, that the equations, ordinary differential equation, which we derived with my wife, do exhibit such interesting solutions. And whether this is true for the real QED with quantized electromagnetic field, we do not know. Maybe this will destroy me, maybe it will enhance. There is no way that I know how to really attack such a problem, but at least this model, when you come to these equations, is well defined mathematically. I have ordinary differential equations, I solve them, and they have properties that seem to be quite interesting. Thank you very much.
So the theoretical part was to write down those equations, and the remaining part was experimental, yeah?
Yes, fully experimental, by trial and error. I look at these equations, and there is no God's way to find which solutions are interesting. This is a of course, solutions can be labeled by the initial conditions, of course. And then you have a 5-dimensional space of initial conditions. And to find those places,
it's not easy.
Not easy
to find something in 5 dimensions.
But
sometimes it is not easy to find even in 2 dimensions. But
that's right. But now we have 5 dimensions, and by trial and error, these solutions were discovered. Many more solutions in this paper, which I mentioned. There were slightly different situations. For example, an interesting situation is that you have a doubling, namely these structures, before they become periodic, they have their complement, which is somewhat different, but the pair then repeats itself. So such solutions also exist, and I'm sure that there are many others, but to find all of them is not possible.
Thank you very much. More questions or remarks? Go ahead, Mark.
Those initial conditions which lead to time crystals, do they have some specific properties?
I don't know.
Except that they lead to
the only specific property that they have is that they produce.
No, that's right. A priori. No.
No. I don't see any. It was even kind of a miracle, probably partly due to pandemic, that I had time to search for interesting solutions of these equations. And the equations, I think, are even more interesting than the whole introduction, because they, in my belief, carry a lot of interesting features that probably could be found by some more sophisticated methods, like those which are connected with chaotic behavior.
More questions or remarks?
I have a question. Are they really periodic, in a sense that you said you fine-tune the parameters to find this oscillatory behavior, but I can imagine if you are just wrong by a little, then they decay at some point in time, or you can really take they are really periodic.
So you doubt the periodicity?
I don't know. You only show like couple.
1 kilometer farther.
Yeah, you only showed like couple of periods, and like you said, you fine-tune the parameters, and whether we are sure that they are periodic.
Well, I cannot prove it.
Yeah, sure.
But when I repeat this calculation more and more, and I see the same structure within the, well, how I check this, let me tell you, because that might be a clue how I did it. I took one frame, and then I found the period, and I plotted in our paper the superimposed structures, and they were always within the line width. So whether this is a proof, of course not, but to me, why they should not be periodic?
There is no proof, but there is experimental evidence.
Yes, absolutely.
Yeah. Okay, go ahead.
I mean, this is a five-dimensional Hamiltonian system, and even has another constant of motion, if I understand well. Two constant of motion. So, according to, let's say, theory of Kolmogorov-Arnold, if the chaos is not fully developed, there are islands of periodic orbits, yes, and they have some volume in the phase space. So even these guys that Professor found are probably stable even within this volume. If you change very little the
the initial conditions, there will be still periodicity.
Yes,
I don't know. I imagine that it could be like that.
This is why I advocated that some people who really are experts in this particular field may try to look at these equations and, as you mentioned, to analyze them with better tools.
Okay,
that's a question from Daniel.
I mean, since there are 5 dimensions really, and you have 2 constants of motion, then really you have a 3-dimensional system.
Yes.
So this is actually the lowest that you can have for a continuous system. I mean, the lowest number of dimensions for which in a continuous dynamical system
Yes.
you may have chaos. So
Yeah.
I mean, I don't think that the Hamiltonian structure here, is preserved not in 3 dimensions. I mean, nevertheless, you may still have periodic solutions fully. What I thought you might try would be a periodic ansatz. I mean, maybe this will simplify the equations.
I tried, but I have not succeeded.
Excuse me, I propose to postpone the further discussion to the coffee break, which becomes shorter and shorter, and we meet again at 5 o'clock, yeah? Okay.
Tak? Nie wiem. No rozumiem. Tak, no ten tytuł jakiś taki był modyfikowany. Nie jest najzręczniejszy może, ale już go teraz nie będę zmieniał. To jest ta pana, tak? A2, nie, ten, który był tutaj wykorzystywany poprzednio, to zdawało mi się, że leżał tu. Chciałem zobaczyć po prostu, bo nie wiem, czy mi bateria nie pada. Ale jakbyśmy mogli ten laser zobaczyć, bo nie wiem. Znaczy, chciałbym coś od lasera po prostu, bo nie wiem po prostu jak stoję z bateriami po prostu. Nie wiem, to jest chyba bardziej widoczne, nie? Ten czerwony, dobra, to chyba to w takim razie weźmy panel, już to tak jest, tak robię. Nie będę tu eksperymentował, widziałem, że to wszystko. Lech. Ja widziałem, pojawił się w przerwie. Cześć. Też się witaliśmy. Zostajesz jeszcze po tej sesji?
Dobrze. Już, tylko czekam aż wszyscy wyjdą. No. Zapraszamy, you are welcome. We want to close doors. Of course.
Musimy odbierać okno. Musimy odbierać okno.
Nie. Okay, ladies and gentlemen, it's a great pleasure to open the next session. The title is Beyond Physics, and this is a fascinating topic. Stories where physics proves its universality as a philosophy of science or general approach, which turns out to be useful, crucial, effective in many other areas of gaining and interpreting knowledge which are not typically associated with the mainstream physics, and definitely not in the current evaluation process. So, our first speaker is Daniel Wójcik, Professor Daniel Wójcik, and we are going to learn what can be and what we cannot see in the brain with extracellular recordings of electric potential. The floor is yours.
Thank you very much. It's a great pleasure and great honor for me to be here. Center has been very prominent in my life. I thought originally I might just give the anecdotes. I could do this probably for half an hour, but Krzysztof forbade this, so I will speak about science. But since this is a very special session, I thought I should say something. Maybe just by way of a comment, you know, I am a graduate of physics. I'm a professor of biology. I am now in the Faculty of Management and Social Communication. I think I'm a paradigmatic example of the Peters principle that, you know, the human raises to the level of its maximum incompetence. I mean, so I guess if I wanted to beat this, then there is still government, but I mean, I have no plans for now. So I decided just to show one artifact and just go through a few comments. So I just wonder how many of you know what is this and what is the relation of this thing is this, of this magazine with the center. Does anybody know, how many people in the audience know the relation of this to center? Oh, good. So this is 1997, so maybe I should say I started my working on my PhD in the Center for Theoretical Physics in 1996. I was still not very certain that was a good idea. I had offers from Institute of Mathematics and from University of Vienna, but Professor Białynicki-Birula invited 3 of us students from the University of Warsaw, and he convinced us to join the center. And a year later, there was an article in this magazine. It has nothing to do with this. I don't even know how to translate it into English. Political balls, or the benefits of the Polish advance. It's nothing to do with this. Well, there was an article called a brain race. Okay, some of you might remember this. You might know these guys. So in 1997, it was the beginning of the scientometrics, and I think that's one of the first popular articles on this time, written by Professor Andrzej Pilz. So let's start with this picture. So you can see some of the people who are here in the audience. You can see also me basking in the glory of the best, and which also shows I knew how to stand for a picture. Interestingly, it says this is the seminar in the Center for Theoretical Physics, and the third person from the left is Professor Iwo Białynicki-Birula. So I think if anybody knows Professor Białynicki-Birula, then they don't even read the signature. If somebody from general public paid attention, then they think that you are hiding our director. It's, I don't know, protection of privacy or whatever. So I just wanted to read these few lines, what they wrote about the center. So the best of the best. In the Center for Theoretical Physics, Polish Academy of Sciences in Warsaw, which was ranked #1 in the ranking of scientific institutions, 11 people are employed. I think actually they counted only people with PhDs at the time. This includes 5 professors. So you could see that there were 4 professors in the picture. 4 professors. So Professor Turski, for some reason which I don't remember, wasn't able to be there on this date. The institution was created in 1980, and as its creators say, it has never been, it never caught this disease of sudden growth, which was so common in previous decades, where the scientific institutions were growing tremendously. So I'm just showing this, you know, in the present context of what the center is today. We started late after this boom happened. The creators of the center, in particular its director, Professor Iwo Białynicki-Birula, tried to select its employees and to let the new ones know that this is not a permanent job. This is why all the scientists working here did all they could to stay afloat, remembers Professor Żążewski. So I just wanted to bring those few memories. And finally, just as a final recollection from the same article, this is the Premier League. And this is the top 40, so the center is #1, and I have highlighted
8 institutions, and this is Center for Theoretical Physics. This is Institute of Organic Chemistry, Institute of Physical Chemistry, Institute of Physics, Institute of Experimental Biology, that's my institute, Center for High Pressure, Institute of Psychiatry and Neurology, and Center of Oncology, which today is National Institute of Oncology. Do you know why I highlighted those? There you go. There is one institution missing, and that's the International Institute of Molecular and Cell Biology, which was actually created 2 years after this article. And I think it would also make it here. So I think that this shows the strength of our school. And with this, I just wanted to say happy birthday to the center, and I hope that we'll continue this collaboration. And now I move to the science. So I'm going to talk about source reconstruction in the brain. So, I mean, one of the things that I have been interested for a long time is the relation between what goes on in the brain and what we measure, because we do not have direct access to what's going on there. And brain is a physical system, and just like any physical systems, if you want to know what's happening inside, you have to do the measurement. So I think it's actually a topic of today in many ways. So I realize that I'm not so far off, maybe in a way. So there are many techniques which are used in the study of the brain. I will not cover them all. Each of them has different advantages, different disadvantages. So for instance, magnetic resonance imaging has the advantage that it's non-invasive. So you can have a human, he can move the head inside, and without getting inside, you can just see what's happening in the brain. The disadvantage is that it works at relatively large temporal scales and large spatial scales, but again, it's non-invasive. What I'm going to focus is something which is called field potentials. So this is the electric potential, which is recorded with electrodes, which are typically placed somewhere deep inside the brain. And the question is, what can we find out about what's happening there? So let's imagine that we have some brain, and we just take some electrodes and we stuck it somewhere in the brain. Then depending on what's happening with the animal, how we manipulate it, we may record different signal. Here is an example of free-varying electric potential in the hippocampus, which is one of the brain structures. This is a rat model of schizophrenia. So it's a rat which gets ketamine, and it is known that in humans, the ketamine gives hallucination and induces some states which are related to schizophrenia. This is so-called evoked potential. So this is an average response in this place in the rat barrel cortex, response to whisker flicks. So you can see these potentials are very different. And a general question we have is, we have had this 10 or 20 or 50 electrodes, and you would like to know what's going on in the head of the animal. And you might ask this question in the case of human, and I will go to that in a minute. So where does this electric potential come from? So the brain, the cellular membrane is a bilipid layer which does not allow the ions to pass through. But within this layer, we have ion channels which are embedded, which are like small tubes which allow the ions to pass through. They are in fact non-linear, so the probability to cross the membrane is a function of the potential. There are also other more complicated mechanisms. But what's happening when you have a cell which is active is you have this constant motion of the ions, and when they move, so you can think of this as resistors, those ion channels, and this bilipid membrane acts as a capacitor, because when you have the difference in the potentials, then essentially you've got charging of the membrane on both sides. You have this motion of ions in the extracellular space, and from the perspective of a remote electrode, this is seen as transmembrane currents. And the physics of this is relatively simple. We can show that you can ignore magnetic effects over all relevant frequencies up to, say, 20 kilohertz or higher in the tissue. And then the contribution to a potential measure with this extracellular electrodes, again, a piece of wire that I just put somewhere in the brain, is proportional to this current source amplitude, and inversely proportional to the distance from the source to the potential. And instead of the electric constant, you've got conductivity of the tissue. This is, of course, under the assumption that you have infinite space with uniform homogeneous isotropic conductivity. And since we have multiple currents located over the whole cell, and we have multiple cells, we have to add this up over all of those currents, and it's usually convenient to think in terms of some coarse graining. I mean, these currents are often correlated. So you can think of this potential, which is being recorded in such an electrode, as sort of as an integral over the whole space of this current source density, as we call it, weighted by the distances from the source to the electrode. So the basic equations are familiar. This is essentially the Poisson equation, which tells you if you know the potential in the whole space, you can compute the current source density. And on the other hand, again, in the simplified case, when sigma is constant, you can just write this solution. So if you know the current source density, you could compute the potential. And if the sigma is non-trivial, then you have to solve this, and we do this using finite element models. So why do I bother with those two quantities? I mean, the point is that the current source density is actually local. So if you see that something happens here in the picture of CSD, you know that the phenomenon is really here. On the other hand, the potential is long range, and I will show exactly what this, or more precisely what it means in a minute, but it's accessible experimentally. Okay, so potential is something you can measure, but CSD is something which is easier to interpret, and that's why you would like to have this. So I like to have some specific picture in mind. I show this every time. This is the first experiment with which I got involved. So you have a rat, and the rat is awake, but it cannot move. It's being brought to the lab every day, and then for half an hour you just flick its whiskers. Okay, so at the beginning the animal gets a little, irritated, worried, what's happening to me, and then it just gets used that that's the new way of life, and then essentially it's just lying there. But the whole brain, the whole system works otherwise. And you can see that there are some electrodes implanted in here. So there are electrodes in two structures, in the cortex and in the thalamus, which play a role in information processing of these signals. So what we believe is being recorded is some sort of information about the mechanics of the information processes in those structures. And then once we have enough information about its mechanics, the animal is getting a small electric shock on the ear just to awake it. And the idea is that this might sort of force the animal to reevaluate what's happening in the external world. What is the change of the sensory information? And the question is, can you see the difference? So those are the structures. I will not go through them. Essentially, information goes from the whiskers through some trigeminal brainstem nuclei to this thalamus. There are two so-called nuclei in the thalamus, and it goes to the cortex and it goes back. It's some non-trivial system, but it's not so important. What matters is that we will have electrodes in these structures and here. So here is the comparison of the cortex in the cortex at the top and in the thalamus at the bottom. On the left, we have animal which is sort of bored and it's aroused on the right. And when you compare them, I mean, you can see that there's basically no difference in the cortical signals. And when you look at the thalamus, maybe there is a little bit of difference. But this is a PR picture. So this reminds me like the Hertzsprung-Russell diagram that Professor Demiański used to show. And then he showed he would say that this is the PR version and this is the real version, okay? So I mean, before I showed you the averages, and these are the real signals. So here, actually, you can see that there is some response in the cortex, but in the thalamus, it's actually difficult to even see that there is a response. And the reason is that the field which is generated in the cortex, it comes from so-called pyramidal cells, which are very elongated, so they are very strong dipoles. And while the cells in the thalamus look like this, I mean, this is a picture from microscopy, which shows the pictures in the thalamus. So they generate so-called closed fields. It's like multiple dipoles surrounding the cell body. So this field decays much faster. So that's why this signal is much weaker. Okay, and so since there were no significant differences between those two cases, our colleagues decided to look into more detail into this rat's brain just to map the field in a substantial part of the forebrain. So they made these experiments where part of the skull was removed, and then they measured the potential on a grid of 4 × 5 × 7 electrodes, so 140 places. And here is just the simultaneous recordings so from those 16 places, which are marked here on this picture from the rat brain atlas. So the highlighted pictures are the ones which are showed here. Now, what matters is not obviously the specifics of what is shown in this picture. What matters is that we see those peaks which are strongly correlated over individual electrodes and the troughs which come from electrode to electrode. And now you have to understand that the difference between the neighboring electrodes is 0.7 millimeters. So going from top to the bottom, it's on the order of 6.0.7, so it's about 4 millimeters. So this is as far as it goes in the rat's brain. So this means that this electric potential is correlated strongly over very large distances. If you think about the EEG, which is being used in common clinical and cognitive studies, it's even worse because you are even more remote from the sources, and the correlations are even stronger and the signals even weaker. So, okay, what's going on? I mean, this is the crucial picture to me. So, think about it like this. I mean, we have this stone which was thrown into this pond, okay? This is the source you would like to get. And the situation we have is this, that we have a few buoys here, which are moving up and down. So just imagine we have those 10 buoys, and from this we want to find out where was the stone, okay? This is the simplified picture, because in fact, like I said, in the brain we have, say, on the order of 100 electrodes, but we have 10 to 11 cells, and each of the cells has, in the order of, millions of ion channels, each of which is doing different things, okay? Of course, they are also, they are not uncorrelated, but the point is we do not know what are those correlations. So again, this is our, sorry about this artifact, this is our game. We want to find out the stone from the motion of these buoys. And the real motivation for me these days is this situation. So when you look into epileptic patients, there's a substantial percentage of them who have pharmacoresistant epilepsy, which means that, you know that in many cases in epilepsy you can treat people with different drugs, but I don't remember the numbers. I think it's on the order of 15 to 20% of people for whom the drugs do not work. So the only way to help them is to actually remove part of the brain tissue. And if you decide to do this, then there's a preference on the part of the surgeon and of the patients typically to remove the part which needs to be removed and leave the rest. And the question is, where do you cut? So obviously, the doctors have lots of experience, and in many cases there are good indications where to cut, but sometimes it's not so obvious. And what we see here, those are two pictures from actual patients, from actual clinical cases. This is a case from hospital in Nancy in France. Those are data from Johns Hopkins University, which I'll be using later on in my presentation. So what we see here, those are so-called strip electrodes, which are those are the ECOG electrodes which are placed on the external part of the brain. And there are some depth electrodes, which I guess are shown here. We see them here. So one of my students called them kebab sticks, so you can imagine. So in this case, to put, okay, so I've always thought that those strip electrodes are sort of less invasive, okay, because they are on the outside of the brain. In fact, the doctors tell me they are much more invasive. The reason is that to put such an electrode, you have to remove substantial part of the skull, remove the dura, and then you just, stick this tape and then you close it. Now to insert this electrode, you just have to drill a small hole and then you just put this kebab stick. Now, terrible as this may sound, actually, we do not have pain cells within the brain. So if you have the stick inside the brain, it's not painful. What is painful is when you go through the scalp. So you want to have as little distraction to the scalp as possible. Anyway, so we would like to, sort of from this type of recordings, we would like to tell the people, what's going on there, like where is the epileptic source. And then, this leads to a number of questions, like for instance, with what precision can you tell, where things happen? Would it help you if you have an extra electrode? If you do, how would you place it? So, those are the kind of questions that I would like to be able to address. Today I'll focus just on the basics of one method that we have developed actually 9 years ago. We have some latest advancements which were published just a few months ago, which I hope to get to them. Something which we call traditional CSD method was proposed by Walter Pitts in 1952. It's the same Pitts from Pitts-McCulloch neuron that Maciek Levenstein mentioned yesterday. He was obviously a genius. It's actually I mean, he was ahead of time in many respects. I mean, I will not go into that. I mean, it's sobering when you think that in my age he was already 3 years dead. Anyway, so there was actually not much advancement since 1952 until beginning of the 21st century, where our colleagues proposed what they called inverse current source density method, and we came up with this kernel CSD method in 2012, and I'll show it. So this traditional CSD is essentially taking the Poisson equation at face and approximating with a numerical second derivative formula, which has some problems. I'll be running because I see my time is running. I'm talking slowly. So one of the problems we have with this is that you cannot compute the approximation to the gradient at the edges. So if you have 20 electrodes, you would lose 10% of your data. In our case of 140 electrodes, if we could do the computations only inside, you would have to go from 4 times 5 times 7 to 2 times 3 times 5, so from 140 to 30. So you have to start with throwing away 70% of our data. So, I mean, if you spend 12 to 14 hours per one data set of continuous recording, then you do not want to do this kind of things. So we use this inverse current source density. Here the idea is that you assume you have an n parameter model of this current source density, for instance, interpolated on a grid. You just plug it in the equations, you compute the parameters, and this gives you an estimation of the sources. But again, you can see the problem is that it's not so easy to interpolate the field when you have non-trivial distribution of the electrodes. So we propose this kernel current source density. So the idea is this again. Imagine we have this, say, distribution of electrodes. Here they are shown regularly, but let's imagine they are arbitrary. And so we know the electrode positions, and we know what were the values of the potential measured in this at these electrodes. So what we do is we want to somehow, in an intelligent way, interpolate or extrapolate this potential beyond the measurements, and then compute the CSD from Laplace equation. So the idea is this: we propose a range of what we call basis sources. So we just take, say, a little Gaussian and we place it somewhere, and we compute what is the potential that it generates. And again, this is completely general in the sense that we can do it in an infinite space with constant conductivity, but we can take also actual model of the brain, so the finite element model with different conductivity of scalp and the brain, and do the computation sort of numerically. What matters is we have this relation between those basis sources in the CSD space and the potential space. And we take another one, and we take many of them, and then we ask the question, okay, so if we have those values of the potential at these electrodes, how do we take this linear combination of those guys so that it fits as well as possible to those measurements? Okay, that's the idea. And of course, the problem is that, say, if you have, say, 10,000 such basis sources and you have 10 measurements, then you have a problem because you want to estimate 10,000 parameters from 10 numbers. That is not good. So there's a trick, and the trick is to use a kernel. This is a notion from reproducible kernel Hilbert space theory, which was actually proposed by Aaron Schein, which was a Polish Jewish mathematician working at Berkeley at the time. I forgot his first name. The idea is this: you take those basis functions from the potential space, you add up the products of them with themselves. So this looks like a weird object, but you can see that any linear combination of those guys, of the basis functions, which we have here, can be written as a linear combination of those guys if I fill those x's with some numbers. Because then this bi of x becomes a number, and again, this gives me just another linear combination of the basis functions. It's a question of, can we show the equivalence in both sides? But yes, you can. So basically you have two representations, either linear combination of basis functions or linear combinations of those kernels with one leg fixed. Now what you want to do is you want to minimize the error of prediction between what you measured and what you postulate. If you want to avoid overfitting, you might add the regularization term. The question is to find the value of the potential which minimizes this functional. And there is a representative theorem which is really the reason why we want to use this kernel function. It says the following: if you introduce this notion, then there exists betas, there is one of the, there are many minimizers, but in particular there is one which is linear combination of those kernel functions with legs fixed at the places where you had the electrodes, with as many parameters as you had the measurements. So the crucial thing to pay attention here is this, that here this capital M, this is the number of basis sources. So this is large, this can be this 10,000. And this is the number of electrodes, so this can be 10. So basically there is the trick. We say that we are doing the estimation in a 10,000 dimensional space, but in fact we can get away with getting just 10 numbers, then you can do it in a reliable way. It's a trick. I mean, this is one of the many inverse methods, and each of them have to impose some constraints, because the problem of finding the potential in the whole space with just a few measurements, it has infinite number of solutions. I have 5 minutes, right? According to my clock. Okay. Right, so I'll be just rushing through this. I mean, you can solve this, and you have to invert the square matrix. It's not really so important. I mean, I know it's not. I mean, I could explain all of this. I wanted to show that I, still use equations, even if sparingly in my job at Nensky. What matters is that we can find the estimation of this current source density from the set of potentials measured, calculating inverse of some matrix, and then change into the space of current source densities. We can do this with regularization, which I run through. And let me just show how it works. So imagine we have a piece of tissue, and we want to reconstruct it with the measurement of a potential at a single electrode. It's a guessed potential. This is a reconstructed CSD. It's not very much like the original, but obviously this was just one electrode. But if I keep on adding electrodes, you can see that we started recovering what was there. And again, the question is, okay, can you understand what happened? How did you move away from those 10,000 dimensions to these 10 dimensions? Well, what you can see is that this K matrix, it's a product of matrix B, which are essentially the basis functions sampled in all those places where we had the electrodes. So this is a square positively defined matrix which can be diagonalized. So if you diagonalize it, then plug it into this formula for the current source density estimation, it turns out that any CSD you can reconstruct is a linear combination of those guys, which I call eigensources. So basically, for any distribution of electrons, there is a set of well-defined sort of n solutions, which are all that you can see. So essentially, this answers my question. I mean, if I have this patient and he has, those 5 electrodes which are placed by the surgeons because of, you cannot place them arbitrarily because you've got veins in the brain, you don't want to break them, etc., etc. You have some indications where to place them. So for this specific setup, I can compute what he can see. Okay, so imagine it's like you want to have binoculars and you want to see something, and he will tell you, you can have the binoculars, but they will have very non-trivial optics, will be constructed in a very specific ways, and you're going to be able to see something which is equivalent to, say, 10-dimensional space. But know exactly what the space is. Okay, and if the electrodes are regular, you can see that this looks very much like Fourier. It's not really Fourier because sort of the measurements are in a different space than when you do reconstruction. You can do this in 2D, but you can also do this in this case of less trivial electrodes. And here is just the distribution of the electrodes that we use in this case. We sort of span the space of solutions around this. It sort of constructs like the convex hull of this guy. We do not have yet the full mesh model of the brain. We use the so-called 4-sphere head model, which contains the models for the, it's like a spherical brain. Okay? I'm a physicist, I'm allowed to do this. And here is just the solution. This is the ground truth. That's what you'd like to see. Those are estimations with the old method, and this is with the new method. I'm not sort of going into the details since I have sort of expected I'll have much more time. And well, we can show this in the brain. And maybe I'll finish with the thanking the people who are involved, in particular Szymon Łeski, who will be my next speaker, who was critical in this. But I just wanted to say that we are in this moment, we are in touch with colleagues at the neurosurgery clinic in Wrocław who are preparing for the first surgery of patient of this type using the STEP electrodes in Poland. So I mean, so this type of surgery is being done routinely in the west of Europe, in the US, but in Poland, I think it was not performed, and we hope that, I mean, we are working to bring those methods to the clinics. For now, just as a support, but you know, this gives me a little bit of a feeling that I'm contributing something to the society. So it's good. Thanks a lot.
Thank you very much. Time is running, but I guess we still have time for one question. Any questions?
Professor Turski?
Actually, I have a question. These patterns of neural activities in the brain, they have to be somehow related to the flow of blood in the blood cells. And is there any attempt to compare or combine your type of measurements with what we can get from fMRI? I mean, we can, if we finally learn how to interpret the results of fMRI, then we will have much better data about the flow.
Yes, no, I mean, so that is actually the problem of the fMRI. That's what I mentioned, this thing about the time scales. So the fMRI is tremendously slow. I mean, it's, I mean, the so-called Bose signals is actually the coupling of the blood flow with the neural activity. And the relevant time scale is a few seconds from the event to the activity which you see. Now, the activity, the neural activity which you would like to measure is on the order of, say, hundreds of hertz, or a kilohertz. So basically, we're talking about a millisecond to 10 millisecond time scale. So we have a few orders of magnitude lost if you wanted to use MRI. So that's why electrophysiology is actually the best, and that's why the people do this.
And the last, I mean, you're sure that this kind of a surgery treatment is not the new version of lobotomy?
Yes.
It is?
No, I am sure that it is not the same thing.
Okay.
I have to process your question too. I mean, in a way, it is and it isn't. I mean, it is in the sense that you remove piece of the brain, but it isn't because, you know, you try to, you know, keep the human still functioning, you know, and sometimes you actually can succeed. I think, you know, people understand some things better, but there is still a room for improvement. And there's, so I mean, so we actually a month ago we had this meeting with those surgeons from and neurologists from Wrocław, and the head of the team came to me and said, you know, from your seminar, I just realized, you know, how little we know about, you know, what we are doing in this brain.
That's probably correct conclusion.
So I think I'm happy that I'm there.
Given the some sort of mismatch of scales in terms of complication, right? A system of 200 electrodes is a different scale than the brain itself with billions of neurons. So.
Yeah. I mean, I should say that, you know, in the humans, it's a well, they do computer. Well, they do computer tomography, they do magnetic resonance scanning, and they do monitoring of the electrophysiology. They do all of them in different parts of the procedure. And the 200 electrodes I mentioned that you can do for the animals. For humans, if you have like 15, 20 contacts, you're lucky.
Oh yeah, I understand that. Well, if the discussion goes so well, let me ask another question.
Okay.
What about spatial scales?
Right.
I mean, an electrode is a large, very large object as compared to a single neuron, but probably an epileptical malfunction of a brain is not caused by malfunction of a single neuron, but a bunch of them. Do we know how large is this part of the brain which malfunctions, so to speak, when a person has epileptical attack?
It's a good question. There's actually several questions. I mean, so first, I don't know. I know that actually, I mean, epilepsy is sort of a broad notion. It's like, you know, you can, it's not really true, but I hope you'll get my meaning. You can be healthy in one way, but you can be sick in many different ways. I mean, sort of, if you say you want to function well, everything has to function, but, or like, I mean, with a car, right? I mean, if it doesn't matter if you have a broken engine or a broken tire, right? I mean, you cannot go. I mean, of course, there are different levels of how the car can be broken, but I mean, if it's driving, I mean, sort of the basic systems have to function. Regarding, so in the answer in your question is the size of those structures and their placement in the brain can be very different. So there's no unique answer. The second thing is about the size of the electrodes. So the electrodes which are being used for humans are actually quite substantial. I mean, so this notion of kebab sticks is not so much off. I mean, it's really, I mean, this gives you the feeling for the size of the thing. Now, this is actually another exciting field, I mean, the neuroengineering. So for the animals, for instance, for recordings from brain slices, I mean, the latest setups with which I am familiar, I mean, you've got electrodes on the size of, say, 10, 20 micrometers, with inter-electrode distance of, I think, for instance, electrode setups from Andreas Hilleman, they have inter-electrode distance, I think, 40 micrometers. Okay, and the matrix has 14,000 channels, I think. You can sample simultaneously only 500 channels, but you can scan the whole thing. Okay, so think about this. I mean, you've got, say, on the order of 15,000 channels. The Brain Initiative in the US, they have had a broad vision, and one of the visions was to develop systems so you could probe every neuron in our brain. We are far off, but I mean, this is on the table. And people try different things, nanoparticles sensing within the brain. I mean, I don't know how this all could work, but that's one of the targets. People want to be able to probe every individual neuron in the brain. Like I say, right now, tens, 15,000s of channels, this is feasible. But of course, this brings another issue, right? I mean, if you think that you want to sample the system with, say, 10 kilohertz frequency, if you want to get the spikes, and you want to do it for 10,000 channels, well, I mean, you have to, I mean, even issues so trivial as just, saving a file on a disk, I mean, they become a challenge, right? I mean, people don't, I mean, the experimentalists often don't think about this. They say, oh, let's get the system with 10,000 channels. And then they come, oh, it's funny how quickly the disks get filled. Well, yes, it's funny.
Thank you very much once more.
Thank you.
And let me invite the second speaker, Szymon Łeski. Sorry. This distributed representations of discrete objects. You are welcome. Jeszcze mikrofon. Dobrze.
Thank you. First, I wanted to thank the organizers for giving me this opportunity to talk to you. This is the session for people who weren't lucky enough to get jobs in physics. I will say a few words about myself first. So I did my PhD in Center for Theoretical Physics, and that was actually the 25th anniversary. At that time, we had a party at this nice restaurant close to Dworzec Centralny, and I remember that very well because my shoes were too tight and I had to walk barefoot from the restaurant to the train station. And yeah, after that, I worked for quite some time with biologists such as Daniel. And since 5 years, I've been working in industry, in natural language processing, mostly in several companies. I was an engineer for a short time, and then I started leading projects and teams of various sizes. But you don't have to be afraid, I will not be talking about project management. Instead, I would like to tell you a few words about a concept which I find really exciting, which was one of the first concepts I ran across when learning about language processing. And this is a concept how you can take discrete objects such as words, which have no intrinsic distance between them. They are just separate objects for a computer, and you can actually learn representations which have some meaning, in which the words are clustered semantically, let's say. So first I will introduce a short task in natural language processing. This is not a very important task, but I have to work on something. And then I will tell you how you represent words traditionally and how you can do this better. And what is really exciting for me is that these concepts from natural language processing can also be transferred to other domains. So other discrete objects, such as, for example, users in a social network or products in a store, can also be represented in a continuous space where you have notions of distance between the objects, for example. And what's funny for me is these techniques use, these methods use techniques from language processing. So let's get started. This is my my example task, my toy task. It's strictly speaking, it is an example of something called document classification. So you have text documents and you assign them to a class. And this is very simple classification because it's just classification into two classes. We have a, let's say you run a campaign of one of these people for president, and you want to have an automated piece of software which reads tweets on Twitter and tells you if people are tweeting positive stuff or negative stuff about them. That's actually this kind of analysis are done. So you would like to have a piece of software which takes a tweet and tells you if it's positive or negative. And obviously you don't want to write this piece of software line by line because, well, maybe in sentiment classification you could come up with an algorithm how to do it. But you can imagine it's not always such a simple task. So essentially you don't want to invent the algorithm yourself. You want to have a statistical model which will see some training examples. So we will have a bunch of tweets which are positive and a bunch of tweets which are negative. Then you will fit a statistical model to these tweets. And then when a new tweet comes in, you will show it to the model, and the model will tell you if it's more likely to be positive or negative. I'm saying you fit the tweets to a model, but actually the model is just some mathematical function. It doesn't read natural language. It works with numbers. So what actually happens, first you have to take these documents, tweets. So for me, one tweet is one document, and represent them in as numbers. So these are, of course, it will not be, probably it will not be a two-dimensional space, but a space in much higher dimension. But your tweets will become points in this space. Those are positive and negative. Now you take a model which might be a logistic regression or a support vector machine or decision tree or neural network, whatever statistical model, it's not important at this point. And fitting the model means you create some decision boundary based on your training data. And then at test time, you have this new guy here, and it fell on this side of the decision boundary, so this tweet has a positive sentiment. And what I would like to talk about today is exactly how you do this, how you come from a collection of words to a point in a metric space, or to a sequence of numbers. So the simplest way it's been done is you just make a list of all possible words. For example, I don't know, 100,000 words in English, and so you have a vector of the size of this vocabulary. So think that it is really long, 100,000 entries, and you encode each word as a vector which has 1 at one coordinate and zeros everywhere else. So, for example, this first tweet the words will be represented like this. So each word will be what's called the one hot vector. It only has one, and everything else is 0. And then you can, for example, sum it up. This is equivalent to saying that the order of words doesn't matter, which is a very rough assumption, of course, but for some tasks it works. And then you have a representation of your tweet as a collection of 100,000 numbers. Most of them will be zeros, some of them will be ones. And your model will learn how these zeros and ones are connected to the labels of positive and negative sentiment. So in this task, you could actually probably write the model yourself, right? You would have some words which have positive meaning, like great, good, and so on. You would have some words which are negative, like bad, terrible, and you could like add a bit for each positive word and subtract a bit for each negative word and see what the score is. And if you train any reasonable model on such representation, you will end up effectively with something like that. Of course, I'm just showing this as a toy task. A task which if you work in natural language processing, you are more interested would be, for example, translation to a different language, or understanding what the user is asking for. If the user is asking about the weather or is asking to set a timer on his smartphone, this is just the toy task, right? But still, let's see what can go wrong in this approach. So one problem is every word here is a separate object. So it's either 0 or 1, and it's 1 only at one position. So the dot product of every two words is 0. And there is no notion of distance. You can't say what are the most similar words to one given word. And there is no generalization. So if at test time your model sees a word like terrific, and assume this word was not present in the training data, the model has no chance of deciding correctly, right? It's just, okay, it was, is it good or bad? I have no idea. I haven't seen this word. And what's more, you sort of, with this approach, you sort of learn every task from scratch. So you learn that the word good belongs to the positive class, but you have to learn separately. You have no prior knowledge. Starting to learn this task, you just have to learn everything from your training set. And what we would like to have instead is we would like to have a words which are close in meaning are close in our feature space. So you would like to go from this kind of representation with one hot vectors to a representation in a space with much smaller dimension. So think this is 100,000 and this is maybe 300. But you would like it to be so that the words which are close in meaning have close vectors. Yeah, and if you could do that, then this model would generalize. So it would see this word. It was terrific. Okay, it hasn't seen this word in training, but maybe it saw this word. So it will calculate the vector of this tweet, represent it as a vector, and say, okay, this is actually close in space to this, so the decision will be the same. So this is called generalization to unseen data. And this would, of course, be very helpful, but the question is, can you do it? And the framework in which this was obtained was proposed in the 50s. There is this famous quote, "You shall know a word by the company it keeps," which means that the meaning of the word is defined by the context in which this word appears. If you want to be convinced that this is true, please look at these examples here. So I thought of a word and I replaced it with a symbol, and I'm giving you 4 examples of this of sentences with the same word. Can you guess what it is? Tea, coffee. Yeah, exactly. So this is what I mean. You don't know exactly. I thought of coffee, but then I realized tea also fits. But these are words which are close in meaning because they appear in the same context. Of course, I'm cheating a bit here because what we are doing, we're not only looking at the context words, but we are also reasoning, which these models want to do. You know, it could be maybe some food, not necessarily drink, but you're sure it's not a verb, right? It can't be a verb, and it can't be a bicycle, for example. So this is what I mean, like close. What's fun? Such words which can be replaced in context. They can be words of opposite meaning, right? So if the word bad fits in a context, then the word good will probably also fit. But there will be, of course, contexts which separate the meaning of these 2 words. So based on this, you can obtain dense representations of words. And there are essentially 2 ways to do this, which are not really, it's not as clear division as I'm showing, but for the sake of this talk, let's say this. So you can just count which words occur close to each other. You can have this matrix of like this is vocabulary size times vocabulary size, and for each pair of words you have a text corpus, right? That you have to have. You take a book in Polish or in English and count. For example, how many times the word number 1 occurred within 10 words of the word number 2 in your corpus. And you have this matrix, and then you can do, it's huge matrix because the size is vocabulary size, but you can do dimensionality reduction, and you can end up with word vectors, which are smaller in dimension and which cluster semantically. And the second way to do this is prediction-based methods, where you train a neural network in a word prediction task. So essentially, you take, for example, here you take a 5-word piece, you remove the middle word, and you try to. That's exactly this task you were doing here, right? you remove the middle word and you try to predict it based on the context. Or, which is less intuitive, you can take the middle word and try to predict the context, or maybe now it's better to say you try to maximize the likelihood of these words provided the context. So if you're anything like me, then you might be confused looking at this, because with neural networks you need to get used to this mental trick that you sort of say what is the architecture of your task, and then you in this task when you train or fit your neural network, you learn the representation of the words and the computation which leads to prediction at the same time. So this takes some getting used to, but the thing is it works. And if you train word representations using this, and then you take a word poet, for example, and look at the closest words, you get writer, author, composer, novelist. You get the closest words are close in meaning. You have walking here, and you have walk, jumping, sitting, streets, moving, riding, and so on. By the way, I'm showing you what I'm showing you are of course not my results. This is like state of the art from 7-8 years ago. This is how people thought about this 7-8 years ago. There's been some progress since that, but maybe I'll talk that if we have time at the end. So now you have the notion of similarity. You can say, I have a word, and what other words are close in meaning. Which also means the model will generalize, because if you feed a word which is close, then the vector will be close, and the result will be close, we hope. And one more reason it is important is because data in this kind of applications, there are cheap data and expensive data. So expensive data are those where you need a person to put a label on the data. So if you have this training set of tweets and you had to hire someone to mark that this tweet is positive, this is negative, this is expensive. And what is cheap is if you can take just any text, you could run a crawler on your computer and download 50 gigabytes of English text within few days probably, and these data are cheap. And what happens here, if you use word vectors, you use to train word vectors, you just need unstructured text without any labels. Once you train them, they encode a lot of statistical structure of language, and then if you train your actual task, you need much fewer labeled data. So as an example, if I gave this sentiment classification task to you, I would only need to show you one example of positive tweet, one of negative tweet. You would know what to do because you speak the language. This is sort of the same process. So you sort of teach the model to understand the language, and then you need much less data to show what the actual task is. Okay, and this is now standard. So this is all natural language processing works on distributed representations, period. Okay, maybe not all, maybe there are some applications where you can get away with bag of words, but that's standard. And now for the really interesting part, there are other discrete objects which a priori you wouldn't think can be put in a space equipped with a distance. So in natural language processing, these are not only single words, but also sentences, documents, you can have vectors for those. And outside of NLP, you can assign vectors to nodes in a graph, to products in stores, to users, to movies, biological sequences, etc., etc. And I would like to just give you a taste of this. So this is how you can, and the original algorithm for words was called word2vec, words to vectors, and many of these have names such as this. This is doc2vec, document to vector. So now, in addition to predicting the word from context, you also train a representation of the whole document. And then, because what we did before, you could take all words in the document and sum up the representation, take the average or a sum. But you can also do this, and it works better. This is product to vectors. So this was done in Yahoo Mail 5 years ago. The paper was published 5 years ago. The study was done 7 years ago. So what they did, they had receipts the customers received in their email. They could have a sequence of products which one person bought, and they did exactly what was done for the word prediction. So they assumed some vector representation for a product and predicted other products bought by the same customer. So this is sort of basket analysis done on vectors. And this is, so these are 3 products, and these are the closest products with the closest vectors, right? So you can see it works pretty well. Now I like this figure very much because this is from 2018 from Alibaba, the Chinese e-commerce site. And this is learning product embeddings from users' behavior. So someone is browsing the store and he visits product D, A, B, and someone else visits other products. You build a graph of transitions. So if someone is looking at product D, then they are, this is a weighted graph of how a huge number of people browsed their site. And now you do a random walk. You do a random walk on such graph, so you end up with sequences. And the analogy is products are words, and these are sentences. And you apply word2vec as is, with no modification on this, and you get the product embeddings. And this is also on graph, but instead of walking randomly, you have weights which control whether you walk close to where you started or try to go as far as possible. So you probe this random walk probes the graph structure at different scales, and now this is a graph of persons appearing in Les Miserables. So this is there is a connection if they appear in the same scene in the book, in the play, and depending on which embedding you use, then your coloring of the graph is either people who know each other. So these are like those semantic clusters of words, or if you switch to a different mode of exploring this graph, then close embedding will not mean they know each other, but they have the same functional role in the social network. So these are like people who only know one person, right, will have this color, and people who are like connectors between different communities will have this color, right? I'm not going into any details here. I'm just showing you pictures. Okay, so that's it. I would like to end with this quote, which I like very much. And for me, the fact that you can take discrete objects, put them in space, and calculate distance, or you can put, for example, users of Netflix and movies at Netflix in the same space and infer which user which like each movie. There's a bit of magic in this for me. Thank you.
Thank you very much. We have time for some questions. Bożena, please.
This automatic classification of positive and negative opinion seems attractive. On the other hand, what the system would do is an opinion not that bad, because it's positive, but then you see no, and then you see bad.
Okay, so that's a good question. So with the bag of words, you would not do much. What you can do is you can. So if you don't want to go full neural networks on this problem, but want to understand it in simpler ways, what you could do is you could, as your processing unit, use not a word but a sequence of words. So then you could use bigrams, which are two consecutive words. And then if there was a bigram not bad, you would learn from the data that this actually means good, right? So that's one answer. And then for more complex models, they don't throw away the order of words, because and then you can also learn that what this means.
Daniel.
Two questions, really. One question is, how do you handle sarcasm or irony? And the second question is, how does this relate to your work, if you can betray things?
Though these are nice questions. So sarcasm and irony are, of course, there are people who don't handle that well. But actually, there was the paper a few years ago. Well, it's all in statistics of language, right? So if you have some sarcastic language in your training set, then you will learn what that means. For the model, it makes no. No, I have a specific paper in mind where what they did, they crawled Twitter with they looking for tweets with emojis, and then they treated the emoji as a label. So you had some text in the Twitter, and you had emoji as a label, and people use this sarcastically all the time, and you could build a model which suggests an emoji when you write a tweet, and actually it worked really well. So if you wrote, "I love how my train is always late," it would give you different emojis than if you wrote, "I love my wife," for example. So this is possible. Probably you would need a lot of data and not the simplest models. For the second question, so what we are doing at this company, we have a grant from NCBR to work on conversational search of products. So this is actually very relevant, because in the conversational part you use word vectors all the time. In the part where you try to understand the product structure in a store, we work with this kind of vectors. Yeah.
Okay. If there are, there is one question up there.
I have a question about this tweet categorization, because if your ultimate goal is to categorize if the tweet is good or bad, then I don't kind of get it. What's the point of extrapolating what's the meaning of the word that you don't know? says like this also depends on the words that are known in this tweet, so the answer won't change, right? I don't know if you get what
maybe you will correct me if I didn't get it. So the point is, you have your training set, which you collected. Maybe someone labeled 200 tweets for you, and you can't expect this training set to contain every positive and negative word. But then you run your model. So this, you had 200 tweets, and now you run your model online with live Twitter. So people are tweeting all the time, and you have thousands of tweets per hour, and they are not restricted by this vocabulary. So if you come up, if the tweet is like this, there is no other word to, like, you have to know what this word was. Oh. Yeah, but so are you saying that you could just ignore this word? Yeah, you could. I mean, it would just wouldn't decide on this. So maybe it's you depending on how big your set was, you would make some percentage of mistakes. But the point is, you can sort of pre-train word meanings outside of this task. You just take a book in English. Yeah, you do this.
Okay.
Right? You have these word embeddings once for all your tasks, and then use them here.
If there are no more questions, let's thank the speaker again. And the last speaker of the session is Marek Dudyński, who I think from the title is going to tell us something about usefulness or facts and myths about using biomass as an alternative source of energy. Am I right?
Yes, of course, yes.
You are very welcome.
Thank you very much, everyone, to be here, because it will be the last today presentation. I make it something light, so don't be afraid. It will be maybe not so challenging as the previous one, but I still want to say something, because I want to discuss the problem of biomass burning. Biomass burning is very difficult. Of course, the burning at all of the any solid object is a very difficult problem to describe theoretically or to measure experimentally. The burning of biomass is one of the most difficult. Why it will be in the next, but we start my presentation with showing how universal problem the biomass burning is in our world. So I will start with first showing that the biomass burning can be observed as an organized form. It is the first on the small scale or the industrial scale. Industrial scale, it means that we can use the biomass in the specialized or the normal electrostation, and it is millions of tons sometimes per year in one installation, or unorganized form, which is well-known fire, everyone, bonfire is everyone, or the white fire burning, also very difficult and very interesting problem. And next, I want to show you the basic facts, which are not usually easy accessible. How much of this is really burned every year? So 4,000 million ton, 4 milliard ton, as we saw, or billion ton, as the English say, are there is burn left to decompose, which is getting from the plantation or from the wood cutting, forest cutting. Almost twice the time is burned in the wildfires. The amount of this means that 0.5% of all forest which is on the earth is burned every year. So usually the normal year of the most old forest we can expect is less than 100. Rest of this, from time to time, there is some drought, some very hot weather, or some accident, or some arson, which really burn almost all possible forests we can find in the earth, including Amazonia, Białowieska Puszcza, or other kinds of the we can expect it. Also, we can compare this with the amount of coal which is burned every year. It is almost the same number, also in the caloric value. So I cannot understand that probably you will show in the moment. You also cannot understand why we assume that the burning of coal is situ neutral. So, because the typical, how much of it is the maximal number for 1 hectare of the mature, very good forest. In Europe, it is close to 400 tons of wood. In tropical forest, it can be almost 600, because the tropical forests grow much more. And you show that usually the forests grow, we got some carbon sequestration, it is amount of this carbon sequestration, and also we got a credit in oxygen, because this carbon, all of the oxygen in wood comes from the CO2 sequestration. Usually we have some in normal wood we have 50% of carbon and 45% of oxygen and 5% of hydrogen. But all of the oxygen and hydrogen comes from the water, which is decomposed during the growing of the cellulose and other elements of the wood. All of the carbon is taken from the air and used in the process of the growing of wood. So we burn this 100 of mature wood. The process is exactly reverse. So we release to atmosphere such amount of CO2 and also use this amount of oxygen from the air. So whatever, it is much worse, because if we left in the wood, in the forest wood to decompose, it is in the very closed CO2 cycles, because they really decompose into the CO2, but because CO2 is heavy, it is left very low in the ground, close to the ground, and can be used by the next plant which is growing. Where we burn this, all of this CO2 is hot, goes very high into the air, and have usually no other part in the plant growing, which is usually say that it is the same process we are taking when we are growing the field. Also, the very simple calculation shows what means the CO2 neutrality, because it should be 3 points in between this, because I add 100 elements. It's showing what happens if every year I use for my heating system 1 hectare of the old forest, and on this place I grow 1 hectare of new one. So I calculate how much biomass I lost and how biomass I will produce during the 100 years of such an operation. And easy adding of this, but showing that in the best situation, when I really for every hectare put every hectare of the new forest, I got half of this which I lost. So I should at least attribute 1 ton of net CO2 emission to every 1 ton of the wood I really burned. Not 0, but 1 to 1. Usually it should be 1 to 2. So it is in the best situation we only have one half of this, which is similar situation when we burn natural gas. It should have the same elements of the CO2 for this. But it is for showing how really ubiquitous and surrounding us the biomass burning is on our life. But now I would like you some our recent research on this process, because we are starting to trying to understand the process of wood burning, and of course the process of wood burning is really not wood burning in fact, because there is not such a thing as a burning of wood in the sense that the oxygen from air attack directly the hydrogen or carbon in the wood structure. There is something quite complicated. I will show you. There is a process. We made a very detailed measurement of all these stages during the very high temperature gasifying, burning in the air. So the first process is a drying. And when you end the drying, you first start to see the pyrolytic gases, which start to burn. Really what burned during the wood burning is not a wood, but the gases emitted from the wood, which are burned around the wood and provide the high temperature for the process. The next process is a pyrolysis. It is the system when high temperature turn wood into the gas and the charcoal. And this is very interesting process from the point of view of physicists, because when we are observed, this process is very fast and can take seconds for such a sample like this, and takes a form of the shock waves. When we heat such a samples to the very high temperature around 1800 degrees Celsius, it is a moment when it starts on the left side and goes to the right in the seconds, like exactly like a shock waves. And this is something which really proceeds when you have a intense burning into the fire. You have shock waves going through the wood elements, which produce transport of the fire from one side room on the other, or one side of the building, and this transport can take seconds. This is why it's so difficult to evacuate people and so on. And as you see, the burning is only observed in the gases we are producing from this. And the next stage is the gasification, or this is the next step. There is a process when the CO2, which is present from these burned gases inside our samples, react with the carbon into 2C plus CO2 into 2CO. And these gases emit and also burn, but they burn without a flame. So we are not observing the flame. And there is a process on the end when there is disintegration of the samples. It is a moment when we lost almost 90% of the mass, when what is rest in the samples became not similar to the samples, but simply in the moment disintegrate in the very, very small particles. And we we wanted to, first of all, I will show, because we made a CFD and model simulation of this process. And these are our articles we show in the computer physics communication, which are will be show our collaborator in this process. Among others, this last one, which is from Brazil, used this model to calculate the fires in the Amazon forest recently. And next, we are going into the carbon structure. And the carbon structure is something which is responsible for this disintegration and also responsible for all possible hazards, health hazards we really have in during the carbon burning, and also influence on the human health, eventual the atmosphere and other things. I will come in the moment. First of all, it is a picture, electronic picture, because we have 200 microns, which showing how the structure of the charcoal looks. The next, we have a nanograph of charcoal, which shows that the piece of charcoal can be imagined like a collection of pipes, which walls of the different thickness, and these walls are made of carbon. And in these walls, the whole structure of carbon can be shown. And this structure of carbon is a very interesting and also very difficult to understand, because after the X-ray and other analysis, we found following how the structure looks. It is mainly made of the small graphene plates. 60% of this, which is present in any kind of the charcoal, is really made of graphene. So it turns out that it is one of the ideas, very simple, that it is maybe a good way to produce the tight cheap graphene or some graphene. But as you see, there is a problem how to understand how this kind of the structure can be produced and how can be reproduced also for the scientific investigation. Because one of the very interesting elements which are connected with such a structure, that if we take elements of the heated charcoal and measure the electric properties and magnetoelectric properties in the very low temperatures, it turns out that such samples have a metallic conductivity. I want to show you once again to appreciate that such samples, such made, when you put it in the Kelvin, 1 Kelvin temperature, showing exactly metal conductivity and also perfect magnetoconductivity, which is perfectly parabolic. Exactly, you can really show perfect parabolic by this magnet, and also show very interesting property. I don't want to dwell very much on this, but also show a very interesting, and I cannot understand completely, the so-called weak localization. Weak localization, it is something that if you measure conductivity, you see some peak in the zero magnetic field. And it is usually explained that it is by electron when electron acting with own field. And this is destroyed by magnetic field. This interaction of electron with their own field is destroyed by magnetic field, and this change conductivity in the zero magnetic field. And we show also such a interesting feature. But whatever. So how to how to produce this kind of structure. We start with the theoretical model, which goes like this, that we take a graphite, which is made of the graphene plate, which is stacked, and we, from this other kind of this plate, make such kind of the burnout with just stochastic, some stochastic probability. So this is which is light is what is taken out, and this is, for example, burn with 1/3 of the atom of carbon was taken away. So we goes on. There is much more. And there is close, and this is a very interesting moment. There is a moment where depercolation on the plate takes place. It means that this, what the atoms remain on the plates are not longer connected. So if it was be in the this 2 dimensions, it will break completely. But because there is a 3-dimensional structure, it still is connected and can be connected up to the 0.9% of 90% of the burnout. After this really breaks down. Why we goes to the 50% of burnout? It is different possibility, different way of the burn, because it depends if you have a probability of taking the carbon atom, if there have a neighbor was taken before or not. So there are different way of taking, but we have different patterns by this way. And the next stage we are going to do is to make a thermalization of this pattern. It means that because there are patterns made by purely stochastic process. And now we want to calculate how this shape will be when we assume that they can relax to the lower energy states possible with the taken into account that there are other patterns very close by. So this part of the work, as you see, there is much, and you can imagine this charcoal elements like a stack of the money of this element such band, put one close to another when the distance between them is exactly the same as the distance before when the original samples. And this work was percolation analysis was made with Maciek Levenstein during this sometimes, and we published already, and now is a continuation. This results show, among other, that whatever you make different percolation analysis, different percolation models, you still in 2 dimensions have a 1/2 only burnout possibility before this breaks down into the separate parts. But also possible 3-dimensional structure, it can be more connected, but with different curvature. We're also looking for the possibility that there is not a simple, very flat elements made, as I said, starting with the graphite initial structure, but with more complication, and this is also, but technically speaking, how to really calculate any kind of the electronic or pseudo-electronic structure for such a situation is much more possible, but with our Röntgen calculation and our data, it is also can be fitted to them, so the structure may be also like this. And what is important for all of the structure from the other reason, this is when we are, when we are going to burn on the next stage, it is the process of gasification, as I said. There is a moment when there is almost 10% or 8% of the mass remain, when all the structure breaks. And all these tiny graphene plates are emitted to atmosphere. It is something you can expect when you are going on the grill. Then when very close to the end of the grill, all of this graphene is present in your air around you, and you inevitably taken into your lungs and also to your blood system and so on. Also, most of this from the wood burning, also from forest, wild forest, also such kind of the graphene are going into the atmosphere. And there is quite interesting process which I want to analyze, that is a quite interesting problem for the future. First, to find a good theoretical description of the how goes into the atmosphere such a different carbon nanostructure, how they are flow, for example, how they are going into the water, how they are flowing in the water, how long they are present in the atmosphere. All of this, because they are very, very tiny, it means they have a 2-3 nanometers. They are very difficult to measure and are not present now in any kind of the understanding or measurement in the atmospheric physics. They are only can measure in this moment quite big droplets, 10 nanometers, 100 nanometers. They are never taking any kind of the measurement of the nanoparticles. And also description of the solar radiation, how it reacts with the solar radiation. It means that it is quite easy to understand how the big soot particle react with the radiation. There simply is a perfect black body. It takes radiation, heat up, and now we have a big particles, which is hot particles, which is surrounded by the air. And it simply goes, the temperature or heat from this particle goes into the, but if you take a graphene particles, first of all, only the 5% or 4% of the radiation is really taken by these particles. Also, it is some kind of take this photon and make excitation, mainly electronic. And next is a question, how this excitation is transferred into the air. Maybe it flows something like that, or wiggle, or doing any kind of development. So to understanding also the fullerenes. Fullerenes also, there are balls, but have only 64 atoms. They are also very small. How they are taking the radiation, how they are transfer this heat into the surrounder, it also, as I said before, measurement of how low concentration of nanoparticles is a very, very difficult. I talk with the specialized Italian group, And they say they have no possibility to measure such a things as like a graphene in the air, emission and so on. They measure a soot, they measure big particles, but never thinks about the measure something which is on the level of nanoparticle. And also because they are nanoparticles, there is no barrier between the lungs and the brain and the blood. So these particles very easily goes from the lung to the blood and from the blood to the brain, and what they happen and how they sediment, if they really sediment in the brain, is also open question. So I think nobody knows in the moment, but it can be quite interesting to know. Thank you very much.
Thank you. Let's thank the speaker. We have time for one question or two questions. Please.
So, is there anything quantum there?
What?
Is there anything quantum?
Is quantum, for example, first of all, there is a quantum problem in this electric and magnetic properties, because it seems to be the second problem which they show that there is no Anderson localization in such a material. And lack of Anderson localization can be, we can try explain in two different ways. First, we can assume that there is, because there are zero mass direct Dirac particles, because what is a localization for such a particles? And this is the subject you are working with Maciek and Janek there. If we can really show that for such a particle, zero mass Dirac particle, there is no Anderson localization induced by disorder. And we are in one dimension, this Maciek found a very nice exact solution showing that it is really the case. And now we are looking for the two-dimension problem. And the second possibility is that the structure is something like a conducting ribbons, which are entangled in many different ways, and electrons goes through these ribbons, and these ribbons are made by the somehow connected graphene plates. These plates really are not disconnected, but they are bond beat and form ribbons, and the electron goes through these ribbons and have this perfect metallic conductivity. And this is also completely quantum for the calculation and also for understanding.
Thank you. Any more questions?
I have a very classical question. So you mentioned the system which percolates and in which the probabilities are distributed non-uniformly.
Yes.
So in the uniform case, there is this concept of percolation threshold, which is essential in the description of percolation. How do you generalize this concept to this non-uniform case?
So we do very similar. This means that we made a concept. We're looking for the percolation for the two-stage model. First, when choosing a particle, when this site is occupied or not, is a Poisson process. And also when you have this site occupied, you choose how much connection it have. This also independent Poisson process. And for such generated system, you also have the percolation threshold, which for 2 dimension is 1/2, and for 3 dimension is close to 0.92 or something like that. This was made, the 1/2 you can show also more or less theoretically, but for 3 dimension it is made by the calculation, numerical calculation.
Thank you. Any more questions? If not, let's thank the speaker again. And that concludes our session. Thank you very much. And according to the program, we still have a poster session. Everybody is welcome to participate, discuss posters with the authors. Thank you very much.
I would like just to add that the food will be served there, so please go there.
Okay, very good idea.